through this cable and the grid is charged. So that such things are also taking, like I attended some, like in Hong Kong and many other places, this is also taking place. So all these things are just evolving, and it is interesting to note how things evolve.
Sir, two more things, if may I.
Please, sir.
Sir, next, I just wanted to know that that spoke about the different charging levels in the same station. 3 outlets are there, depending on the QR code. Then I might think that the tariff is also different for different charging levels. So how the common people, just like I know what is the price of diesel or petrol in my state, in other states. So how the common people will know about the rate at which pump it is there, or suppose a pump is just you have one of the pictures that ACDCL has a pump. Similarly, there might be some private owned things also. So does the tariff is different or the tariff is similar for similar pattern of charging and for different pattern of charging?
Sir, these are interesting questions, and I do not know the exact details. I will try to come up with the answer on Saturday. But to the level that I know, that this charging is not only based on the kilowatt hour also. This has a component of time also. Like the thing is, like suppose you have put your car on charging, and the battery is charged up to 90%, and there is only, it will take much more time for the last 10% to get charged. Then they will start charging based on the time that you are booking that slot. Even there is a loitering charge. Loitering charge means, suppose your battery is fully charged and we have gone somewhere, your car is fixed in that charger, you have not disengaged. Yeah, you have not disengaged, then also you get charged for, that's like waiting charge and all these things. So the charging is not exclusively based on the kilowatt hours, but it has some other components also. And so I think it depends on the time you occupy that space of charging. So there are different components. But your question is like, and for the DC power and the AC power, is there any differential billing, or it is the same thing?
Sir, one last thing, sir.
Right, sir.
Hello, sir. One last thing, sir. I'm very sorry for that, but I had a few queries.
Please go on.
That. So, sir, what happens in a hybrid vehicle during it? Hybrid, there might be a fuel, and there is EV also. EV portion is also there. So during charging, we are aware about that during charging from a fuel, a little bit spark, it may be little. So in that case, how the charging will be managed for charging a hybrid vehicle?
Sir, I didn't get your question. You are asking that how to charge a hybrid vehicle. Is that so?
Yes, sir, because it has both fuel and so in that case, electricity coming in contact is near to the fuel. So that may be dangerous or some problem may be there. So how that is tackled in the petrol pumps? Charging stations or in petrol pumps?
No, see, actually what happens in these hybrid vehicles is that the motor, see, in any case, for all vehicles, we have a starting alternator that they say, okay, so which cranks the motor first. So that is in any case for all vehicles, including diesel, petrol, everyone, there is a cranking motor, and that runs on the battery that we generally put up in our cars, 12 volt something of some power. So in a hybrid car, what happens is that motor is a different motor, but it is actually an electric motor with much more power, and the battery is a lithium-ion battery, which generally they keep inside the, I think in Maruti case, they keep under the co-driver's seat or something like that. So when the car first cranks up, this battery only supplies the power, and during the acceleration process, this motor also adds to the torque, and during the braking, this absorbs the energy. So the electrical system is somewhat like already existing in all cars for say so many decades, maybe like from the time these cranking motors alternators are there, the starter motors as we say, because the starter motors are generally replaced by these smarter uh, motors, which are generally maybe like induction motors or permanent magnet synchronous motors, and that is controlled by the like controller in the car. But the as you were wary of, like you were thinking that might be dangerous, it is not any more dangerous than the cars that we already use, which are not hybrid, because that much electrical wiring and all these things are already there. Am I able to convey the idea, sir?
Yes, sir. Thank you. Yes,
Right, sir. Any other questions, sir?
sir. Not from my side. Thank you, sir. Sorry for troubling you.
Please, this is very interesting. And Mr. Rajesh Guria, you have some doubts.
Yeah, am I audible, sir?
Yeah.
Okay, yeah, very good evening, sir. My name is Rajesh Guria. I'm from Dumka Engineering College, Jharkhand. Actually,
evening,
I have two questions. First question is that you have told about the charging in no time, right? For that case, you have told that battery swapping. For
Yes.
for battery swapping, so all the position of the battery should be the universal for all car design or all two-wheeler vehicle design. So, is it possible to create the universal design set for the battery position?
Yes. See, I don't think battery swapping is a feasible option for these vehicle cars and personal cars, which have, so like in the personal cars, the battery is kept in the very like just above the chassis, very much embedded within the car. It is not possible to just swap it. But in case of these battery swapping are being used mainly for three-wheelers like Toto type batteries, which generally carries loads. So in those cases, I think they have standardized some sort of battery, and it is standardized. Like for a Toto battery, if you for these auto rickshaw batteries, like electric auto rickshaw batteries or these Toto batteries, these are standard batteries, and those batteries can be swapped easily. And those batteries are also having some sort of a chip, and I did like RFID chip, and the to find out how much charge is there, to identify the battery itself. Those are there. So those sort of batteries which are universal, and we know the basic lead acid batteries which these people use, those can be swapped, but it is not feasible for the sort of lithium ion batteries which are there in high end cars and passenger vehicles. I don't think it is feasible, or such logistics is easily possible. Sir, am I able to explain the situation?
Yes, sir.
Right. Any other questions, sir?
Actually, one another question was there. What are the different tariff plans? Already, sir has asked this question, and you have told that you will get the answer on Saturday. So I will wait for the answer. Different tariff plans for the government EV charging station and private EV charging station.
Yes. That is a very practical question. I think I'll try to find out that at least in our area, like WBSCDCL or CESC, what are the tariff plans they are using and how they are charging.
Yes, sir. Okay, sir. Thank you, sir.
Right, sir. So let us now go to the next section of EV charging, which is protocols. Like there are so many, like for this EV charging system needs some protocols. Why is the protocols required? One is payment integration, so that when you are like there are so that there is a seamless payment system works. Like maybe UPI, maybe from your bank, maybe from your credit card. So for that you need a protocol, seamless billing of energy consumed and charging the same to the vehicle asset owners. Next is interoperability. This means generally the EV infrastructure, the EV ecosystems work like this, that there's a company who has a network of EV chargers. But he is not the manufacturer of the EV chargers. He buys EV chargers from the market as per the market rates and from different manufacturers. So for all the EV chargers that the EV charger manufacturer makes, it needs to be compatible with the network person. For that interoperability, he says that, okay, is your EV charger compliant to OCPP or something like that protocol? If yes, then they can just connect it and the communication will work. So that is for interoperability. Then there are, of course, standards like requirements for safety standards. There are different safety standards like in what case the charging should stop so that there is no hazard, overcurrent, and maybe arc leakage and other such situations, high temperature and such situations. Then, of course, the other thing is charging efficiency. Like the protocols are there to communicate with the electric vehicles about the state of charge for the vehicle, so that, like, lithium ion charging is a bit tricky system, and if you charge a lithium ion system beyond its capacity, then there can be an explosion also. So to take care of such things, and so that the charging is done at a fast rate but not at a dangerous rate, these protocols are required. And as the market is growing very fast, of course, we need such standards. So this is the requirement for EV charging protocols. The main protocols that are being used nowadays are the Open Charge Point Protocol, OCPP. Then there is CCS, there is CHA demo, and of course there is Tesla's NSEC. The Open Charge Point Protocol, or OCPP, is a key standard that allows chargers from different manufacturers to communicate with the central management systems, or CMS as they call, ensuring flexibility and scalability. Other standards include the Combined Charging System, CCS, popular in Europe and also North America, the CHA demo for Japanese vehicles, and Tesla's North American charging standard, NSEC, which is increasingly adopted by other automakers. These standards ensure EVs can charge across various networks, enhancing user convenience. Now, as you understand that if an EV owner should be able to go to any geographic area and get his vehicle charged, so this interoperability and the standardizations are very important. And that is why we need charging protocols. In India, if you are a EV charger manufacturer, you have to be compliant with OCPP. OCPP protocol is a published protocol. You can download it also. There are, I think, there are several versions of it, and from there, the exact physical parameters like voltage, current, power factor, and whatever the voltage, DC current, and all such things are already mentioned, that whatever needs to be communicated to the central management systems, and how the central management system will start a charging, when it will stop a charging, then how it will manage the booking of a slot of a charger, and all those things are predefined, so that you do not need to make your own protocol. Now, coming to Open Charge Point Protocol, an open source protocol for communication between EV chargers and central management systems, developed by Open Charge Alliance since 2009. Now, there are various versions of OCPP. I think these are the like OCPP 1.6 was developed in 2015. Then OCPP 2.0.1 came up in about 2020. We ourselves had done something on OCPP 1.6 in 2018 for some EV charging manufacturers. It like we implemented the whole embedded systems. Like it is just these systems on the networking protocol and everything. Then OCPP 2.1 has come in January 2025. This has a very big development that in OCPP 2.1, they have added the provision for vehicle to grid capabilities also. This means that not only that the power can flow from the grid to the vehicle battery, but the power can flow also from the vehicle battery to the grid. Now, why do you need it? Since electric vehicles have got a big battery, so this battery is at many places, or in future it will be here also. I don't know if this feature is already used in India or not, but of course I know that it is being used in Hong Kong and other such places. So what happens is that to stabilize the grid, this facility is that the battery of the EV is used. Like when there is surplus power in the grid, then these vehicles are used to absorb the power. And like in the morning or in the evening, when there is a dearth of power in the grid, then it is augmented by the battery of these EVs. Of course, if the battery of the EVs is required to be used for this system, the EV needs to be docked into some charging station. But still, I think there is some sort of an incentive given to the EV owner so that his battery can be used to stabilize the grid. Now, the benefits of OCPP is that it ensures vendor agnostic interoperability, reduces cost, and supports scalability. Adopted in 137 countries as of January 2025. Technical aspects, actually it uses WebSockets, of course. In TCP/IP packet formation, it uses WebSockets for real-time communication and supports encrypted data for security in the global networks. Now, one thing is that there are other protocols also, like there is this combined charging system protocol, CCS, supports AC and DC charging up to 350 kilowatt, dominant in Europe and North America. There is also CHA demo used by Nissan, Mitsubishi. This supports up to 150 kilowatts, prevalent in Japan. And there is NSEC. It is Tesla's standard, now adopted by other automakers. Supports high power DC charging. There are some other protocols also, like OCPI, OCHP, and other such things. Like there are like Solid Studio is a company in European company, a Scandinavian company which is into developing many such standards. So these things that there are some standards, some things are getting more accepted, and it is a dynamic situation. Regarding that, this CHA demo, that is a Japanese system, is generally getting replaced by this CCS, combined charging system. I think that is gaining much ground, and Tesla system is also gaining much ground. Now, one thing I want to point out between these protocols and OCPP is that these protocols are for DC charging, fast DC charging. So this protocol is a communication between the battery, the EV charger, and the car, the EV. Whereas OCPP is a communication protocol between the EV charger and the central management system. So OCPP does not compete with all these three things. OCPP is used at a higher level between the EV charger and protocols are generally used between the EV charger and the EV itself. Now let us go a bit deep into the EV charger communication network and how the whole thing is set up. Now you will see that this three-phase forward is a three-phase system which comes through SPDs, that is surge protective devices, and other switch gears for protection. And this goes to a auxiliary. This is an auxiliary supply for 12-volt DC power supply to the auxiliary systems. There is another line that is going. This is for the AC charger. This is nothing but a contactor. So this contactor, this is a level 2 type of charging. So if someone wants a AC charger where the AC energy will be used by the onboard charger itself for charging the battery, he will opt for this option. And the third is, the most powerful thing is this one. So three-phase supply comes to this power module. This power module, we can go into the details. Like, this is the main power electronics device which converts the AC power into DC from 700 volts to 1000 volts level. And this is a DC fast charger option. So you can have either this or this. And this is a connector. This connector shows that the lower two connectors are for the DC powers, and this is for line 1, line 2, line 3. These are the three phases for for when you are using the onboard charger of the EV for the AC charging level 2 and neutral. And the other connectors are for communication. This is the CCS controller. Like, this is running on the CCS protocol. Now this controller communicates with the AC and DC energy meters. Typically, this AC and DC energy meters work on some protocol like Modbus over RS485, which is very standard. So the AC energy meter monitors how much energy is coming in, and the DC energy meter monitors how much energy, DC energy, is going to the battery. Other than that, there's a communication with the HMI, that is the LCD. Then there's a RFID communication. The RFID, generally the vehicle owner shall have a RFID card with which he can enable the charging. Then there's a LED and push button for other interfacing. There is a CAN connection between an insulation monitoring device and the cables, the DC cables that are pushing the power, so that the insulation is monitored online, so that there is no like insulation failure or short circuit happening when this huge power is flowing through the from the power module to the electric vehicle. And there is, of course, this communication between the electric vehicle and the controller directly. And now this connection is for the OCPP portion, like where it is connecting with the central management system. So this is a microcontroller based system. It has all these ports. This is a power electronic system. This is a switch gear, and this is a input protection system. This is the auxiliary power supply to power all these systems, and these are the peripheral systems which are being controlled. Now, coming to this power module, suppose like what I discussed previously, like these power modules are of the power level of up to 350 kilowatts. Generally, here in India, we find up to 150 kilowatts. Now, 150 kilowatts is actually quite a big power. So generally, these modules are made with stackable AC to DC power converters. Like each converter is generally about of the rating of 18 to 30 kilowatts. So such power supplies are stacked in a rack. All those power supplies have a network within them, and there's a controller for all those power supplies. That controller actually communicates with this controller. And that stack, like that is also a very high power density stack. Such power supplies are there in the units that I had already shown in the picture. So those stacks are there, and those stacks are also nowadays something is manufactured in India, but those stacks, as far as I know, are mostly getting imported from China or somewhere. So this is a whole EV charger like technology in the block diagram. Let me go to the second screen. This is a bit different version of the same thing. Here, basically the same thing. Here you will see that there are like a bit more details, like the auxiliary power supply will have these DC-DC buck regulators of different voltages for the controllers, for the sensors and everyone. This is a MCU or MPU. And this MPU will have this CAN transceiver, operation amplifier, and all this sensor. This is the front end processing to get the voltage and current. Here, what is being shown is the ADC of the microcontroller itself is doing the energy monitoring, whereas in the earlier case, in this case, the energy meters were different and it was communicating on Modbus with the controller. Both the things can happen. So in this way, it is doing AC energy monitoring, DC energy monitoring, CAN transceiver. Now, one important thing for this whole technology is a PFC. This PFC is a power factor correction. Now, since AC power is getting converted into DC, a normal like bridge rectifier can be a solution, but here it is not acceptable because the power factor will be very bad. I think the power factor for a normal rectifier will go down to 0.7 or 0.65 or something. But these PFCs, these are generally bridgeless PFCs. So these PFCs are synchronized with the incoming supply, and there are no rectifiers as such. These are all MOSFETs or IGBTs, and like there are nowadays silicon carbide MOSFETs and gallium nitride MOSFETs are also being used, which are even higher order efficiency. So there's a PFC section, and after the PFC there's a DC bus, and this is a DC to DC converter. As I was telling you that there are stackable 30 kilowatt DC-DC things like this. So the PFC is also stackable and the DC-DC converter is also stackable. From there, it goes to the EV. These are, so I think in these two diagrams, any questions? Shall we discuss anything deeper? Okay, so let us go ahead. These are different connectors that are being used. So as you will see that, and this is something very important, like in the picture that I showed you in the of the EV chargers installed in Kolkata, there you would have seen that these pictures of the connectors are there. Now, compatibility of connectors is one of the most important thing. If the connectors are not compatible, you cannot charge your vehicle. So I think the vehicle that we were seeing in was of this CCS2 sort of configuration. Now these, like as you will see that probably these are AC connectors and these are DC connectors. For the ACs, like these are for the 3-phase and these two are for communication. This is also practically same. Here they must be having more communication lines. And this is for this. And these are the DC chargers. In DC, you will find that there are two DC plus minus big things. And but these also have the AC points in them. So for these chargers, it is selectable that whether you will have a level 2 charging or a DC fast charging. Level 2 charging, if you have time, it is very safe because the charger, you are using the onboard charger, which is compatible with the battery made by the manufacturer. And if you have a provision for DC charging, you can also use this thing for fast charging. This is for CCS1. This is a charger for CHA demo. That's a Japanese protocol. This is for CCS2. And this is for, I think, Tesla, a different sort of connector. Just I had tried to find out one like details of this connector here. So as you will see that this is a J1772 charger pinout. This is a J1772, and this L1 carries the primary voltage. This is the neutral. So this is a single phase AC charger, and these are for this line and this line. This is for enables communication between charging station and the vehicle, regulates the controls and charging process, and this is the earthing. So this is basically line, neutral, earth, and these are for communication. Any questions regarding these networks and protocols? Okay, so next we can go into the details of a DC level 3 fast DC charging station. Here, this is into the actual power electronics. This shows a 30 kilowatt Vienna configuration of PFC block diagram. As you will see that this is a like PFC block where there are silicon carbide barrier diodes and silicon carbide MOSFETs. Like there can be other configurations also for 3-phase PFC blocks. So, but this is one that is used by quite a few manufacturers. Here we see that the 400 volts 3-phase power is coming, and then this voltage is isolated. This voltage isolation can be done by either by potential transformers or linear optocouplers, or other dedicated ICs are also available nowadays. Potential transformers are generally very robust, but it is slightly costlier and bulky. whereas other electronic chips that are used are generally cheaper and less bulky. Linear optocouplers are also a very well established system, but linear optocouplers generally need some sort of calibration, because these optocouplers always change characteristics from one piece to another, and so a calibration becomes important. So this three-phase AC voltage is sensed here. Then there are three current sensors. These three current sensors can be also CTs again, but again CTs will be bulky. Otherwise, this can be LOCs, or this can be Hall current sensors. Generally, Hall sensors are quite suitable for these applications. So the Hall sensors, through some operational amplifier and AC current sense, this goes to the digital DSP unit. So after the input, all the three voltages and three currents are sensed in this digital signal controller. Now you will see that there are three inductors. These inductors are required for the PFC, so that the current can be shaped in like a sine wave, by suitable switching of these silicon carbide MOSFETs. Silicon carbide MOSFETs are used because they can work up to very high frequencies, and in a configuration, the dead time can be reduced also. So these are the modern systems for high power PFCs with high frequencies. Here you will see that that this is a high voltage DC output. The high voltage DC output through isolation is also sensed, the output voltage sense. This voltage is of the level of 700 to 1000 volts. This isolation is also done generally by either by dedicated chip or linear optocouplers. For driving these MOSFETs, you need an isolated gate drive for all these MOSFETs. And for the isolated gate drives, you will also need isolated power supplies, which have to be arranged for. Then the PWM will come out from this digital signal controller and control this PFC. This is a total digital design. From here, it's a HV bias supply from which this DC-DC and LDOs can take power supply. So one thing you will see that this, even if this is not working, this is generally a three-phase rectifier. But when this starts to fire, then it becomes a PFC by adjusting the current. And along with this digital signal controller, there is a temperature sensor. These temperature sensors are generally for the incoming, the air that is getting heated, how much the air temperature is there, that is sensed. And the heat sinks are also sensed for the temperature. Generally, we use NTCs, isolated NTCs, like as temperature sensors for these systems. Then there is a E-square prom, other security, and other clocks. So this is a typical arrangement of the PFC section. But one thing I want to make sure is that there are other PFC configurations also. This is just one of the PFC configurations which are used. Any question on this PFC section? Hello. Am I audible?
Yes, sir, you are audible.
Okay, right. I was just expecting some response. Right.
No, you are audible.
And this is a DC to DC section of the fast charger module. So here you will find this is the output of the previous section. And there is an isolation between this. This is what it is doing is isolating the DC power from the input AC section, which is important. Whatever power goes into the vehicle must be isolated from the supply power. So this is a high frequency transformer, and so this is generally a resonant DC-DC controller, DC-DC conversion is used. For that resonance, some capacitance and inductance is given because that resonant conversion is of highest efficiency. These are also of silicon carbide MOSFETs, and the secondary rectification is also done by silicon Schottky diodes, silicon carbide Schottky diodes. Now, this can probably be to enhance the efficiency. This can be also made for synchronized rectification, but here they have used silicon carbide diodes, so that is also very efficient. This inductor is, of course, very much required. And then this is the HVDC output. So this is the output that is going to the actual battery. This battery, like it is of the level of 700 to 1000 volts, because so many batteries are in parallel, individual battery blocks. This current is again a DC current sensor, and it has to be of like a Hall sensor sort of thing. Since it is on the power side, it cannot be a shunt. It has to be a Hall sensor. So this Hall sensor is sensed through an op-amp to the DSP. Then this DC voltage is also sensed through some LOC, linear optocoupler, or some dedicated chips with some isolation through an op-amp to the digital signal controller. Now these op-amps are generally, these are second order filters. The filters have to be tuned for so that the noise does not come into this DSP. And but the bandwidth should be such that during a short circuit or some transient, the DSP should be able to sense the transient very quickly. So generally, what we see is the bandwidth of this is at about, say, 100 kilohertz or so, because the switching of these things are of the order of 60 or 70 kilohertz. And for the PFC, the switching is of the order of 25-30 kilohertz. And for this DC-DC conversion, of course, the more higher we go for the conversion frequency, these magnetics can become smaller, but there is EMI-EMC problems as we go higher up in the frequency with such large power. And to manage the EMI-EMC is a very big thing. All these things need to be compatible to EMI-EMC standards so that they do not disturb any mobile communication or any other things. Those are very standards, like you have to get certifications from EMI-EMC certifiers so that your system is compatible. Here also those things are this same DSP through isolation again communicates with the CAN transceiver and Ethernet and all these things. This CAN communication is for communicating with the vehicle processor. This Ethernet is for the OCPP type of communication, which goes to the higher level management systems. And of course, there is this temperature sensor, this E-square prom, and this thing, just like what was there in this system also. This is just getting repeated. So these two diagrams, I think, gives the essential power electronics configuration of the EV charger, of the DC EV chargers, DC chargers basically. And as you can understand that 30 kilowatts of power is flowing through these things, and there are stacks of such things to make up to 150 kilowatts or 200 kilowatts of EV chargers. So this is of very high power density. Heat has to be managed very efficiently, and these are very sophisticated systems, like very highly power dense systems nowadays. Any questions from this DC to DC section?
Sir, may I?
Yes, please.
Sir, how the reactive power balance is managed in a charging station which is connected to the grid?
Okay, so reactive power, see, when we have a PFC, like power factor controlling, so that means this section is already ensuring that whatever current is coming is in phase with the voltage, like the voltage waveform and the current waveform is in sync, so that the power factor is nearly 0.98 or 0.99. I'll say 0.99 only. So since the current and voltage is already in sync, you are not taking in any or giving out any reactive power, either like capacitive power or inductive power.
Okay, thank you, sir.
This PFC is taking care of like managing, or I will say neutralizing all sort of reactive power from the supply. And from the grid point of view, this is just a resistive load. This is not an inductive load or a capacitive load because of this PFC. And that too also, it's a balanced resistive load from the point of view of the grid.
But sir, there are so many power electronic converters. So they are somehow in the grid side, they are reflecting as harmonic distortions. So the power factor is totally taken care by that PFC here due to these interfacing power electronic interfaces.
Yes, what you told is very true for all sorts of power electronic things, 90% of them. But that is only when you are using like a uncontrolled rectifier or a switching system. If you are really using a PFC, the PFC will always manage the current so that it is in phase with the voltage. Only thing is, since the frequency of the PFC is say 20 kilohertz, that means you will have harmonics above 20 kilohertz or so in the grid, and that is for the grid, that is nothing, because the transformer and other things will eat it up. That so such high frequency components doesn't affect the grid. The grid is affected. So if the 50 hertz is a fundamental frequency, then the grid is affected, say up to 20 times that thing, but not above 20 kilohertz or something. So first harmonic, second like say third harmonic, fifth harmonic, maybe there are even harmonics also. But after 12th or 15th harmonic, it is insignificant generally. So here the current is also balanced and the harmonics are also taken care of. Like this PFC not only takes care of the phases of the voltage and current, but it takes care of the harmonics also, so that it is called the current THD, ITHD, and is also very low. The ITHD levels are, I think, lesser than 3% in these cases. Yeah, that is a general standard that is considered. So the current THD is also low and the power factor is also very near to unity, that is 0.99. So in that way, so this does not disturb the grid, though huge power is being drawn from the grid.
Thank you, sir.
Anything else, or I think we can recapitulate what we have done, because the next section we can start on Saturday otherwise.
Yes, sir.
So any questions about the whole thing that we had studied today, or you can send me by email or something also. And of course, I will try to find out the very interesting query about the differential tariffs for different cars and what is going on. So I will come up with that answer. Madam, do you have any other
Thank
questions?
you, sir. No, it's okay, sir. You continue, sir.
So, no, I was telling you that should I continue on Saturday, or I think it is about 9:25. Should I start?
Yeah, you can stop here. Yeah. You will continue the next day, Saturday.
Right. Thank you, madam. So, anything you want to summarize, or what is how we are doing it, or what will be your expectation on Saturday, and any feedback from you, madam?
So we will let you know. Okay.
Right, madam.
Okay. Thank you, Somnath
Thank you.
sir, for your wonderful presentations. We have learned many things from your lectures, like DC fast charger, wireless charging, battery swapping. These are due to us. Participants may have questions. So in session 12, that is day 6 on 27th September, 3:30 to 5 p.m., sir will be there. So if you have any questions, so that time you can share. So we will learn more about charging infrastructure that day. So thank you, sir, once again. And good night to all of you. Tomorrow at 6 p.m. we will be online again.
Okay. Thank you, madam, and thank you to all participants.
Thank you, sir.
It was very interesting to get the feedbacks, and I understand everyone was very involved. This is though this is not a deeply technical or something like it is not too technical, but it is very relevant subject, and we should be aware of it. And this is the upcoming technology, and
Exactly.
India, I think by 2030 or something, there is some limit that we have to become carbon zero CO2 system, like carbon neutral or something like that. This is very much required. So I think this is a very interesting topic that I got the opportunity. While preparing all these things, I learned many things also. And by interaction with you, I hope to learn many things myself. Thank you, madam. Good night.
Sir, if possible, please share some videos so that we can see your infrastructure as you are working in EV.
Okay,
in
sure.
Institution level, it is we don't have that much of infrastructure, no? So we want
that
to
will be
see
interesting. Yes, of course. Thank you, madam.
Thank you.
Good night, madam.
Good night,
sir. With the feedback links are shared in the chat box.
Chat box or in WhatsApp group?
Yes, already
Madam?
it is given in the chat box.
Oh, yes, it is already given. So participants are requested. Fill up this form and submit it. Madam,
Two feedback forms are there. 2 feedback forms are there for session 1 and session 2. Okay. Please try to submit that 2 different feedbacks for 2 different sessions. Okay. Thank you. Good night, everyone.
Good night.
Good night. Thank you.
Okay, we are He is an associate professor in the School of Electrical and Electronic Engineering at the Singapore Institute of Technology and Deputy Director of the SIT Teaching and Learning Academy at the Singapore Institute of Technology. His expertise lies in power engineering with research focusing on microgrid, smart grid technologies, advanced metering infrastructure, renewable energy, electrical vehicles, and energy storage systems. He holds a PhD in electrical and electronic engineering from Nanyang Technological University, that is NTU, where he also worked as a research engineer and fellow. He is a registered chartered engineer and senior member of Institute of Electrical and Electronics Engineer, that is the IEEE. He earned his Bachelor of Engineering degree in 2007 and PhD in 2012 in Electrical and Electronic Engineering from Nanyang Technological University, Singapore. His professional journey began as a research engineer at NTU in 2011, progressing to research fellow, then lecturer at Nanyang Polytechnic, then assistant professor at Singapore Institute of Technology at 2019. And his current role since 2023 and 24 is as an associate professor. A chartered engineer and a senior member of IEEE, Dr. Sibanishan holds membership in IET, IES, and other bodies, including serving as executive committee, member of IEEE Power and Energy Society, Singapore chapter, committee member of Singapore Smart Grid Working Group. His research focuses on microgrid, electric vehicle, as I said, and he has received grant around $14 million as grant as a principal investigator at COPI. Notable projects include Electric Harbor Craft Onboard Microgrid at $1.99 million. This project is ongoing, and Microgrid Digital Twin Development is $1.86 million. It is completed. His innovation include a 2022 licensing agreement with EA Technology on partial discharge diagnosis. Award highlighted his excellence, Best Paper Award at ICPEA 2022, Teaching Excellence Award at SIT 2022, and Educator Achievement Award at Nanyang Polytechnic in 2018, and Best Innovation and Renewable Energy at NSEC Award in 2012. He has authored 17 journal papers in high-impact outlets like IEEE Transaction on Power, Delivery and Applied Energy, 21 conference papers, and 2 book chapters on energy storage and EV integration. His work is advancing sustainable solution for Singapore's energy sector, blending academia, industry collaboration, and practical applications. So now, we understand he is a really resourceful person, so we will enjoy his lectures. Thank you, sir. You can start your lectures.
Thank you, madam. Thank you for the introduction. And very glad to be here today. Let me just share my screen first.
It is visible, sir.
Okay, thank you. Again, thank you so much for inviting me to give this lecture, and it is actually a very useful topic and something that is very close to the things that I'm doing now. So I thought it is also nice to just share about, some of the work that we are doing in SIT. So before that, I'm an associate professor in Singapore Institute of Technology. So I just wanted to, before I start, I wanted to give a a very quick overview of SIT. This campus that you see on the picture is our new campus that we just moved in last year. So so who we are basically a University of Applied Learning, and we offer industry focused degree programs. So our aim here is actually focused on growth industries. So we very much focus on industries that are growing, especially in electrical power and energy areas, as well as semiconductor and so on. But one thing that differs us is our focus on industry, which means that whatever we do, we are not driven by, for example, journal papers and so on, but more on projects that we get from the industry, solving their problem statements, licensing our IP to them and so on. So that's basically our KPI. And because of that, what happens is that we want to also teach our students what is useful for the industry. So very much our programs have very less exam focus, very much on assignments and projects that require the students to do something rather than just show that they know. So that's basically who we are. And we are the third largest university in Singapore. So first one is NUS, of course, and then the second one is NTU. By number, we are about 11,000 now. So we have 11,000 students, undergraduate students, about 1,000 of us as academic staff and research staff and students and so on. And 40 undergraduate programs, 8 postgraduate programs. And we have also one thing, new thing that we started last year was something we call stackable micro-credential programs. That means that you can stack different micro-credential to form a degree. So that's something new in Singapore as well. So in total, we have 11,000 students studying about 40 programs. So quite a large university in Singapore's context. Of course, we are not talking about don't compare with India. We are divided by not schools. We call it clusters. So I'm in the engineering cluster. We have chemical engineering and food technology, infocom, health sciences, and design schools and specialized business. We also work with overseas university partners. For example, the electrical power engineering program basically works together with the Newcastle University, the UK university, but then they have an office in Singapore. So this program is basically jointly offered by SIT as well as Newcastle. So similarly, we have other programs. For example, Culinary Institute of America basically offers the culinary programs and so on. So that's basically the way we operate. One thing very nice and useful was when we moved to our new campus. Before we moved, we actually designed the campus from scratch. So we had that opportunity to do that. So what we did was we designed it to be a microgrid that is live and test baitable. So it's not a microgrid that's just very static that you can just consume the power or generate power, but then it is something that we can install new devices or collect data, change the energy management algorithm and so on. So it's a test bed that is very live and operatable by our staff. And so this very first live microgrid test bed actually within APAC region, in fact, so within a university campus, And so this is where the students and industry will come and work together with us to implement test bed new innovation. And we are located very close to the industry. So this is where the industry are located. So and SIT is just close by. So there are a lot of small, medium enterprise and large companies that houses their offices and industry plants here. So we can then go collaborate. The students who can go for internship and then come back for class and so on. So there's some kind of ecosystem that we have developed here. And so there are a lot of partners that we work together. Something that relevant to electrical power engineering. So the campus microgrid basically has about 1.8 megawatt peak of solar PV system installed at almost all the rooftops of the building. We have 3 megawatt hour in total, an aggregated 3 megawatt hour of battery energy storage. They are located at 5 different sites. Yeah, they are located at 5 different sites within the campus. So they're located at 5 different sites within the campus. Because of safety and regulation in Singapore, each battery cannot be more than 600 kilowatt hours. So each of them 600. We have 5 of them located within the campus. This will allow us to basically test, for example, distributed energy sources. So the energy management system can operate the different battery at different times and or aggregate them to produce more power. So distributed ESS can be tested within the campus. We also have about 68 charging stations, fast and slow. And on top of that, we also have what you call vehicle to grid charging. So none in Singapore. There's no Singapore charger that is capable of vehicle to grid. The cars are, but then the chargers are not capable. It's not bi-directional. So we have a new project that actually allow us to test bed 10 charger and then aggregate them for vehicle to grid dispatch to the buildings. And so that's the reason project that I'm doing. Also that these buildings are basically can be islanded. So we cannot island the whole campus because the solar PV generation is only about 10% of the campus maximum demand. But then what we do is we are able to isolate buildings. So for example, the building E6 here can be isolated at the building level as well as the floor level. So at the building level, we call it a nano grid, and then at the floor level, we call it a pico grid. So we can isolate them, and then they can be supplied by the battery and the solar PV only, and so on. So the synchronization of the grid connection and all these can be tested. New algorithms can be developed and so on. So it's a test bed as per se for us to use it for electrical power engineering related researchers. Okay, so that's just a very quick introduction to SIT, where I come from. So today I will just focus on 3 important topics in the part where we are talking about charging management system. But before I go to charging management system, I wanted to share a little bit more about the electric vehicle charging system as itself, because by knowing what is inside the charging system, we will be able to understand how we can manage them. And then I will talk about the charging management system and the smart charging management system, including the V2G part of it. So that's basically the outline of today's presentation. And please feel free to unmute yourself and ask questions. I will stop and then we can answer. We can discuss your questions as we go. I don't have to wait until the end. Okay, so before I go on to the charging management system, so we want to talk a little bit about the electric vehicle charging system, right? But before that, we will just for completion's sake, I want to just introduce the different terminologies that might come in my presentation. So I think we all are very familiar that ICE vehicle, internal combustion engine vehicles, petrol, diesel type of fuel-based vehicles. There's no charging, there's no plug-in required. Is what most of our vehicles are now today. And then we have the hybrid electric vehicle, which is not half lah. Is a electric vehicle, but then doesn't need to be plugged in for charging. The charging happens through regenerative braking, right? So there's no tailpipe emission when they are idling or going slow because it's supplied by the battery. But when they are going fast or they're accelerating, it still uses the fuel. So it's not 100% clean. That means it's not like zero tailpipe, but then emissions are much lower now. So these vehicles are very much what you call mature in the sense of its development in terms of its technology. And then we have the plug-in hybrid vehicle, which has a larger battery. Can we have to mute please?
Ma'am, can you please mute everyone?
Yes, sir. Yes, sir.
Ma'am, please. Yeah, please mute others.
Okay.
Lot of noise.
Yeah, thank you. So I think they're in temple. Madam, would you be able to mute them? Ravni, madam, can you, sir, can you mute yourself? Okay. Okay, I'll just continue. Hope you don't mind. It's getting louder. Okay, thank you. So the other one is, of course, the plug-in hybrid electric vehicle, which is larger battery capacity, which can be plugged in for charging, and then they can travel further. Again, there are some portions where they will still use fuel in terms of gasoline, petrol, or diesel. But then a full charge can actually bring them further. They can use it for acceleration as well. And of course, the one that we are looking out for is a battery electric vehicle, which are purely energy storage based. There is no need for buying petrols, and there's no tailpipe gas emission. Of course, this is tailpipe gas emission. We are not talking about emission from the electricity that's used to charge the vehicle. That's another different topic to discuss. And it takes a few hours to charge this full battery vehicle compared to a plug-in hybrid vehicle, but the driving range is also longer in terms of the distance that it can cover. So that's basically the terminology that we have. I want to talk about what do you call that, the charging methods that we have. So in Singapore, majority of the charging methods that we have are based on are deployed in public car parks, right? So public car parks, which are typically slow chargers, right? So these are used by public. And I think many of you might have known that, Singapore, we have very less landed properties. Most of us, 89-90% of us stay in high-rise buildings, residential, private as well as public residentials. And then there are a few very less landed kind of a property that you stay in India. So because of that, we share car parks. We don't have our own car park lots, right? So we cannot buy a EV and then install my own charger. We have to share chargers. So that's an advantage as well as a disadvantage. Most of these chargers that we have in the in the car park, public car parks are slow chargers, typically 7.4 kilowatt type of charger, and they are more suited for overnight charging, right? And these slow kind of a charges takes about 2 hours to give you about 100 kilometer of driving range. But the good thing here is that in Singapore, the island is very small. One whole round across the island will take you about 50 to 60 kilometers only. So that means if I can charge for 2 hours, I can actually literally last for 2 or 3 days when I'm just traveling to work and back home. So we're not talking traveling from one end of the island to another end of the island, right? So good enough for Singapore in terms of the amount of time needed for charging the vehicle. I don't need to charge the vehicle to full. Again, I just need to charge it enough for me to travel to work. And most of us live very close to place where we are working. So maybe I just need 20% of SOC to get to work and come back and so on. So the time required for charging is not so long. And the charging cost here is about 65 cents. 60 to 65 cents per kilowatt hour. And then we have also the fast charging one, but then they are located not within the public car parks, a little bit further. It's located where businesses are and so on. So these are typically the 22 kilowatt kind of a charger. So we have the 60 kilowatt, we have the 100 kilowatt, 120 kilowatt, and also the 180 kilowatt. So these are the typical chargers that we have. The 120 kilowatt kind can actually give us about 100 kilometer of travel range within 10 minutes. So that's about 25-30% of typical SOC. So that's the difference between a slow charger. So 100 kilometer can be charged, requires about two hours for a slow charger, but about 10 minutes for a fast charger. So we're talking about 120 kilowatt kind of a fast charger. And fast charger, we don't have too many of them. There are because they are, high power and so on. So depending on the operator as well as the location of the charger, it costs somewhere from 65 cents to 73 cents. It's not very expensive because the amount of power is the same right now, and the amount of energy that you draw is also the same. Just the installation is a little bit different. And of course, we also have the ultra fast charging, right? These are very fast chargers. One example is the ABB Terra, right? 360 kilowatt charger, and that can give you 100 kilometer in about 3 minutes. So that's the speed at which the ultra fast charger can charge your batteries. 3 minutes is like, going to a petrol station and pumping petrol and going off, right? So it's a very fast, convenient way. So we don't do this frequently, right? It is when you urgently require, extra juice to just, travel from one point to another point and then going back home to do the slow charging. Because fast charging is also detrimental to the batteries, right? So you want to then, use this only when emergency or when required. And we also have a sandbox that was just started in late 2024. But these are mainly for electric heavy goods vehicle, right? The trucks and so on, mainly operated in the shipping port and the commercial fleets. So these are the 360 kilowatt kind of ultra fast charging. So these are the one that's available, not for public use yet. It's more for fleet of heavy vehicles. The fastest now that we have in Singapore for public use is the 250 kilowatt Huawei charger. So this is also ultra fast, can be categorized as ultra fast, and it was installed, somewhere around a couple of months ago only, and it can give you 100 kilowatt in about 2.5 minutes. So it's very quick in terms of the amount of power it can give you. But then, we cannot be just focused on the capability of the charger, because now the capability of the car is also important. The EV, for example, the Hyundai Ioniq 5, which is very much used in Singapore, can only take about 350 kilowatts. So if you have a charger that's greater than 350 kilowatt, no car can take now. There is a BYD Atto 3. That one can only take 100 kilowatt. So even if you have a 120 kilowatt charger, you can only take 100 kilowatt. So charging capacity or capability is not only dependent on the charger, but also dependent on the what do you call that, the vehicle itself. So the vehicle's battery must be able to take that high C rate charging that you are probably giving from your charger. Otherwise, you will be limited by the capability of the batteries on the charger or on the what do you call that, the battery itself. Of course, we also have the battery replacement or battery swapping kind of technology where, you have a robotic arm to just replace the battery and then, load it with a fully charged one and so on. So these typically are used in highways and so on. I mean, in Singapore, we have one that we just launched on 1st of August. So this is the very first one. This is again not meant for public. It is meant for heavy duty vehicles. So it's like a 5 minutes kind of a swap. So they come in and then they swap the battery and then the vehicle can go immediately. So it's faster than actually filling the tank of a truck. And so the battery swap basically costs about $134 or so in Singapore for 80% SOC. Right, so 80% SOC is equivalent to about $134. That means, let's say about 10% of SOC is about $16. So what it does mean is that, it's a swapping. So if you come with 20%, I replace you with a 100% charged battery, I'm going to charge you for 80%. If you come for 50%, and then I replace you with a 50%, 100% battery, then I'm going to charge you for 50% of your SOC. So that's how the mathematics works. So the economics is based on how much capacity you bring in at arrival, how much SOC at arrival against, my full charge. We minus it off and I charge you that amount. And 10% is about $16, what do you call that, for 10% of your SOC. So that's how battery replacement works. So in Singapore, we have somehow trials ultra fast charging, and we have one working for the battery replacement now. Okay, that is the method of charging, right? So I also want to tell you the two types of charging. So ultimately, the two types. One is a slow charger, another one is a fast charger. So for slow charger, we talked about the power. So this is the power rating in terms of slow charger, 7.4, 11, and 22. These are numbers that's very typical now. And then fast charging is, we also 50 kilowatt up to 120, 360, 250 now, and so on. So the timing are given, and then these are all numbers according to some standard EV battery size, right? And typically slow charging are used where your sojourn time, that means the period of time you are parked in the location is longer. So that means, for example, in residential places. So when you are coming back home, so you are going to park your car and then probably leave the next day. Or when you go to work, you park your car in the morning and then you leave in the evening, after work. So you are having like 8 hours or so stay in that location. So when you have a longer stay, then slow charging or AC charging makes more sense. And then fast charging is of course typically used for urgent charging, right? Urgent charging where your dwell time or your sojourn time is very short. And and this is very much useful for heavy vehicles or fleet of vehicles. For example, taxis, they cannot park for a very long time because they make money by picking up passenger and moving around, right? So these are where you want to do urgent charging. You don't mind paying a little bit more so that you can start working, right? So for example, heavy vehicles where you want to deliver goods from one point to another point, you don't want to be parked at a location for a very long time. So but of course there are disadvantages of fast charging. The main disadvantage is the burden on the electrical infrastructure. Of course, having the electrical infrastructure to be able to support high power charging, but then how do you manage this charging so that it doesn't affect the grid or impact the grid is another thing, which is why we are talking about the what do you call that, the uh, smart charging algorithms that we will talk about in a short while. AC are okay, they don't impact so much, but then even for a 7.4 kilowatt what do you call that, a slow charger, it is for Singapore's context, right? We live in 3-room, 4-room houses, right? Is equivalent to at least two 3-room houses, right? So the amount of power required, so one car charging slow itself is an additional of 2 houses that being equivalent to 2 houses. So the power consumption of EV charging is actually not small in that sense. So let's talk about the charging system, right? So when we talk about charging system, we are talking about a few things. Of course, the EV is not included in the charging system. So the charging system involves two major things. One is the EVSE, we call it the electric vehicle supply equipment, which is the charger by itself. And then we have the fixed installation. But these fixed installation are not just, it could be just a very simple isolator or a circuit breaker that help you to safely disconnect and so on. So when it is a slow charger, the installation may just require an isolator. But then when it's fast charging, when the power is higher and so on, and there are more protection requirements. So then this is actually part of your electric vehicle charging system. So the fixed installation must take care of the charging capacity of your charger, and then provide all the accessories required for the charger. So the charger itself, as well as the accessories, for example, the emergency switch, the circuit breaker, the relay, and so on, forms the EVSE part of things. And then this is the building side, the installation side. So they have their own protection, they have their isolator before they move to the switchboard. So typically you have a connection point in the switchboard for this particular set of charger, or maybe just one of the charger. So when you talk about EVSE, we are talking about the entire charger plus the installation. And then we have the the different types of charger in Singapore. So we have everywhere else. In Singapore, we follow this technical reference 25. These basically define the different standards for electric vehicle chargers. So we have method 2 chargers. So method 1 charger are chargers that are connected to the socket outlet, the normal, 3-pin socket outlet, 15 ampere or so. But then they do not have any supplementary pilot or auxiliary contacts. That means there's no communication. It's just pure power cables. This is not allowed in Singapore. So Singapore's requirement when you want to charge EVs, you must have a pilot wire to perform handshaking, check the power, check the connection, and so on. So without that, you won't be able to use your charger. Right, so mode 1 is not allowed in Singapore, which is why I never put it here. Mode 2 chargers are the one that I know the method of the connection is basically still a single socket outlet, very standard outlet, and then you are basically utilizing the AC charger with a cable and a plug. All right, and there is a control pilot wire or function and a system that helps take care of the personal protection, take care of the electric shock protection, and they are placed between the what do you call that, the plug and the EV itself, the charger and the EV itself. So there's some kind of protection taken care. And typically the values of the current cannot exceed 32 amperes, right, for a single phase, and or even 32 amperes for a 3-phase system. So that is mode 2 charging. And mode 2A and mode 2B basically it defines the connection of the cables, right? So I'll show a picture in a short while. And then mode 3 is more on a connection where it's a AC charger that permanently connected to a AC supply system. So mode 2 are basically you are plugging in a single socket outlet, right? But mode 3 are more fixed chargers that's fixed to a supply network. Again, must have the control pilot function. You must be able to restrict the charging cable if it's removed from the EVSE and so on. So all these safety requirements that must be included when you have different chargers. And here restricted here meaning when the charging cable, you can remove it from the charger. There is some chargers that the charging cable, the two sides of the charging cable, one that goes to the car, another one that goes to the charger, right, can be removed on both sides. This is called these are one type of charger. So these are restricted for use. That means these are cannot be used for public usage. It can only be used by private owners. For example, I have a fleet of vehicle, I run a taxi company, so I'm using this charger for my taxi only. Then this can be used. Otherwise, if it's used for public, it must be the plug wire connecting to the charger must be fixed one. Cannot be a one that can be removed. Then lastly is of course the mode 4 charger, which is a DC charger, and again every one of these must have pilot. So in Singapore, any charger manufacturer who wants to come in sell the charger must have communication or pilot communication, and this applies to EVs, So that's typically the way we define the chargers in Singapore. So in terms of the figures, so you will see here, the single socket outlet kind. Mode 2B, right? And then you also have the switch isolator kind of charger. And then the mode 3 is the one that I was saying that you might have the both side is pluggable, right? So these are not permitted for public, and those which have the plug connected fixed connection to the charger is allowed for public use. Right, so these are all AC charger, and then the mode 4 is of course the DC based charging. And we also have in Singapore we don't have the pantograph kind of a charger, and then last one is of course the battery swapping kind of charger for 4-wheelers and so on. So these are basically the different types of charging system that we might have in different part of the world, and I think similarly goes for India. Okay, the EVSE, just to define, basically the supply side of the AC and DC charger is the same. It's a single phase 230 volt or 3-phase 415 volt. And the only difference is when it's a AC charging, you have onboard charger. The AC chargers are typically smaller in size. but the DC chargers are bigger in size because the charger is off board. That means the power electronics devices, the converters are basically on the charger. Unlike for AC, it is not on the charger, so that's why the charger it's just a supply equipment. And how we define, if your charger is supplying AC current, then it's an AC charger. If it's supplying DC current, it's a DC charger. Okay, so and then the DC charger basically connects directly to the batteries, but the AC charger connects through an onboard charger. And this is where your limitation happens. So the power of your AC charging is limited by the onboard charger, right? And also the power of your DC charging is limited by the capability of your battery accepting the amount of current. So how much C can it take depends on the batteries, chemistry, and the design, and then your DC charging can then focus and decide accordingly. And how they design is because the pilot wire basically tells what is the maximum current you can take and so on. So that's basically how it works. So there are different type of EV charging connectors. In Singapore, we use the Type 2 charger. There are different types of connectors. So, but then there are more now that is being used, the CCS2. This is a combined type of connector. So I think we all know that there are many charging standards organization, right? So they take care of different parts of the standard. So one very important one is, of course, the communication part of things and the information exchange, how you communicate, how you exchange information, and also the networking part. So all these charger, allows some form of communication. So there are always pilot wire and so on to share the communication between the EV and the EVSE. So for CCS2, of course, it's a combined connector, so they can do AC and DC charging directly. I'll just give you an example of a Type 2 connector. That means the one that doesn't have the DC separately. Yeah. So how it works is basically when you have the, it can be used for single phase, it can be used for 3-phase charging, it can be used for DC. If you are using DC, L3 and L2 forms the positive and the negative. So if I want to use single phase, then it's L1 and neutral. If I want to use 3-phase, of course, L1, L2, L3 and neutral. If I want to use DC, low power DC, low power is maximum about 80 ampere, then it is L3 and L2, right? Plus and minus. If I'm using high current, right, 140 amps here and about 140 ampere, then I'm using both N and L3 for positive, L1 and L2 for negative. So that's how it operates in terms of the charging connector. So you can do single phase, 3-phase, AC high current, DC high, DC low as well, right? And then of course we talked a lot about the pilot wire. So this is the PP, which is a proximity pilot. So it's actually a insertion signaling. So when you have this PP, basically it serves as a charge cable detection. So if you are connected, and then it also helps you to limit the current. And basically it has of course one of the major purpose is to take care of the mechanical locking, right? And you want to have sparkleless disconnection. So when you take out, you don't sparks, right? And then, of course, the major purpose is that the EV must know that the EVSE must know that the EV is connected, right? And this is done, and it shouldn't leave. For example, the EV is connected to the charger. It shouldn't just drive away. It doesn't allow the car to be turned on and so on, right? Basically, what it does is actually it uses a circuit. It creates a circuit using a resistor. So there are different values of the resistor, and this resistor is connected to the protective earth. So it basically creates a circuit, and from here we can then decide or know what is the maximum current. So you can then limit the current. So if it's 100 ohm resistor, then it's a 63 ampere and so on. So this is how the EV SE knows how much current can be supplied and so on. Right? So it's based on a circuit that's created by the resistor of choice. And then, of course, we have the control pilot. So control pilot is what do you call that, is more for other purposes, like, you want to continuously find the continuity, checking if the protective earth conductor is connected or not. You want to verify that the EV is properly connected to the EVSE, how, energization of the power supply to the vehicle after, all the proximity pilot have completed is checks and so on. When you want to de-energize, this is also the one that tells the EVSE you want to de-energize, and then decides what's the maximum amount of current and so on. So these are the various functions of the control pilot as well as the proximity pilot. Very important concept when you're talking about what type of charger we are using or what type of connector we are using for the chargers. Okay, so the EV charging system, as I mentioned, so these are a very basic single line diagram of the 10 V2G charger that we just recently installed in SIT. So we have the 10 chargers connected to some isolator, and then there is a subboard, right? V2G subboard has some metering device, circuit breakers, and protection relay as well as control cables. And then they are then connected to one of the outgoing feeders in the main switchboard, right? So then, for this main switchboard, you have another isolator. So there is a requirement by the TR25 that this, this emergency isolation, a main isolator for the shut-off switch, right, must not be located more than 15 meters away from the charger. So that means if I have a charger, the isolator cannot be more than 15 meters. So you must be able to, very quickly run there and then switch it off in case there is some challenges and so on. Right. So that's basically the connection. And then, of course, if there is a need for billing purposes and so on, you want to connect to your building management system, there is a separate communication wires between them and so on. So this connection to the installation together with the charger is what we call a EVCS system. This charger itself, with some accessories that we have here, this is called the EVSE, electric vehicle supply system, or the charger. So just to give you that. And of course, there is a very important part, which is the communication and control. For example, for the EV to connect to the charger, we have IEC 15118 and so on. And then from the charger back to the BMS system, it can be Modbus, backnet system, and so on. So the different communication for different parts of the network and so on. I'll share a little bit more about comms later in the V2G part. Okay, these are the chargers that's installed in SIT. So we have a Gridwise Korean company that provides these slow chargers, 7 kilowatt AC bi-directional. So we had a lot of problem in getting a bi-directional charger for our project because there's no one who is able to supply with a C certification, right? So because, for example, in China, you have V2G chargers, but then it's meant for certified for Chinese. And then we have a Korean one where it's certified for Korea and so on, not for international use yet. So we had to work around and find a charger, then get them to then get the CE certification and so on. So this is a slow charger, bi-directional also. And then we have the 11 kilowatt bi-directional DC charger, which is from a company called Star Charge. It's a Chinese company. So they 11 kilowatt output power, also 11 kilowatt both directional AC and charging and discharging. There are some charger, V2G charger, that does 11 kilowatt for charging, and then one we saw is 5 kilowatt for discharging. So the power for input and output are different for charging and discharging. So there are different type of chargers. So that's basically what I wanted to cover for electric vehicle charging system. So we talk about the vehicles, the charging types, the methods, as well as what are the components within the connectors as well as the system. Before I move on, is there any question that there's anyone want to ask? Okay, if not, I will continue. So, so very important today's topic is about charging management system. So, having charging management system is important. Why? Because any VEE charger, when they are connected to the grid, right, you will need some form of management system. But it may not have direct impact on the grid if it's not controlling the charging. So, but the CMS today is meant to perform sorry, it's meant to perform, for example, help to optimize the efficiency of the charging points, all the charging points that's connected to one central hub. It provides, historical or real-time data for the charging point. For example, you have an app that can tell what is the SOC now being charged, and then once it's done, you will get a notification. All these are functions of a charging management system, and it also allows the company to easily add new charging stations, add new station groups remotely. They can actually, for individual users, you can let them access the information quickly, or for their own consumption, or add new users and so on. So that's basically the work of charging management system now lah. Of course, there is also the roaming of charging EVs lah. So similar to how we roam from country to country using our mobile phone. So, for example, if I come to India from Singapore, I need to connect to a local telco, for example, ATAL or something. So I need a roaming services. Right? Similarly, EV can also roam between countries, or within a country, there could be different charging point operator. So, for example, in Singapore, we have about 5 charging point operator operating the different districts in Singapore. So one charge point operator is called Singapore Power, takes care of the northeast region, and then the northwest region is taken care by another company called Strikes. So but then the EV owners can be charging. They could be working in the west, northeast, and then staying in the northwest and so on. So there is a need to do roaming within a country. A small country like us also we need roaming. For example, from a car that moves from Tamil Nadu to Kolkata, for example, and so on. They want to charge. They must be able to charge. And OCPI is the communication that allows the electric mobility service provider. So it's a roaming kind of service provider. The charge point operator, the two charge point operator can talk between the two through the EMS, e-mobility service provider, to perform roaming services. So the vehicle there's what do you call that? Registered with one charge point operator can go to another charge point operator and charge and be billed by the charge point operator one, and so on. So OCPI basically takes care of the communication between charge point operators through an EMS. OCPP 1.6 or 2.0.1, which is the latest one, takes care of the charger to the charge point operator, right? CPO, the communication between the charger and the charge point. 1.6 doesn't allow V2G. So 2.0.1 allows for V2G communication, right? So that's basically the different communication and that interesting roaming concept of vehicles. Of course, charging management system has always been there. There are, ever since EVs as not individual users, but then for public use came about, charging management system was there to allow for energy administration, the payment processing, how do you do fleet management, and so on. And for hardware monitoring, enable the troubleshooting of charger when it gets wrong, or give you a fast response to charger issues, and of course to do user management. But today's topic is important is because we want to now move into a smart charging management system which optimize the power distribution across chargers. Okay, so that is where the smart charging management will come on top of the charging management system that does all this today. Right, so why are we doing, or why are we looking at this? Because this is a study that was done in UK. So it's an average, weekly average demand profile in UK for a full year of 180,000 EVs. 180,000 EVs, which basically showed us that there are a peak during the 7 to 8 p.m. Period, and there is also another small peak during the 7 to 9 a.m. period in work-like places, right? So there is a peak here, a smaller peak, and then a bigger peak at 7 to 8 p.m. So which means, right, 75% of EVs are basically charged in residential premises using slow chargers, right? Using slow chargers, and 15% are charged at work-like premises. That means that when they go to work, school, and so on, they basically charge the EV. So which means, right, even though that, a typical EV owner will basically return home at probably 7 o'clock, park his car overnight, and drive to work the next morning, right? So basically, even though the EV can be fully charged by maybe midnight, the car park lot is unlikely to be vacated, right, for another car to come and charge, right? And this same scenario can be seen in also the residential one. So the key important factor here is that we see a peak of charging happening in the evening period in the residential premises. So what does this mean is that there is a sudden peak that were not there earlier, right? So we need to now look at how I can then manage the charging in residential buildings or work-like places to ensure that these peaks are flattened to as much as possible, right? So that's basically why we want to know how I can then utilize smart charging management system to do this. In Singapore, we have a very interesting, I think, many countries who have a traditional power system will have this challenge. So, as I mentioned earlier, we have the what do you call that, car park that are public car parks, right, within our nearby our homes, right? So these car parks are built when the homes were built, and they were built with no thought of EV penetrating so significantly, right? So they were built, 20 years ago. Nobody talked about EV. Nobody thought EV will be so significant. So what happened is that now there is no spare capacity. Every building, every car park now in around Singapore has at a maximum of a 40 ampere MCB, right? And a three-phase MCB as a spare capacity, which means, right, if I have a 7 kilowatt slow charger, which takes about 30 ampere per phase, at most I can connect for 3 charger for one car park, which can accommodate about 700 to 800 cars. One pristine houses is about 1,000 houses, right? And then about 700 to 800 car park lots are available, but I can only cater for 3 cars to be charged or 3 charger if I'm basing on my capacity. So what happens is that first of all, the current network were not designed for EVSEs in mind. So we never thought about it. And new upgrades, meaning I need to change all the way from the transformer. So I need to upgrade my transformer and so on. So that is a very costly infrastructure capital investment. And the increase in the number of EVs on the road did not match the power distribution upgrades. That's another problem. So now we are thinking about how do I do this now, allowing people to come. They must not have the range anxiety that, oh, I come home and then, there's only three charging lots and it is filled. When do I charge? And then, you have to come back and then check whether the charging lots are available. Maybe arguments will come because I parked here first and so on. After charge, you never remove your car. A lot of problems. So charging management system help us to manage this. For example, a very simple example here. I can have an algorithm that does EV load management, right? And then instead, I still have the same 40 ampere spare capacity, but now I'm connected to 9 chargers instead of 3. But I allow the charging to happen such that they don't exceed the capacity of the charger. The capacity of the installation, right? So I can manage the current, for example, to make sure that it is in total. For example, we can in fact go a little bit further. A type B MCB, right? For example, will only trip the overloading will need trip 3 times of iron. It means at 40 ampere. At 40 ampere, you will only trip at almost 120 ampere, right? So you actually can play around with higher. No, you don't have to fix at 30 ampere. So, for example, I can run up to 60 ampere per phase, and still don't trip this, and I just manage the timing accordingly. So this is also possible. And of course, otherwise, I can allow everyone to come and connect their charger, the car, but they are not charged. They only charged according to my algorithm, right? I can then expand, then make sure that, when they leave in the morning, they have their car charged to a certain level they require. So this charging can play in two ways. One is I control what time I charge each of these cars, or I can control the power that's used, so the amount of current that's pumped into these chargers, to these cars, right? In terms of the power management. So there are a variety of ways that we can do this. This is the interesting part of it. So when you talk about a charging management system, we are talking about two things. One is slow charging and fast charging. We spoke earlier. When you talk about slow charging, the definition is typically charging rate divided by 4. So a quarter of the charging rate, then it is called a slow charger. Anything greater than a quarter of the C rate, then it's a fast charging. And in both of these, there are two types of charging. One is called the coordinated or smart charging and uncoordinated charging. So uncoordinated charging is, of course, the very, of course, when you talk smart, then it's dumb is just dump. You connect, once you connect, you start charging, right? So it doesn't have any algorithm to think whether I should charge or not charge and so on. Of course, the other one is the delayed charging. Delayed charging has some kind of very minimum intelligence to just delay the charging, not to occur at a peak period, right? So and that happens is with in a very simple time-based method. That means if it's 7 to 8 p.m., don't charge it. That's it, right? And then once it's 8 p.m., it creates another peak because every car will turn on and start charging now. So that's delayed charging. They are considered uncoordinated charging. And then, of course, we have the smart charging or the coordinated charging. They are the best strategies for managing the impact of EV charging on the grid. And there are two types of this coordinated charging. We call it time coordinated charging, TCC, or the power coordinated charging, PCC. Right? So they are basically used to then smooth the valley, or or shave off the peak. So that you don't create a new peak. So basically it involves some kind of algorithm. So one example here is that, in time coordinated charging, the number of charges are corresponding to the power available. So if I have 9 kilowatt, I got 3 charger, everyone will get 3 kilowatt, right? So average power consumed by all chargers are same at 3 kilowatt. So if I want to increase another one, I need to increase the total available power. But in PCC, it can be different. So I can, even if I have 9 kilowatt, I can charge 6 cars, but each of them has lower power, 1.5. 1.5 times 6, I'll get 9. Or if I have a little bit higher, 12, I can charge them a little bit higher, 2 kilowatt, but I still can charge all the 6, right? So there is some advantages and disadvantages between the two, and we will look at it in a short while. So all of these basically are following a different methodology of filling up the time slots with either the power or the different EVs, a fixed EV with fixed power, or different EV with different power, right? So for example, in this slot, if you see EV1, EV1 and 2, and EV1 and 2 and 3 are basically charging at the same time. But then the power is different. EV1 is this amount of power, EV2 is this amount, and then EV3 is this amount. So the EV3 is basically getting lesser power compared to EV1 or EV2. So the power is basically coordinated. In TCC, basically it is EV1 and EV2 only charging here. Then here EV1 is stop charging, EV3 is charging, and so on. So this is basically time coordinated, but both the cars that is charging at the time get the same amount of power. So they are just allocated by time. So that is the two types of coordinated charging in TCC and PCC. So just look at a few algorithms kind of that is available. One is called the coordinated valley filling and peak shaving. If you see, basically the objective function is to minimize the total demand. So the total demand here is basically the demand of the non-EV demand at time k, as well as the charging or discharging power. So this takes care of V to G as well. So the whole objective is basically to reduce the total demand, right? So this is This is the objective of this coordinated valley filling. So you want to see whether you can then optimize the EV charging or discharging by using valley filling or peak shaving. So I can coordinated valley filling. That means this is just basically coordinating EV charging to fill up the valleys during in a power curve, or you can work with both charging and discharging by peak shaving by discharging the vehicles and then filling up with charging later on when there is a valley. So they are basically coordinating in a different way. If you have V2G, then you can do the second one. Of course, it allows the results basically tell that you can reduce the load variance by 47% if you're using just the CVF, and up to 65% load variance if you're using the CVF-PS with the peak shaving, because you're able to discharge the vehicle to support peak shaving as well. So that basically helps to reduce load variance. So load variance meaning the fluctuation in load, right? So if you can flatten that load or smoothen that curve, right, then it becomes lesser of a load variance. So that's what we want to achieve. Eventually, any company, if you talk about, or any power system operator, if the load curve is a straight line, a constant line is the best. It's best to manage, but ideally it won't happen. And then we have the opportunity-based cost minimization. So for this example, the EV charging and discharging are basically with an objective function to minimize the total cost. That's not what's total demand, right? Now is to minimize the total cost. It's based on the price of the charging, which relates to the energy is being charged or discharged, right? So they just if it's a charging, the price is it's like net metering minus if it's discharging plus if it's charging, and then it also considers the cost of battery degradation. So in this case, the discharging as well as charging has some kind of revenue or reward. But the whole objective function is basically to minimize the cost. So we saw load demand minimization. This is another option, which is the focused on cost minimization. So they use a few type of algorithm, forward, backward, energy location using charge opportunities or discharge opportunities. And the idea basically it is able to now reduce total cost, charging and degradation. So they have a cost for the degradation function, which I never include here, right? And so it can reduce the total cost by 30 to 50% against uncontrolled charging. This is including degradation of the batteries. And then, of course, with that, it enhances the grid stability and also the convenience of EV owner. So that is opportunity-based for cost minimization. There's another one which is for, PCC kind of charge coordinated charging. So the objective function is basically to minimize the battery degradation cost, nothing else. It's not about cost. It's not about load demand, but it's about battery degradation. So the battery degradation cost in this work is basically a function of the capacity fading rate, right? So the capacity fading rate of any battery, but this as a function of the power. So if you have the function of the power, you'll be able to find the capacity fading rate. And cost wise, basically they use the battery replacement cost as a cost to find the cost of the degradation. So they focus on a 3-layer framework. There is a dynamic power adjustment. It is PCC based. So you reduce the charging power to lower the battery temperature and degradation. So because they are very much focused on not degrading the battery. And another one is vacant resource allocation. So they optimize charging slots to minimize the cost. So they use both of these, and you can achieve almost 15% lower peak load or 30 to 50% cost reduction versus uncontrolled charging. So there are a variety of ways of doing this, right? So that's why there are cost minimization, there's load minimization, or even to just take care of the battery. So there are variety of ways of doing smart charging management. There are different algorithms to do this. One work that I did was on looking at different priority criteria when you do charge scheduling. So when I have a for example, a PCC kind of algorithm. Right? I did this for both PCC and TCC. So, there could be priority criteria for different EVs that comes in, because you want to ensure that all EV has the ability to be charged. Right? I don't defy anybody of charging opportunity. That means if I come to a car park, I must be given the opportunity to charge. Right? And the second one is the fairness in charging. Right? If I come in with, for example, I'm going to be allocated time based on my SOC, for example. Right? So I come in, my SOC is only, I need about 30% SOC. There's another car that requires 70% charging. So what will the normal algorithm does is to allocate more time to the 70% car, right? And allocate less time for me. That is somehow not fair, right? So how do I then manage this charging fairness and chargeability, right? So there are three priority criteria that we identify. One is, of course, the SOC. So it's the amount of charge you require, which is a function of your arrival SOC and your required departure SOC. It could be 100%, or could be any other number. So what is the SOC you require for the charging management system to charge your car? So that's one criteria. So which means the higher your SOC requirement, your priority is higher because you need more time to be charged, right? And then there is a slack time, right? Slack time is like June time. So June time meaning the amount of time the vehicle is connected to the charger for charging, right? So, and you will be staying there for that period of time. So it's typically, when example, in a residential building, when the owner comes in and park at 7 o'clock, and then they leave at 10 o'clock, 7 a.m. in the next morning. So you have 12 hours of sojourn time or ideal time connected to the charger. So that's one more criteria. So if your select time is lesser, meaning you have shorter period to be with the charger, so the algorithm basically will decide to give you more opportunity to be charged to your desired SOC. And then allotted time. That means even if I've allocated you time, but then in order to ensure fairness, I will, if you are allocated more time or more power, right, then I will allocate somebody else the opportunity. So to be fair, because if I charged you for 20% SOC and I've now charged this X percent for even 1% SOC, then I'll give that car another opportunity in order to ensure fairness. So that's how it works. Basically, the algorithm decides for PCC, decides the power of every EV for 48 time slot, and then it basically renews the CPS charging schedule every half an hour, right? Every half an hour. Sorry, this is every 15 minutes. And then we have the same one for TCC. So, but then for TCC, it's a 1 and 0. So it's whether I charge the vehicle or I don't charge the vehicle at that time slot, and it does that for 48 time period. Sorry, 48 is still a half an hour. Yeah. 24, 48, yeah, 1 whole day, half an hour period. And so basically, the result shows that the priority criteria has an impact on the chargeability as well as the fairness of the EVs. For example, we used a probability of the EV not being charged as a measure of the performance. So that means if the EV is not charged to its desired SOC, then how many numbers of time it happened, and over how many number of charging events per day. So that's basically our performance criteria. And we can see that at TCC, between TCC and PCC, it's very obvious the PCC actually does better in terms of lower probability of EV not being charged, because every EV are located some kind of time to be, some kind of power to be charged, even if it's low. But in terms of TCC, you will see that the TCC actually perform worse than the PCC. But some interesting finding was that you can see that the slack time, right? If the slack time, having slack time is actually giving you the lowest probability of EV not being charging, which means that is one of the best criteria to use. But when I use slack time against together with something else, for example, slack time and allotted time, actually the probability increases. And slack time with or the other two, the probability still increases. And SOC by itself is 11. SOC with slack time actually reduces. right, and so on and so forth. So this is basically telling us that slack time is actually a very good way of managing the priority of the EV. But just that is not enough, right? So because it doesn't tell you what is the fairness of the charging. So we looked at the percentage of failure for each of the EV. We reference to the total number of charging event, and in this case, just to note that EV1, EV2, EV3, we used EV with a smaller battery capacity and smaller energy requirement. And EV13, 14, 15, you will see that they have a larger battery capacity and larger SOC requirement. So if you look at this, then for PCC scheduling, in fact, we can see that the priority criteria, slack time, actually punished in some manner, has higher percentage of failure. SOC and SOC plus allotted time actually gives you better output in terms of scheduling smaller capacity requirement vehicles. And on the other hand, if it's a larger capacity vehicle, slack time and SOC doesn't do good, right? Only the slack time alone actually helps. The SOC by itself gives you, the SOC and allotted time itself gives you or punishes the vehicle not to be able to charge, giving it higher failure percentage. And for TCC, the other way around, you'll see that, for TCC, the percentage failure for smaller vehicles are much lower because they are, as long as they're given some time, they are able to charge because they require smaller amount of energy. And on the contrary, of course, the EVs that have larger SOC requirement are punished in the sense. So this basically tells us the different performance and of the priority criteria, and very much is about using slack time and allotted time to give you fairness in terms of charging management system. So that's basically the outcome of the study. Okay, so very quickly, I have 15 minutes. I'll just quickly go through another work on charging management system also, but on vehicle to grid. So we are doing a project with a company called Strides. So Strides Mobility have a fleet of taxis and commercial vehicles which are EV based. And then they are using also an opportunity to then participate in the market when the vehicles are not used for delivery of goods or for taxiing. They want to discharge the vehicle to participate in the market, right? So electricity market for demand response, for if it's large enough for frequency regulation, right? So what happens is that we are developing an end-to-end EV all the way to the market communication structure and the test bed to perform this. And part of this requires us to develop a V2G model module to then do estimation of V2G capacity before you are able to participate in the market. So that's the basic concept. So again, the CMS, the CPO, in our case, the aggregator and the CPO are the same people. It's a company called Strides, who are also the CPO, the charging point operator. But we are trying to develop a solution that allows them to also work with other charging point operator to discharge vehicle who are participating with Strides, but then in another district connected to another charging point operator. So you're still able to participate in that sense. So the architecture basically works in a way that, we have the EV. So EV basically has, communication protocol 15118. And then we have the EVSE, which is our charger. Charger communicates with the charging point operator, which is so-called our CMS, charging management system. We have to look at these two green boxes as one entity in this case. And they communicate using OCPP 2.0.1 because these are V2G capable. And then the aggregator basically talks to the market using Open ADI, Open Automated Demand Response. And then OSCP, is an Open Smart Charge Point, communication with the grid operator. And then the grid operator basically takes care of the EVSEs through 61850. So this is the basic communication concept between the charger, the EV all the way until the market. And we are establishing this now. We have completed this part where we have able to then aggregate or dispatch the EV from using the charger between these three communication layers. So aggregator can discharge and send a signal to charge and discharge the EVs accordingly. And now we are working with the market to do the open ADI part. Okay, so but one important thing that we are trying to do is there are two applications of the V2G. One is to do peak load management, very simple. There's no participation in the market. I'm just looking at the load demand in my building, and then I want to discharge the EV so that I reduce the load demand. Right? It could be due to cost of electricity pricing during the peak. Right? And but there are many things that the optimization module require. The very first one is actually the V2G capacity estimation. I need to know how much cars are connected, how much SOC they have, because I need to I'm going to discharge them, but then I must also know when they want to depart and how much they need when they depart. So that I must, even if I discharge them, I must be able to charge them back at a different time before they leave to their desired SOC. So V2G capacity estimation basically does that. And of course, if there is a priority value, we also take that into account, and all other information is required for this optimization model. So it's a very complex kind of optimization to look at different parameters to then decide which EV to discharge and how much to discharge, and make sure that you can charge the EV back to the required SOC before departure. And another one is for demand response, where you participate in the market. So this one requires us to look at the pricing of electricity at different half-an-hour time slots. So this is the Uniform Singapore Electricity Price coming from the Energy Market Authority, the Electricity Market Company. And I know, of course, you want to participate in demand response at points of high electricity price. So you don't want to participate here. You want to charge it at low cost and then discharge it at high price. So there's energy arbitrage in that sense. So again, you will see that at this, we also need V2G capacity estimation, and that's one algorithm that was our optimization module that we need to develop in order to make this project a success. So a variety of things that we did. Of course, you need to know before you are able to do estimation is what is the maximum and continuous V2G power capable by the power electronic converters in the EVs as well as the chargers. So this basically forms the constraints for the power constraints. And then, of course, the energy availability. So what is the current SOC? What is the minimum SOC required, and how many cars I have? Then that will basically tell me what amount of energy I have. And then using that, I can then determine, whether which EVs will be able to give me the total available power. And eventually, total available energy. And of course, we are working on a half-an-hour market in Singapore, so we will use a half-an-hour time period to determine the power available. So when you participate in the market, you're not just focusing on the energy, but you're talking about the power you can supply for X period of time. So we need the power as a parameter to inform the market. So eventually, based on the amount of power, we are able to then determine what's the amount of energy that you can produce. Now, I'm not going to go into the details, but then we have this algorithm to basically do the energy availability calculation plus because you cannot do this separately. I need to be able to schedule the charging of EVs, and then from there, I determine what is the energy available, because the charging will tell me how long the EV will be there in that location, so that when I want to discharge them during peak periods for peak load management or for market participation, they are there to be discharged. Okay, so this is an example. So for residential location where the EV comes at a certain SOC and they have a desired SOC and they have arrival and departure time. So at the residential buildings, typically we are working at the evening period. So there are two periods where there's small peaks. One is the night period when the EV comes in, and then there's an early morning peak period as well during the 6:30 to 7:30 when people are getting ready to go work and go school. So what happens is that the charging, the capacity estimation algorithm basically determines what the capacity available. So the dotted line here basically tells us the number of EVs. As the number of EV increases as the evening period comes in, right, the EV starts to arrive, the capacity, which is the solid line here, increases because there are EV coming in with available SOC. They're not charged, yeah. They are connected, but they're not charged. So they're based on the telematics that we receive from the charger, we know how much capacity available, and then the capacity basically increases. And then at at 8 o'clock, what we do, we want to shave off part of the peak period at 8 o'clock. So we start to discharge the EV. So we start to discharge the EV for V2G, and then the capacity basically reduces. As we discharge more EVs, the capacity reduces to a certain point where we cannot discharge anymore. The reason being is that we don't discharge the EV more than 40%, right? That's our decision in this project. So if it's more than 40%, less than 40%, we will stop the discharging. And then, we wait until 11 o'clock where the off-peak period kicks in. The price of electricity is cheaper. The off-peak period doesn't have so much of it's more valley feeling now. Then we will start to charge the vehicles. So as we charge the vehicle, the capacity increases again. So the capacity increases to a point where we have about, 50 kilowatt ready for discharge. And then in the morning peak between 6:30 to 7:30, what we do, we start to discharge again. So we discharge for a period of 1 hour, and then the EV starts to leave. So this one is not because discharge, but because the EV starts to leave at 7 plus or so. They start to leave, so the number of vehicles drops, so the capacity drops. So that's an example for residential buildings. And this is how the peak, the load curve looks like. So this is where we discharge the EV, so the load curve reduces. And then this is the peak valley filling where we start to charge the EV back to the SOC required. And this is a very small valley peak load, peak shaving during the morning peak period. And similarly, we do that for office, but office is a little different because they operate in a different timeline. So what we have done is, the vehicles comes at a certain SOC, but there's no desired SOC. We just make sure that we are keeping the desired SOC as it is. So of course, we are not able to achieve exactly in terms of that percentage, the decimal points, but then close to the arrival SOC. And they come in the morning, they leave in the late evening, and similar concept. And morning when they come in, they are sometimes they are fully charged, so the capacity increases. And then when we do the discharging is during the afternoon period. So there's a national level peak in the afternoon 12 to 2 period and so on. So that's where we start to discharge the EV. So as we discharge the EV, there is a drop in the capacity available to a certain point, and then we start to charge it back again so that we can achieve the required SOC. And so this is how the office building peak shaving happens. But then because in office building, we also have solar PV. So the solar PV also complements the V2G discharge, and we can reduce a significant amount of building load during the 12 to 2 period. Okay, so there we did a comparison of the accuracy between the different methods. There's a fixed SOC, limited estimation method, and so a plug-in probability-based method in the literature. So our method we proposed, obviously we are doing better than the other two methods. There's a different case study that we looked at in terms of when do we charge and when do we discharge the EVs. There are other algorithms in the literature where we focus on federated connected V2G for EVs. So this one is not using, so it's basically you don't want to use a lot of data from the EV. So whatever you receive from the telematic may not be available to you. So for example, what is the battery status, what is the location, and so on. So it's not using some raw data from the EV to protect the EV user information, because we talk about PDPA and personal data protection, and so on. So this algorithm basically uses a very small amount of information, but then uses game theory to incentivize V2G participation. Right. So then EV owner voluntarily participate for incentive and then to stabilize the grid and earn rewards. So that's game theory based V2G participation. This is useful for private owner vehicle, but then for our project we are using a fleet of vehicles because the owners are fixed and these are companies. We are using their fleet, so it's a bit more easier than individual vehicles. Otherwise they won't discharge. Why would I discharge? Yep, sorry. So yeah, this is another one. There's a two-stage optimization framework. These are typically for both the private vehicle and taxis. They use them to complement each other. So it's a unified scheduling between private vehicle as well as the electric taxis, which are fleets. And then they are able to ensure they are able to meet the compliance of power limits by also discharging according to the required peak demands and so on. So there are different types of algorithms available and for V2G. So one that we are developing is more focused on fleet of vehicles and for participation in demand response program as well as for peak load management in buildings. Okay, so I come to my last slide. So this is the conclusion of today. So we talk about the type of charging, the technical requirements, and so on. We focused on the charging management system a little bit more. What are the challenges? Why do we need the charging management system or smart charging management system? And some of the solutions, including how do you use priority criteria to decide when to charge, when not to charge, based on chargeability and also fairness to the EV owners. And lastly, we looked at charging management system for V2G, very focused on capacity estimation, and it's a very important part of it, how we build scheduling approach into capacity estimation so that when you do V2G, we know how much capacity available to discharge for any purpose, frequency regulation, demand response, peak load, and so on. And this is another example of a distributed energy storage. So the car are basically batteries located at various location, and you can aggregate them to do discharging. All right, so yeah, this is my email address. If you have any questions, you can always email me, and then I will be able to happily answer your questions. So maybe we can open the floor to questions. Anyone have any question you want to ask?
Okay.
Anyone, any question?
Thank you, sir,
No problem.
for sharing your invaluable insights and expertise with us today.
Sure.
Your presentation is truly helpful, and we appreciate the time and effort you took to prepare and deliver such an engaging session.
You're welcome.
We are grateful for your participation in our ATAL FDP as a resource person. Thank you once again, sir, for your valuable time and expertise. Thank you, sir.
Thank you very much. Thank you for having me. So we can close the session?
Yes, sir.
Okay, thank you so much,
Okay,
everyone. Good
thank you.
night.
Good night, sir.
Good.
So let's welcome Dr. Suman Dev for his second session. We are excited to learn from your experience and knowledge, sir. Sir, please start your session.
So good evening, everyone. So I am sharing my screen, and please confirm me once my screen is visible, as well as I am clearly audible or not.
Yes, sir, it is visible and audible also.
Okay, I think fine. So now the topic is renewable energy integration in microgrid. So today, this session, I will be covering under these headings. Similar like yesterday, I will be just give some introduction related to this topic. Then what are the different renewable energy sources which are used for microgrid application today or in future it will be used. Then what are the renewable project challenges? Then I will talk about what is microgrid, what are the components of a microgrid, how the configuration of a microgrid will be defined, what are the various advantages and disadvantages of microgrid, its integration and control aspects. Then few case study I will be presenting where we have actively involved that type of microgrid projects. Then what are the softwares and tools are used for renewable power integrated microgrid system, and I will be trying to give one demonstrated related to one software called Homer, which are generally used for microgrid hybrid projects. Then lastly, if time permits, then we can discuss little into details. So this is India energy potential of renewable energy. So solar is exactly closer to half of the total potential, and the renewable potential zones in the country are basically located in Rajasthan, Gujarat, Karnataka, Tamil Nadu, Uttar Pradesh, Punjab, Maharashtra, Uttarakhand, Himachal Pradesh, and northeastern states. Northeastern states, basically it is related to hydro, and if you see this one, then you can see these are the states where related renewable energy is potentially available. So here we can see in India install capacity wise 50% is fossil fuel and remaining is non-fossil fuel. So here as per Ministry of New and Renewable Energy, large hydro means if it is more than 25 megawatt, that is not considered as a renewable energy, whereas below 25 megawatt capacity called as a hydro for renewable applications. So what are the renewable energy sources? Yesterday we have talked, that is solar, and solar also basically it is photovoltaic as well as CSP. Then wind power, biomass power and cogeneration. Waste to energy means if it is some waste material like agricultural waste or municipal solid waste, those type of materials also considered as a renewable energy, and it is called waste to energy. So about 40% of the installed capacity is coming from non-fossil fuel, as well as I will say that it is from renewable things. So 10% is coming for large hydro plant. So this is different sector wise install capacity. So we can see that more than 50% capacity is in the private sector. And if we see this put install capacity wise, then as per IRENA report, India stands fourth globally in total renewable energy capacity, and also fourth in wind power and fifth in solar power capacity. So this is a very good uh, optimistic scenario for India wise renewable capacity. So India announced its ambitious goals to address climate change. So what are the goals? By 2030, renewable energy capacity installed will be 500 gigawatt. And that means we can say that 45 gigawatt year on year growth. So each year it will be installed about 545 gigawatt. Then 50% of the energy will be coming from renewable energy sources by 2030. And solar wise, we can see that 15% is the cumulative annual growth rate. In case of wind power, it is 10% growth rate. Also, by 2030, India has a target to generate green hydrogen that is equivalent to 5 metric ton per annum. And also to reduce carbon emission is 1 billion ton. And also India have target for net zero emission by 2070. So how to achieve it? This type of goals. So we require long-term motivation, business strategy, and short-term progress in innovative solutions, collaboration, policy and regulations, gigafactories, and research and development, which will be achieved by partnership with academia like you people, industry like we, and various government stakeholders. So this is the way, if we collaboratively work together, then India ambitious goal will be met. So this is a typical Indian ecosystem, how it works. So in India ecosystem wise, there are two separate entity like central government and state government. So policy will be dictated by both. Then planning will be Central Electricity Authority, CEA. Regulation, if it is state-wise, then Central Electricity Regulatory Commission, and state-wise, it is a State Electricity Regulatory Commission. Implementation by NLDC, RLDC, SLDC, and DISCOM. And this is for execution side. These are the stakeholders who are responsible for generation, transmission, distribution, market, and definitely consumption is by consumer like us. So in India, integrated national power system operation is done through 6 control centers. One is National Load Dispatch Center, that is called NLDC, which is in Delhi. Then 5 RLDC, means regional load dispatch centers, are there. One is north, then western, southern, eastern, and northeastern, which is in Shillong. So these are the total 6 entity which are responsible for grid management in India. So now I will talk about what is energy transition. So energy transition is a radial shift in the energy system from an existing model to a new model. So today our industry and transport system heavily dependent on fossil fuel that we know, which emits greenhouse gases, and it is damaging environmental, and it is creating environmental pollution. So in this context, energy transition is a pathway towards transformation of the global energy sector from fossil fuel based to zero, that is low carbon future. So India has, as I said, that net zero target by 2070. So what are the drivers for energy transition? So there are 5 main drivers like climate change mitigation, long-term energy security, price stability, national resilience, and economic opportunities. So again, collaborative efforts requires from government, businesses, and individuals to accelerate this transition to the low carbon future. And these are the few strategies that will help for India energy transitions to reduce greenhouse gases and to make achieve India as a net carbon neutral target. So these are the different strategies which is be responsible for a radial shift to new model, that is called energy transition. So now I will talk that triple pillar powering the energy transition. So to do this energy transition, so there are three pillars. One pillar is renewable energy, different renewable energy it will help. Then energy storage system, because renewable energy, it is not constant and it is not consistency. That's why we need storage. And microgrid, which is our present concern. So now just I will tell what are the different renewable energy sources are available and used for microgrid applications. So yesterday we talked about solar photovoltaic. So just I will play one small video. Most probably sound you may not able to hear, but I will explain how it works and how basically it looks like. So I'm playing this video.
The sound is not coming.
So I think sound was not audible, na? This one. Hello.
No,
Yes, sir.
sir.
There was
Sound
no
is not.
sound.
Okay. Okay. So I think maybe I will explain in a minute that one. So yesterday we are talking about solar PV single axis tracker system. So this is a small solar plant with based on single axis tracking system, which is rotating from east to west side throughout the day, and it is generating electricity. And this is a very small scale plant. Its capacity is only 1 megawatt peak plant. So this is yesterday also again we discussed about concentrated solar power, which is like that. So the basic difference between these two CSP systems are only in this case there is no storage system, but here there is a storage system which will store solar heat during daytime, and whenever it is required during night time, again it will be used to drive the turbine, and generator will be generating electricity. So I think if time permits, then I will show later how the CSP plant will be looks like. This video will talks. So now there are different biomass technology are available for power generation. So basically these three technology are used for power application, that is combustion, gasification and digestion. So what exactly this process is, I will explain in next few slides. So this is a biomass combustion process for power generation. It is similar like conventional coal-based power plant. So instead of coal, here biomass is used. So this is biomass handling system. This one, then this is the conveyor belt from where that biomass is going to the boiler. Here it will be combusted and it will generate high pressure and temperature steam. That steam, similar like conventional coal-based power plant, it will go to the steam turbine generator, which is will generate electricity. Then electricity will be connected into the grid. So this is called biomass combustion process for power generation. Here biomass is combusted, means in presence of oxygen it is burning. Another technology called biomass gasification. So instead of combustion it will be gasified. So here what will be happening? Here there will be very limited oxygen supply or there will be no oxygen supply. So instead of combusted, it will be generating gas, that is called producer gas. That gas is mixture of carbon monoxide, hydrogen, methane, which has some combustible property similar like any natural gas type of things. Only that density of energy is lesser than natural gas. So again here the gas will be produced in the gasifier chamber where there will be no oxygen supply, and the gas will be having some tar and particulate matters. So this needs to be cleaned and cooled before going to the combustion chamber. Otherwise the engine will be fouled. Then it will generate electricity. So sometimes whatever we are doing, the heat which is coming from the combustion turbine, that will be simply wasted, that heat, and it will be vented into the atmosphere. So instead of that, that heat can be again go to the one boiler, that is called heat recovery steam generator. So this heat will be heated water which will again generate some steam, and again the bottoming cycle this is called one main cycle power plant, and this is called bottoming cycle power plant. So here that steam will be again generating electricity by steam turbine generator. So here efficiency of the whole system will be increased because we are utilizing that exhaust heat from this primary power generation cycle to the secondary power generation cycle. So as a result, the efficiency of the gasification system will be increased. Sometimes in this gasification chamber, we are using coconut shells or wood, those type of material. So after gasified, it will be coming to the bottom. Then that charcoal means after gasified of that coconut shell or wood, that will be very good material for activated carbon generation. So that byproduct, instead of wasting, we used to generate to use as a activated carbon, and activated carbon it is very costly. So this is total system is called integrated gasification combined cycle power plant. So this is another way to generate electricity by biomass gasification process. This is another process from where we can generate biogas, and the biogas can be used for heat or power generation. So here what is happening in a Gosala, there will be many number of cows. That cow dung as well as urine, it will be coming to the one storage chamber.
For the world. Can I? Why is it like that? Without the world, but for the world. Without the world.
Can you please mute? So it will go to the storage chamber, then after that it will come to the mixing chamber where it will be mixed. Then that slurry will go to the one digester. Here there will be no oxygen supply. So here it will be digested and it will generate some biogas. That is called biogas. It is a mixture of carbon monoxide, hydrogen and methane, and part of the will be sulfur. So sulfur and other contaminants needs to be removed. Then it will be stored into a one gas storage tank. After compressing, it will go to the gas purification system where it will be cooled and it will be a heat density or energy density will be increased. Ultimately, it will be going to the gas turbine, which will generate again electricity. And the slurry, that after digestion, it will come to the outlet pit, and once it will be dried into the one pond, so that manure will be used for gardening purpose, or it will be very good manure for agricultural field. So again I will just show one small video so that you will understand that how the biogas system is working for power generation. Maybe again the sound will not be audible to you, but I think you can see and you will understand that how power is generated from biogas plant where biomethanation technology are used. So this is a one Gosala in Ghaziabad. So here I visited. So here lots of cows are there. Then the cow dung, whatever is coming, sorry. So it is digested in the digestion chamber. Then it is going to the one engine that is called producer biogas based engine. So which will be, there will be two types. One is 100% biogas based engine. Another one is biogas as well as some part of the diesel will be used. So here this gas engine is totally run by biogas. So there is no diesel is required. So the compressor will be giving very good amount of pressure, and energy density also will be increased, and it is going to the biogas engine where it will be combusted and it will run that turbine and it will generate electricity. So again, another one renewable energy sources is wind. So I am not talking about other sources of energy in details because you know that one. So once wind is blowing, then electricity or power will be generating, and the amount of power will be generating from wind plant is 1/2 into rho into A into V cube. So rho is the density of the air, A is the total swept area of the blade, or I will say that rotor, this one, and V is the velocity of the wind. So this is another way we are harnessing renewable energy. Then hydro also, again, this is another renewable energy sources, and as per Ministry of New and Renewable Energy, if it is less than 25 megawatt, then it is called renewable, otherwise it will be large hydro. Another energy sources from renewable, that is called geothermal energy. In India, GSI estimated geothermal potential about 10 gigawatt, and in this month Eminari notifies national policy on geothermal energy to accelerate India's goal on the net zero emissions. So in couple of years we are expecting there will be few geothermal projects also will be coming in India. So right now only one small geothermal plant is there in Arunachal Pradesh, that is used mainly for domestic hot water generation, but here also electricity will be generated into different way. So there are three type of geothermal plant. One is called dry steam power plant, plus steam power plant, and third one is binary cycle power plant. So for all the cases there will be two wells. One will be production well, another one will be injection well. So what is happening? If we go at depth of the earth, the temperature will be increased. Even I will say that as a, if we go center of the earth, then temperature is 6,000 degrees centigrade. So after roughly say 2 to 3 kilometer depth, if we dig one well, then that hot steam will come. So that steam directly can run the turbine, and generator will be coupled with the turbine, and it will be having generating electricity, and then steam after cooled and generating electricity, again it will be injected and it will be go to the interior of the earth. So if the temperature is not enough to run the turbine, then what we are doing, this heat we are passing through one heat exchanger, where other cycle it will be having low boiling temperature ammonia. So this ammonia will be heated and it will be driving turbine and generate electricity. Then that after transferring this hot water heat to the ammonia, again it will go to the injection well and it will go to the earth inside. Another renewable energy called ocean thermal ocean energy. So it refers generally three type of technology. One is ocean thermal energy conversion, OTEC. So India wise potential is 180 gigawatt, then tidal energy and wave energy. So this is across the shore area, ocean energy potential is there, and there are few pilot project right now. Different developer are planning. So here what is happening, when sunlight is falling onto the surface of the water, then it will be heated. So as we go down, then temperature will be reduced. So here what is happening? This is a closed cycle where again ammonia, which is low boiling fluid, is used. So this ammonia will take heat from the topmost hot water, and again it will be high pressure and temperature will be generated, and it will be driving the turbine. After generating electricity, again it will come to the condenser, where it will be cooled by cold water, which is little depth of the sea. Then again this ammonia will go to the evaporator, it will expand, and it will again go to the turbine, and it will generate electricity. So these are the different renewable energy sources available for power generation and can be used for microgrid applications. So what are the renewable energy challenges? In India, although we have robust demand, because our load requirement is increasing day by day, then investment also increasing. Many developer investors, they are ready to invest for this type of new technology like ocean thermal or geothermal or biogas plant. So invest wise there is no problem. And India government also having policy support, because solar, wind, everything's policy is there, and geothermal, ocean thermal policy was not there, and recently India government has started this month itself that policy. So in future we will see that with policy support from India government, some of the this type of new type of renewable energy will be used for power generation applications, and most probably it will be used for microgrid application, because initially nobody will be going for bigger capacity plant. So they will do small capacity, few kilowatt or maximum megawatt scale plant for power generation, which will be utilized for microgrid application wherever that electricity is not there, particularly northeastern states where geothermal potential is there, but some of the area due to hilly terrain it will be difficult to make conventional grid line, and it will be having microgrid system. So India has challenges, like because in next 12 years India electricity requirement will be growing by 2.5 times, which is very huge. And to meet that requirement, we need to go for very bigger scale storage capacity, which is in between 25 to 35 gigawatt. Then we know that millions of people are staying in village or some of the island like Sundarban, where electricity do not have. And most of the electricity is coming from imported oil by generating electricity, and India also have climate change issue. So these are the challenges have India for renewable energy. There are other domestic challenges like is there, because if we see this picture, so in different states, different developer, they are not able to install their capacity of the different plant due to these many challenges whatever having. So as an example, Renew Power 500 megawatt plant is delayed by 12 months. It is in Gujarat in solar plant. Then again, as an example, Tata Power Renewable Energy 350 megawatt hybrid plant, that is solar and wind in Karnataka, it is delayed by 9 months. So different developers or owners, they are not able to develop their determined capacity with particular power purchase agreement with the government entities due to these challenges. Even not only that, there are some hidden challenges also there, like we although we have meteorological models how much energy will be generated in tomorrow or next month or whole year, but still that exact prediction cannot be made due to different climatic factors, natural calamities. So everything is uncertain. So even if we design something, it cannot meet that our expected demand. Then even if we have extra energy, say from solar plant, then there is a no option for storing, because if we go for storing option, then that capacity of the storage or system size will be very high. So due to that, we will be losing very big amount of solar power. So another thing is there, some of the policy also creating some problems. In Rajasthan, we have seen that power purchase agreement, as per that government entity, they said that in a year you can pump this much megawatt hour of electricity. So more than that electricity you cannot pump. So what happened, within 9 months they meet that planned target to evacuate. So remaining 3 months, although they are producing that energy, but due to that curtailment at the grid level, they are not evacuating that power. So that power is wasted. So these are the intermittency challenges also there for renewable projects in India. But anyway, government is also changing that policy so that it will be customer friendly. So now I will talk about microgrid. So why microgrid is required? So far we have discussed what are the challenges, what are the problem. So due to these problems, like to power a small population in a remote area which has no access to the main grid, because I personally visited some of the island in Sundarban like Gosaba, then other island also. There is no conventional utility grid is available. So Gosava Island, they have one community scale gasifier. So from that gasifier they are generating electricity and they are distributing in that village. Similar line in Sagordip Island, they have also internal one grid. So they are generating electricity from solar, then wind as well as DG, and they are distributing that electricity throughout the island. Then we know that if even if we generate electricity into centralized way, then there will be heavy transmission and distribution losses. Generally, the transmission and distribution losses across the world, even if we see that, it will be in the order of 8%. So minimum 8% or maybe some more than that percentage energy will be lost due to transmission and distribution. That's why we used to go for microgrid system. Then the need to use renewable energy that are present near to the customer, because maybe that utility grid is not there, but this type of renewable sources are there. Maybe some of the places geothermal will be one of the good option, like some northeast Himalayan area, there is a good geothermal potential. If we harness that geothermal energy, presently government is thinking those type of things. Wherever that electricity is not there, so from that geothermal energy we can generate electricity, and by help of this type of system, we can supply that power to the rural community, and it will definitely accelerate our energy transition and India's net zero goal. So what is the potential for microgrid? So if we see this one, so in India community microgrid, the growth rate is 18.8%, which is very good. And not only that, today in India 2025, our community microgrid capacity is 304 megawatts. So India also have planned to go for 5 times of today's microgrid capacity in next years. So this is a very good scenario for microgrid promotion in India. Then I will just tell what is microgrid. So microgrid are small scale version of power grid which distributed energy sources, that is DER, here wind turbine, battery or flywheel, solar cell, fuel cell, then and storage system, and also loads are localized in a defined electrical boundary. So this is my electrical boundary, and it has one common point of common coupling, and it offers alternate solution to the grid stress problem, because if we have that microgrid, then main utility grid will be having less stress. Then it can be operated in grid tied as well as islanding mode. I will tell about more details in the later slides. And for a grid tied microgrid, one can produce electricity. So this is a grid tied scheme, and excess energy can be sold into the grid. And there will be two type of loads, non-critical loads and critical loads. And I will tell what are the different types of loads also there later. Then it is able to operate in an island mode, that is able to supply critical loads without main grid dependency. Another features is that it able to consolidate distributed generation, load and energy storage device in a single entity. So as per government, as per US government Department of Energy, they used to define what is the microgrid capacity. So commercial microgrid capacity will be more than 50 kilowatt, whereas community or campus it is 1 to 10 megawatt, and utility scale greater than 10 megawatt is the utility scale microgrid. And yesterday I talked about one microgrid project in Saudi Arabia, which will be the world largest microgrid, that is 5 megawatt capacity. So that will be the world largest microgrid once it will be installed. So it will be supplying power for the whole village. So this is the microgrid capacity available. So I will say that this capacity can be 50 kilowatt to few tens of megawatt. Then what are the microgrid components? So in microgrid, it presents various type of generation sources that feed electricity to the users. These sources are divided into two major groups. One is thermal energy sources and other one is renewable energy sources. What are the thermal energy sources? Example, micro gas turbine or diesel generator. Whereas wind, whereas renewable, we already talked wind, solar PV, hydro and biogas. And it is also not possible for a microgrid system to rely on total renewable energy for 100%. That's why for a microgrid application, generally this type of sources are used. Sometimes it can be a fuel cell also. So these are the loads in a microgrid system. So what are the loads? Priority, consumption and flexibility. Within priority it is critical and non-critical. What are the critical loads? Hospital, fire station, data center, police stations, and non-critical household, supermarket, etc. In case of consumption also, there are low consumption like household and medium consumption like business, supermarket, small office, and high consumption like industries. Whereas flexibility load is responsible for charging electrical vehicle or non-responsive, that is household. Then third component of a microgrid, apart from renewable storage, so is another component for a microgrid system. Why storage is required? So storage is required to smoothening that power supply to the load or grid. Another option is energy shifting. Means if we store that energy whenever more generation is there in case of a solar, then it can be discharged that battery or storage system during later, so that we can extend that energy shifting from daytime to evening time or night time. Again, another purpose is support the grid when the wind is not blowing or water is not flowing for hydro generation or sun is not shining for solar generation. Then also storage is required to supply peak power demand, and also it stores energy produced by the energy sources whenever it is not used. What are the different type of energy storage systems? So basically it is categorized under mechanical, electrochemical, chemical, electric and thermal. So mechanical means flywheel, compressed air and gravity. Then batteries for is electrochemical, chemical is fuel cell, hydrogen, electrical is alta capacitor, and thermal is different type of storage system, solid or liquid base, and falling particle also another new type of concept is coming into the market to store that energy into falling particle, that is basically a simple glass type of sand material which will be used during night time. Then what are the components of a microgrid? So I told. Now I will tell what are the configuration of a microgrid. So basically there are three type of configuration is available or categorized for microgrid, that is called off-grid or standalone system, then grid connected or on grid, and third one is hybrid. So here we can see that secure access to local energy, then it minimizes fossil fuel dependence, and it is simple grid design. But in this case, it is a little bit complicated design, and it is flexible because it is using grid electricity which is coming from multiple sources, and the main grid will be acting as a backup source. So yesterday I have told how the scheme for a solar microgrid operates. So this is the scheme for grid connected system. So it is meeting that consumer loads, and remaining things it is going to the distribution network, and bidirectional meter it meters that import and export power. Ultimately it will be billed. So now third configuration is called hybrid configuration. So what is this? A typical configuration of a hybrid microgrid can be divided into two subgrids. One is AC based subgrid, which is connected to the DG, means diesel generator, wind turbine and AC loads, and DC based subgrid integrating with fuel cell, solar photovoltaic plant, then electrical vehicle and DC loads. And this AC bus and DC bus, it is linked with one bidirectional converter that is called BDC. So one bidirectional converter is sufficient to integrate between DC grid as well as AC grid. So the advantages of hybrid microgrid system is to reduce investment cost by reducing the number of electronic power converters, because only one BEDC is sufficient. Then it enhances nodal reliability due to availability of the alternate sources like these things, minimize the renewable energy generation, maximize the renewable energy generation. These are the different advantages of a hybrid microgrid system. And grid connect, okay. So compared to the conventional AC and DC microgrid, hybrid microgrid can provide a more effective solutions for integration of system components that are inherently AC and DC oriented. So now what are the advantages or disadvantages of microgrid? So definitely, as we are using renewable sources of energy, so it is environmental friendly relatively. Then operation and investment issues like it, as I said, that it will be giving little bit relaxation to the transmission and distribution system, so that congestion of power will be minimized. It will reduce the transmission distribution losses, because it will be very locally specified, locally distributed. Then it can give reactive power support to the whole system. These are the invest things, and also it has good advantages in terms of resilience and reliability. So these are the points: decentralized of supply, better match between supply and demand, reduction of impact of large scale transmission and generation outage. Those are the advantages of microgrid system, whereas there are disadvantages like it is relatively more cost, then market monopoly is there, stability issue is there, bidirectional power flow, and uncertainty. These are the disadvantages of microgrid system. So now I will talk about integration of a microgrid system. So for integration, energy storage is very much essential for an efficient and reliable clean power for microgrid. It allows to generate clean energy when it is abundant, store it, and then again to use it when it is really needed. So how it is? So it will provide backup power, then continuously it will match electricity supply and demand scenario, and also it will be stabilizing power quality with grid forming inverter in case of if it is a solar. And there are some grid constraints also there due to renewable power. So how to address this grid congestion issue? So basically we can categorize into three. So we need to do long distance transmission can lead a congestion without a robust infrastructure. So we need to go for robust infrastructure. Then we need to upgrade our grid system to handle increased renewable power. Why it is required? Because India government has planned by 2031 or 32 the renewable capacity will be 600 gigawatts. That means we need to do robust infrastructure, particularly for transmission and distribution. Otherwise, grid congestion will come into picture. In case of upgrade offshore wind farm, again it needs some efficient transmission system from offshore to the inland area. So grid upgradation, modernization, and implementing microgrid technology is very much essential to handle 600 gigawatt of renewable power in near future. Then what are the control aspects? So main control is required for electrical parameters for a microgrid system, that is voltage, frequency, active power, and reactive power. So microgrid control system can categorized here as a three things: primary control, secondary control, and tertiary control. So in primary control, what it happens? It stabilizes voltage and frequency. After an islanding event, microgrid may lose its voltage and frequency stability due to mismatch between power generation and consumed. So to offer plug and play capability of distributed energy generation and properly share active and reactive power, preferably without any communication links. So now secondary control, what it is? So secondary control restores the microgrid voltage and frequency deviations caused by the primary control. So due to this primary control, whatever instability will be there, so that secondary control, it will be reducing. And tertiary control is the last and slowest control which manage power flow between microgrid and utility grid, and it facilitates economical operation solutions. So this is the way a microgrid control system generally works. Since the goal of today's microgrid is renewable energy generation, power purchased from the main grid should not be considered for 100% from the renewable energy sources. So we need to store this energy and sell it back to the grid with higher tariff. But one problem also there for this type of system, people may do whenever that grid electricity is little cheaper, that time they may use that electricity to store into the battery, and again that same electricity will be sold to the concerned authority with the agreed tariff rate. So this is a one problem for this type of microgrid system to control how it will be things. So those type of challenging things also come into picture. So now in a microgrid system, how power flow and metering is done. So there will be two scenario. First scenario, renewable energy is not generating enough power to the microgrid. In that case, there is no energy storage device, and microgrid import power to the main grid from the main grid. And scenario 2 is little different. Renewable is generating excess power. Maybe there is no storage system, or even if it is storage system is there, it is stored maximum things, so it cannot be further stored, and microgrid export power to the main grid, that is called utility grid or national grid. So to do this system, now we need to have net metering option. So what net meters? It measures energy consumed by the microgrid. Again, it measures energy exported to the microgrid. That means when we are exporting energy to the grid, then it is metering. Again, once we are importing energy from the grid, again it is doing, and the between two minus, it is net meter will be done, and it will inform to the utility and microgrid owner about power exchange on the PCC. So now I will talk about a few case study related to microgrid. So shall I stop for the time being for some question answer, or maybe lastly we can discuss?
So if you want question answer right now, participant can question you. As you wish. How many slides are pending?
Maybe another 4-5.
Then you can continue.
Okay.
You can continue. We have last 15 minutes, maybe for questions.
Okay, thank you. So this is case study. It is a project for biomass energy for rural India in Karnataka. So government of Karnataka in association with international funding agency, that is United Nations Development Program, and also India Canadian Environmental Facility, they implemented this very project. So this project, I told that gasifier means by use of wood. Here we are using woody biomass like eucalyptus wood. So that wood is used for biomass gasification, so which will generate electricity. The broad goal of this project was to develop, implement, and demonstrate and disseminate a bioenergy package to meet the rural energy needs in a sustainable and proprietary way to promote rural development. And this is the demand is meeting for 25 villages, which consist of 500 households. So there are 3 villages, Kobigiri, then Madhugiri, and Borigunte. So these are the 3 villages. There are total capacity of the gasifier is one place, it is 3 into 100 kilowatt, and 200 kilowatt, that is total 500 kilowatt, and other 2 villages 240 kilowatt and 240 kilowatt. So this gasifier is IISc Bangalore licensee gasifier they have given, and voltage limit is 415 volt 3-phase system. And as I said that it is distributing power to the 500 households. So here this is the producer gas that I told that composition is carbon monoxide, methane, hydrogen, and rest is nitrogen. So it is operating right now. It is not. It life is over because it has done very long back, and at that time whenever we involved, the design was for 15 years designed. So this is the sum of the cost things, and generally for your information, to generate 1 unit of electricity, roughly 1 kg of biomass is required. So this is one biomass based microgrid project in Karnataka. Then another project, it was for township. It is integration with solar photovoltaic battery to meet 1.1 megawatt load. So here we have done some study related to peak load, average load, daily load. Based on that, we have studied different scenario, a different solar PV capacity or PCS capacity or battery capacity to meet the 1 megawatt or 1.5 megawatt load. So we have seen that although here that extra electricity is little more, but cost of generation, that is called levelized cost of energy, is very less. So that is the reason we have selected their load requirement 4.5 megawatt solar PV plant and 1.1 megawatt hour BESS system. So as a result, what is happening? What is the impact to doing this type of microgrid system? Grid import energy is saved by 72%. Whatever earlier we are importing that grid electricity with little higher tariff, definitely more than 4.59, because if we go for peak electricity charges, it may be more than 7 rupees per unit. So average tariff also will be closer to 6.5 or something like that. So as a result, we are saving 58% of the bills annually. Then annually, even in terms of money, we are saving 95 lakhs rupees due to this microgrid system with battery energy storage system. Then definitely, as we are using solar PV, so we are using 54% of the green electricity, and capital cost is 25 crores. And generally, this type of system payback period will be 9 to 10 years. And these are the some monetized and non-monetized benefit for this type of system. It controls RAM rate of due to the PV plant. Then grid demand charges also it is reducing because we are installing 4.5 megawatt power plant. That is the reason that demand charges also reducing. And definitely, as we are using renewable energy sources, so carbon footprint also it is reducing. So another few case study, it is for one country in South Africa, in Seychelles. So there also that country, basically there are 108 islands. So within 103 islands only people are staying. Remaining islands, no one is staying. And in that country, only sources of energy is DG-based power plant. And here we visited and we done some study, and ultimately we proposed for one microgrid system to meet the requirement. So we proposed 1 megawatt solar PV plant along with 750 kilowatt hour battery along with existing DG set, so that they can meet their renewable power. So another case study we did for institutional campus in Bangalore. So here also we proposed 600 kilowatt solar PV plant and 100 kilowatt hour battery along with 2 DG. So what are the benefits? It is increasing green power. Then it saves peak energy. Grid islanding also it is one of the biggest benefits, and it reduced DG operational hours as well as electricity cost also. Another study for industrial campus. So this assessment study we mainly did to address what are the voltage variation in grid profile due to microgrid, what are the effect of grid outage times, and what are the DG operations and impact also we have studied in this case. So it is almost similar like yesterday, but here there are some other softwares like WindPro, WAPS, Windographer we are also using for wind things. Rest other things, it is almost similar like whatever yesterday I was explaining. So HOMAR is hybrid study for many things. Thermoflow also different type of renewable energy we can study. This is also there. So these are the softwares and tools we are utilizing. So now just I will try to play one video how HOMAR we are using for microgrid design. So today what happened, I am taking this session from my home. So I do not have direct access to that HOMAR software today. So let me try one video so that you will be understanding. Although sound may not be audible, but whatever things are content are there, it will be available in the write up. So it will tell how it will be. Just allow me 1 minute. So this is HOMAR software we are designing for microgrid for different type of energy sources. So here also one can download this Homer software, which will be 21 days free, so that people can practice and understand. And they have also online technical team available to guide how to use this program. And Homer is integrating software between different renewable or conventional sources of energy. So generally what we used to do, we used to do solar generation from solar software like PVSys, wind generation from wind software like WSP, or different things. And Homer also have inbuilt meteorological data which can be also used for see how much generation is possible from different renewable energy sources. It also have some library where cost of the different system or component, including battery, everything is available. So once we'll be using Homer Optimizer tool, then based on cost of solar plant, DG plant, battery energy storage system, wind plant, whatever energy sources we are using for microgrid application, so based on that cost input, it will give optimum solution. Which solution is the best in terms of economics? So it will be calculated in a faster way, and maybe it will be giving n number of cases with the different permutation combination to match that particular load. So as an input into the Homer, we need to give what is the load we are giving. We can give that load in terms of daily, or we can give monthly or yearly. To match that load, it will automatically dictating which is the best configuration and optimum configuration for that type of particular applications based on that cost data bank. So where it itself that, otherwise we have also in our office, we have also cost data bank. So we used to give little bit fine tuning of the cost data, and accordingly it will design best winning option or best cost cheap option by Homer things. And Homer also have three module. One is Homer Pro, that will be for standalone system. Then Homer Grid, that will be for utility system, and another version is there that is for distributed generation. So that's all from my side. Now I think we can take questions answer if, for 10-15 minutes we have. So it is done from my side. So now it is open for questions and discussions if you have.
So if you have any question, please write in the chat box. Any questions from participant side?
Hello, good evening, ma'am. Tamil Chelli from Pave Engineering College. Sir.
Yes, sir. Yes.
Hello, sir. Can you hear me?
Yes, I am able to hear you.
Sir, Homer software is a free software, or we have to pay for that software, sir, for installing integration with the grid?
As I said, it is available for 21 days trial. So that time one can install and can practice. After that, same system cannot be used. If you install some other system, again you can continue for another 21 days. Similarly, a PVC is also like that. So it is 1 month free. So once 1 month over, maybe you can install some other system. then you can try to understand that one. And if you are okay with that one, then maybe you can talk with that homework team. And as I understand that they have some good discount, particularly for colleges and uh, other institutions. So it is only free for 21 days.
Okay, sir. Thank you, sir.
Good evening, sir. There is one question in the chat box.
Okay, yes, sorry. This question is
From Pooja Sharma.
nowadays we are talking about smart grid as well. So can it be linked to what we have done through this presentation? So smart grid also similar type of things. It will be having smart features, controlling all the things will be there. So I do not have a very good understanding about that smart grid. Sorry, I may not able to link into that way. So it is another way to use that all the control system into smarter way. I think if we do not have much questions, I think it is done from my side.
Swapna madam.
Thank you, sir,
Yes.
for this wonderful session. We have learned a lot. Thank you for your valuable time. Thank you, sir.
Okay. Thank you all for listening.
And happy Durga Puja, sir. Good night. Also.
Yes, same to you for all. So I was also a little worried when this session date will come, because tomorrow onwards also will be having celebration. It is starting in Bangalore. So I am in Bangalore. So in Bangalore also lots of Durga Puja are happening, and I am very closely associated with one of the Puja committee that is called KBA, Kagdaspura Bengali Association. So tomorrow onwards, maybe we'll start our Puja celebration here. So I also wish you people also you enjoy that Puja. Maybe tomorrow also this session is continuing.
Yeah.
So
Yes, sir.
It's continuing.
3 sessions will be there along with one test.
Okay. Okay. Thank you all.
Thank you. Good night, sir.
Okay. Good night all.
Thank you, sir.
Thank you.
Hello, sir.
Yes.
Thank you.
Sir, can you kindly give your mail ID? I also stay in Bangalore, so I'd really love to connect with you.
Okay, mail ID. Just I am sharing my screen once again. Maybe if you don't mind,
Write in the
then
chat box, sir. You can write in the chat.
Okay. That I can also do. Yes, correct. Okay, I will give a mail ID as well as a mobile number also. So you are also in Bangalore. Okay, then maybe you
Yes,
can.
sir. I also stay in Bangalore.
Where you are staying?
Sir, I stay in Electronic City Phase 2. I'm now teaching in Alliance University.
Okay, good. Maybe you can touch with us also. Maybe some of the industry collaboration, if you want to have, then maybe we can also discuss those type of things, because we are also looking for people like you, academicians, so that we can jointly do some project, or sometimes we are taking outsourcing from different colleges for different professors, because we do not have sometimes that type of expertise or skill set. So project to project basis also we used to take support from you people, because I very frequently connected with Jadavpur University, then IIST. So we work together with support from industry institution like from your side. So in future also, if we want to do some of the collaborative projects, then maybe you people also connect to you can try to reach me also, so that we can discuss and we can do jointly something. That also can be one of the possibility.
That's nice, sir. Please, sir, write
And
your
even
email
if
ID
you
so
need
that we
some trainings also, maybe you can also reach, so that our expert can give training to you also, which will be helpful for you.
Sure, sir. I'd love to reach out.
And
And
sometimes
sir, thank you
actually
for
we
your
are inviting teachers like you people just for industry training. So if it is if you are in say Kolkata, or if someone is in Mumbai, they can reach through me also, so that we can try to arrange some of the training sessions related to some softwares, particularly electrical software like ETAP, PSSE, those type of softwares also. Maybe we can give training. So our experts are there. Sometimes it can be without any charge, because we also want to be associated with institutions also. So that can be discussed with our top management. But generally, we are also ready to support you also for providing training, or giving some of the lectures, so that you can enrich your knowledge, and you can come and we can give that training also. That also possible. Anyway, so I am giving my email ID as well as phone number in this chat box. Whoever is need any assistance from Tata Consulting Engineers, please reach to us, so that we'll discuss and we'll do the needful things. Thank
thank
you
you so
once
much, sir.
again.
Thank you for your valuable session, sir.
So I have given my email ID and phone number also I am giving. So you may please reach to me if anything is required.
Sure, sir. Would love to reach you.
Okay. Thank you very much.
Thank you, sir.
And please,
Thank you so much.
so wish you all the best and enjoy Durga Puja.
Thank you, sir. Shubho Sharadya to you as well.
Okay. Good night.
Thank you, sir.
Good night, sir. Good night.
Dr. Bhattacharjee did his PhD in renewable energy from IIEST Shibpur. Since 2019, he has been working as faculty member in the Department of Electrical and Electronics Engineering at BITS Pilani, Hyderabad campus. He has over 10 years of teaching and research experience in different areas of electrical engineering and renewable energy. He has published 30 reputed SCI international journals, 32 international conferences, 6 book chapters, and a book in the area of renewable energy. He has filed 6 patents, and one of them was granted in March 2023. Dr. Bhattacharjee has 7 ongoing funded research projects in the field of renewable energy, battery storage, and EV charging stations as PI and co-PI from different Indian government agencies like DST, DBT, etc., and also private industries. He is a recipient of the DST Young Scientist and Technologist Award in July 2024. He is currently having active research collaboration with RMIT Australia, University of Buffalo, New York, University of Exeter, UK, etc. through joint research work. His current research areas are solar PV, battery energy storage systems, energy management, smart microgrids, power electronics converters, machine learning applications in renewable energy and electric vehicles. So, sir, please start your session.
Yes, I think, yeah. Am I visible and audible, please?
Yes,
Confirm once.
yes, sir.
Okay.
Yes, sir. Yes, sir.
Yeah,
Yes,
thank you so much, Shampa madam, and also other organizers of Netaji Subhash Engineering College for organizing this FDP program. And we are here to share our knowledge as far as we can within that given time frame. And today, I'm going to share some of the important work and then related information regarding the topic which is given to me as a, let me share the screen. If it is visible, can you please confirm once?
Yes, sir, it is visible.
Okay, fine. Let me put in the slide mode. Is it showing clearly now? Can I start?
Yes, sir.
Okay, thank you so much, madam. Yeah, okay. So today's topic of discussion is role of battery storage for sustainable e-mobility. And thanks for a nice introduction about the overview of what we do actually at present since couple of years. So here, starting with the motivation and the content of my topic is of discussion is that the motivation of need of energy storage, then energy storage for sustainable development as a goal, and the role of battery storage, specifically battery storage, I would focus on here the topic wise, and sustainable e-mobility, how it is important, its challenges in implementation and possible solutions, recent advancements and research done on the battery storage and conclusion of the work. So to start with the basic points which I would like to highlight, everybody knows about it. Just for a small recap, we can say that role of battery storage or energy storage as a whole, as a family, that the backup power supply is essential when the main distribution grid is unavailable or weakly available, you can say. And then demand side management and peak load saving is one more important part in the power systems aspects. Then allowing heavy penetration of renewable sources, RE sources, into the existing power grid. These are the areas where energy storage can play a great role. And power quality and frequency stability issues also can be mitigated by energy storage choice, suitable energy storage integration with the renewable sources as well as the power systems. And last but not the least, the last important which we have to focus in today's discussion is the e-mobility or the e-transportation, then electric vehicles basically, and charging infrastructure. Here the energy storage plays a key role. We'll talk about it in different aspects today. So starting with the energy storage as a whole, as I said, we'll move on to the battery storage. We'll focus on more in the battery storage part. But before we go to that, let us have a quick check of the status of the current energy storage topology or technologies, what we have in our technological hands. So that is right from the bulk power management, and then the ancillary or the distribution grid support, load shifting these or peak shaving these areas, then the power quality and the UPS small scale to medium scale energy storage applications. We have different large scale from pump hydro to compressed air energy storage. We all of us know mechanical energy storages that needs large scale of infrastructure as well as cost of capital cost, which is called. And so for the mobility in the sense for the mobile applications, means for portable applications, we prefer those specifically the batteries have a large set of battery technologies available in the market, and also still research is going on in material science aspect as well as the systems level research. Talking about the small and medium scale energy storage. If we talk about you can see multiple batteries technologies are available as per research, and some are also coming up. We have not accommodated everything here. A couple of popular battery storages are mentioned here specifically, and also flow batteries are again although old technology, but again newly it has been revamped the last couple of years in multiple aspects of the EV charging station as well as the stationary storage applications. And looking through the high capacity supercapacitors, the problem is the short-term discharge. We prefer this storage, not for the long-term or large scale. A couple of challenges are there. We will talk about it, and look at this one. It's the extension of the previous one, which I would like to highlight before you go to the technological aspect of the energy storage. You can see here multiple energy storage coverage areas are given, like discharge time is the y-axis and x-axis is the power rating. So you can see here from kilowatt to megawatt scale we are having, from watt to megawatt rather, and then discharging time from seconds to hours we are having. So here you can see this is the battery I can point out here, which covers a coverage area is from the wattage to almost like hundreds of kilowatt, and here also from the seconds to hours also it can achieve while discharging. Whereas you can see the other storages are somewhat biased. Either it is totally in the energy side, long-term discharge, or in the short-term discharge in the supercapacitor side. And also you can see here the red dot lines is the HFCSS, nothing but hydrogen fuel cell storage systems. So this is one of the important and most promising energy storage coming up in the market in a big way, and to compete the batteries, but it has the challenges of storing the hydrogen, and also the pipeline of the carrying the hydrogen to the actual applications. It's also expensive. It is definitely technologically challenge is there, multiple challenges are there. So research is going on in the storing hydrogen topologies and also generating hydrogen from different green power sources called solar powered green hydrogen sources are also there. Electrolyzers are there, which are helping in water splitting and generating hydrogen sufficient for the powering the electricity applications through fuel cell. So this kind of application is very important, and energy conversion and storage of fuel cell, which is hydrogen as a fuel. But the problem is you can see the coverage area is huge, but it could have solved all the problems. But there is a challenge in hydrogen storage and generation aspects, and also carrying it to the applications. That's why for now, battery storages have taken the most of the attention of the researchers and the application side in the smaller to medium to even large scale of power applications. So we'll talk about mostly batteries here in this total discussion, different types of batteries and their applications in EV respects, and then how to do a bit more details. Some of my research work also with my PhD scholars I will like to share, which may open some window and the areas to do for further research, the faculty members who are interested in such areas. You can see here, talk about the motivation as we are talking about. Going to the batteries sectors, we need to highlight a couple of points for the people who might already know, most of you, but to have a highlight on the issues. You can see here the energy storage for the electric transportation. It is our motive today. So BESS or battery storage can enable 30% of the required reduction in carbon emissions in the transportation sector and the power sectors, providing access to the electricity over 600 million people who can, who doesn't have the access or weak access, as I said, means intermittent access. Then battery powered vehicles promote the green transportation also, neglecting the fossil fuels, or you can say reducing the fossil fuel usage. And then between the this almost a decade, like 2010 to 2018, the demand of battery storage grew up by 30% annually and reached a volume of 180 gigawatt hour in 2018. It's a globally, not in India. Then market is expected to keep growing at the estimated 25% annual rate. You can see the spike in the rate of the growth to reach the volume of a 2,600 gigawatt hour within 2030. That's the target now. And battery electric vehicles accounted for 2/3 of the new electric car registration globally in this 2020, despite COVID pandemic. It got slowed down, but it still is quite a high, significant contribution of the battery operated electric vehicles. So you can understand how battery storages are required to manufacture as well as to scale up. And the share of the BEVs, battery electric vehicles, has significantly increased in the countries like Netherlands, UK, Norway, and France. So in India also we are not way behind. We are also in a faster growth. Then increased electric buses registration in 34% by 2020, and policy targets the electrification of 25% of the vehicle by 2025 and 50% of the all new buses or all new passenger vehicles in large scale to the battery powered. That is the target. And you can see here the projected as per our FAME, all of you I guess know about the FAME scheme. There is a faster adoption and manufacturing of electric vehicles. It's a government project of FAME action plan. In here you can see by 30% of the new sales share of the EVs by 2030. That's called the EV30 at that 30. That is the very important scheme nowadays, which is boosting up the EVs application more in the coming decade, and also the usage of batteries. Now, what you can see the large scale, 24 million of the two-wheeler EVs, and then 2.9 million of three-wheeler EVs, 5.4 million of four-wheeler EVs in the next 10 years. And by 2035, India will need to set up its own gigafactories of batteries. As I told you, that the exponential rise in the EVs adoption will lead to the large-scale megawatt to gigawatt-hour factories of the batteries will be required. And in the next decade, India's annual requirement of lithium-ion batteries, of course, that is now most popular for the mobile applications or the automobile applications for the lithium batteries for several reasons. We'll talk about it. Is projected to almost 26% of the annual global production. These are the motivations of why should we go for this today's discussion. I thought of telling you somewhere the latest news. So you can see the exponential growth of the batteries in E2W means electric two-wheeler, three-wheeler, four-wheeler and electric buses, or the large-scale vehicles of the EVs. See the growth from 2019 within the almost 10-12 years. You can see here right from it started with the gigawatt hour. You can see globally. From 4, it has gone to 441, almost more than 100 times. And you can see here for almost 500, it has reached as a gigawatt hour requirement projected by 2032. And for example, three-wheelers are of course less popular in the community transport like auto rickshaws and all. And four-wheeler passenger vehicles also are having more than 700 gigawatt hour requirement. Electric buses also selectively around 60 gigawatt hour of the batteries are required in the most of the countries who are adopting EVs to as a green transportation. And this is the slide which I wanted to share with you. That is the portable applications. We are talking about the EVs. So definitely it has to be flexible and portable. That is the most important part. Should not be bulky enough. So thinking of, I have taken this, prepared this slide for the couple of important parameters. One is you can see the types of the batteries, which are popular batteries in our market. And you can see the life cycle, average cycle efficiency, energy density, cell voltage, charge discharge rates. Toxicity wise also environment is a factor. We are talking about green environment, so we of course have to be careful of the batteries technologies which are less toxic or non-toxic, and say in nature. And capital cost is also a big factor in countries like India, where people are investing money, of course thinking of the long-term usage as well as the payback period. So lead-acid battery is the most popular and also localized, you can say, energy storage we have used so far. And nickel metal hydride also, and nickel cadmium and sodium sulfide, and also lithium ion. So this NAS and lithium ion is drawing the more interest nowadays in renewable energy as well as the electric vehicle sectors. You can see here these are comparable almost as per the life cycle. And 50% DOD means it's a depth of discharge, which all of us might be knowing who are doing the battery research a little bit. So depth of discharge is inverse of the reverse of the, you can say, the state of charge. That is if we talk about the deep discharge, and if we talk about the partial discharge, the cycle life gets impacted. So that is what we have shown here. Typically 4,000 around for the sodium sulfide, and then also the similar. Now, in fact, material science has improved a lot. So by electrode modification and also material capacities wise, the lithium-ion batteries have become even almost 5,000 to 6,000 cycles. Also, it has achieving now in the lab scale, but commercial scale it is still under 5,000. So we are having some of the finite life of the batteries. We have to have a renovation and also recurring expense if we use these batteries for the electric vehicles. But we cannot help, because you can see that the efficiency of the battery, DC-DC efficiency, charge discharge efficiency, cycle efficiency is quite high, almost 90% it can reach. Energy density wise, you can see also it's highest so far among the other battery which we have shown in the family of the batteries. And you can see here most important part is the volts per cell. That is even more important because of the compared to other batteries. You can see here 3.7 to 4.2 volts per cell, which implies that for the same capacity, the lithium-ion battery will take lesser space and also compact design, and as well as it will lead to the lesser space in the vehicle, or you can say design also optimized. And remember, the energy density is quite high. So that is most important part. And the rate of charge discharge is also important, because we have to have somehow fast charging, fast discharging for the EV charging applications. Nobody will wait for the longer time of charging. So chargers are nowadays, it's one more research aspect. Multiple types of chargers, efficient chargers, fast charger, moderate chargers are required to come in the market in a big way to support these batteries for the EV applications, more EV adoption. So C by 6, what is C? C is the C rate, is the capacity. You can see C is the ampere hour capacity. Let's say battery is having, a basic UPS battery is having, say, 7 ampere hour battery we have in UPS. So we have, say, 12 volt, 7 ampere hour. So C rate charging or discharging means 7 ampere. So it's an ampere hour. C by 2 means 3.5 ampere. 2 C rate means 14 ampere for a 7 ampere hour battery. So that is the example, just an example I'm giving for a smaller one. So C by 6 to 4C. So you can see, understand the range of the charge discharge capacity is also quite high for this battery. 4C, you can say 4 times the C also we can allow, but of course we have enough thermal protection is required. So 2C to 3C is somewhat moderate, and then up to 4C is also now adopted for the fast charging and fast discharging cases where transient comes in the EV aspect, as well as the fast charging is to be adopted. So that's why the batteries which are supporting the higher discharging charging rate, we are adopting those like lithium-ion batteries. And you can see toxicity of lithium-ion is moderate compared to the nickel cadmium, because cadmium is quite a toxic element. So that's why, and as well as lead is a toxic element to the environment. We have to somehow dispose this after a couple of say years or cycles of 1,000 cycles. But nowadays recycling is also being adopted worldwide in a big way. That is another market of research. That's recycling and repurposing of the batteries which are already being exhausted or semi-exhausted by the electric vehicle operations, or any small scale or the emergency load operations like electric vehicle. And after that, we are having a second life of it. We can use it for some household or the stationary storage applications for the second life. And after that, we have to either dispose or recycle. So instead of disposing, we are extracting as much as possible the material, and we are repurposing it or recycling it for a new energy storage or in new batteries. And then it can be avoided to have a toxic impact of the environment in the long run. And this is important. Looking at the capital cost, if you see, capital cost is quite, as of now, is high, but exponentially decaying with the time. Lithium-ion battery cost is exponentially decaying with the time, with the material cost, and indigenously, this manufacturing hub are being set up in the countries like India in a big way. As I have discussed in the previous slides, that India, how it will be taking place in global market in coming years. So this is the couple of batteries are important. Now coming to the stationary storage applications, where we need in EV aspect. EV is a mobile applications, or I can say transportable applications, but stationary storage somewhat needs for the EV charging stations. There we need a stationary battery storage for some charging purpose, and of course as a backup when the grid is not available somehow, then the battery, sometimes it is powered by grid, charged by grid, or sometimes it is charged by renewable power sources also. So looking to that, there is an important portion which we like to highlight is a new type of battery, as I told about, the flow batteries. If you remember in the chart we have discussed. Okay, by the way, just sorry to interrupt. Am I audible right properly? Just to check. Am I audible properly?
Yes, sir. Yes,
Yes,
sir.
sir.
Okay. Thank you so much. Yeah, so you can see here the lithium-ion battery we have just discussed in the last slide. So definitely you must be knowing about its ability and efficiency, cycle life, and other advantages. But compared to that, if we talk about the stationary battery storage, there instead of the you can see here the cycle life in the 4,500 and so on, we can have almost more than 10,000 or typically 13,000 plus cycle life of the new battery called vanadium redox flow batteries, which is coming in the market in a big way. Which is actually, most reliable as of now for the stationary storage applications in the long cycle life and scalability applications, where lithium battery has limitations. But one of the most challenging part is it cannot be used for the portable applications or for the mobile applications or for the EV application directly. We can have the EV charging infrastructure application, but not for the EV directly. Because it can be portable, you can understand from this one that although efficiency is somewhat comparable, but the cell voltage, you can say part cell voltage, Here it is almost like a 1/3 of the part cell voltage. That means it takes bigger space for the same capacity of the battery. That means we cannot recommend this for the mobile applications, means the automobile applications. And you can see here the full, I mean the charge discharge rate also not that much fast as the lithium-ion battery. We can make it, but because of its structure and the chemical reactions, it takes time to gear up. But major issues are, you can see here this cycle life. The battery life can be made even longer, up to 20,000 cycles, remixing the electrolyte of the anode and cathode, means anode side electrolyte, anolyte, and cathode side electrolyte is catholyte after the completion of a rated cycle life. Means, for example, after 8 to 10 years, we can further recycle or remix the, remix the electrolyte of the two sides and again make it as almost a new battery. So it is almost theoretically infinite cycle life, practically very, very long cycle life compared to the other batteries. So especially the application with solar and other applications, wind and renewable energy, we prefer this very long cycle life, scalability and deep discharge capacity we can use for the renewable energy sources, where the stationary applications like EV charging station, telecom sectors, data centers we can use. And also you can see the lithium batteries are suitable as of now for fast charging and relatively lower cost compared to that. If you can see here, the cost in a small scale, that's why the flow batteries are not recommended for the smaller scale of production, rather the large scale in a couple of kilowatt to hundreds of kilowatt as of now. Even a couple of things, megawatt of battery bank people are using in Denmark and other countries where with the wind power, they are using in megawatt hour scale. And in a large scale power system, that is different thing. But for the e-mobility, if we talk about, then charging station also can be some pilot project in Singapore, and as well as recently in India, people are also starting in different places. You can see here why this element, vanadium, we talked about, it has a reason. See, among the popular redox flow batteries, if we talk about, then definitely these are a couple of important things, that flow batteries, cycle life, cross-contamination is one effect, because there is a chemical issues are there, and cycle efficiency and nominal cell voltage. You can see here the iron chromium, zinc bromine are also popular redox flow batteries. Why redox means reduction and oxidation, that's why it happens while charging and discharging, as we all know. Basic electrochemical equations for batteries in the half cell of the anode and cathode side. And while it's a reversible equation where one side go for oxidation, other side has to have a reduction, and vice versa during discharging. So this VRFB or the vanadium redox flow battery is actually superior compared to the other two well-established flow batteries are there. There are a couple of more flow batteries coming up in the market, but they are still in the lab scale, not in commercialized in the big way. But we can see that for the 90% depth of discharge also, we are having these 8,000 cycles compared to these other batteries. Almost nil, because other cases you can see cross-contamination happens when through the membrane. As you know, the batteries, we are not talking about those basic chemistry here because it's electrical engineering aspect I would like to talk about. So the membrane, you can see that ion diffusion and the ion exchange membranes are there to pass the ions through from the cathode to anode and vice versa. And this iron chromium, you can see two different elements, iron and chromium, two different sides of the electrolyte. And also the zinc and bromine also, there are sulfates or the solutions are there. Whereas vanadium is both sides vanadium, it's all vanadium. That's why there is no cross contamination, which will further improve the life cycle. And efficiency wise, it's also comparable. And you can see these, the drawback for all the flow batteries is that it is good for the stationary storage, not for the EV application, but for the EV charging application, it is useful, where the stationary. This is the summary of the previous slide. You can say why this storage is there. First of all, longest cycle life, then scalability of power energy capacity. Scalability means nowadays it's a matter of scalability everywhere. We need technology to be scaled up. Let's say today the demand of a charging station is 10 kilowatt, and tomorrow the charging station demand will be 15 kilowatt, 20 kilowatt. And also the time span will be increased for more vehicles are getting penetrated. So instead of total renovation of the batteries, we can have some more stack size. You can say series and parallel we can connect, and we can make it more power capacity without changing the entire battery pack for this particular battery. The beauty is that. And the more electrolyte you can add to the system by external resources, so you can increase the energy capacity. That means power energy capacity can be independently scalable, which is quite an important feature which no other batteries have at the present market. Now, of course, no toxic gases, although vanadium is toxic in the powder mode, but in the liquid mode of electrolyte, it is not toxic as such to the environment. And deep discharge capacity. And remember, this is one of the most important part, which I would like to highlight, that is low risk of explosion of the batteries, flow batteries. The lithium batteries are nowadays, you can see everywhere, the fast charging and discharging, mostly EV aspects, as well as the large scale lithium and battery, because of its high energy density and the low temperature range of operations. If any irregularity in the temperature rise happens, then it goes to thermal runaway and leads to explosion later on. So if the proper monitored charge controller and thermal management is not maintained. So that is additional cost of operation as well as installation of the thermal management is required in a major cost of the lithium batteries, where this battery by some actions are having low risk of explosions. I will tell you why and how. We'll discuss about it. See, this is the schematic I would like to show. Many of you might know, many of you might not know. For you, just I would like to have a highlight, because today's discussion is all about the battery technologies for the EVs. So you can see there's this battery, you can see the total mechanism is absolutely different from the other batteries. Two sides, we have two different tanks filled with electrolyte. And then one is the cathode, one is the anolyte side, or the cathode electrolyte and anode electrolyte. See, vanadium ions, you can see V4, V5, and V3, V2. Based on, you can see this is stack. Stack means its electrodes are there, and then there are multiple layers based on series parallel connection, and the capacity wise it can be taken. Remember, as these are independent in structure, you can see here the stack size can be regulated to regulate the power capacity of the battery whenever required. And this electrolyte can be more electrolyte volume. If we add, then it will increase for more charge discharging time, means more energy capacity. Power into time is energy. So energy capacity will be increased independently. So power energy capacity can be independently increased for this battery as and when required. And these pipelines are important to carry the electrolyte through the micro pump. There is small micro pump is there, which is the drawback we can say, because it will be the self-consumption. The pump power is consumed from the battery itself. So efficiency goes down a bit, because the lithium batteries are having efficiency of 90% around. It is having around 85% efficiency because of the pump consumption and internal losses are there. So this is the typical special battery arrangements where we'd like to highlight this portion to understand the mechanism of these flow batteries and how these are beneficial to use for long-term usage as well as the stationary applications. And this is the internal structure, or you can say how the stack looks like. You can see here from this portion you can understand that through the stack the channels electrolyte flows inside, and there's a membrane which it's a proton exchange membrane. Only plus ions it can exchange by that while charging and discharging. And you can see here it's a typical structure of the electrode, typically graphite electrode we use for the cheaper cost and the better conductivity. You can see here these serpentine sort of channels are created. It's called flow field, or the channels, where everywhere the electrolyte should carry through the body, not only as a charge transfer of the ions, but also as a heat exchanger. So the good point is that by regulating the electrolyte flow rate from this pump, we can regulate the pump by some electrical arrangements by pump controller, by suitable controller design, which we can sense the power loss and the thermal or the temperature of the battery continuously, and we can have a closed loop control, and we can use the module we can modulate the flow rate of the electrolyte, and we can not only regulate the charge transfer capacity, but also we can regulate the temperature, because the electrolyte flow acts as a heat exchanger from the stack to the tank. You can see from the stack to the tank. This is the flow of the electrolyte, which the heat generated inside, I square RT, the heat generated inside, also the chemical reaction, not only the electrical losses, but also chemical reaction generates the heat. That heat is carried outside, which lithium-ion battery does not have this provision. So we have to have external thermal management system and also proper sensor arrangements, which we do not need for this battery. So the cost of the management and maintenance is quite less compared to the lithium batteries in the long run. But for the capital cost initially of the vanadium itself is a rare material, so definitely there is a scarcity of the limitation of the natural resources. So that's why the cost is still high. But remember, for the long-term usage, it is worth investing money in the flow batteries compared to lithium batteries. And you can see here this for the sustainable e-mobility. If we talk about the electric transportation, the challenges and possible solutions. If we talk about here, just a moment. Hello. Yes. Have one. Really? Okay. Am I audible now? Just
Yes,
now,
sir.
let me stop sharing.
Yes, sir, you are
Okay,
audible.
but
Yes, sir, you are
okay,
audible.
but organizer actually told me that I am on a hold. That's why I was thinking. Okay. Yeah, maybe internet connection at some time, at some point it is there. Okay. I think Dr. Shampa, I think you asked me to change to hold on. Is it fine now?
Yes, sir. Absolutely fine, sir.
Okay, but no, I mean, she has told that it is on hold. That's why I got stopped. Okay, anyway, it's fine. Let us continue. So in the challenges and
continue, sir.
implementation of, okay, yeah, please. So the challenges you can see for the lithium battery specifically, if we talk about on field, that is the stringent charging and discharging characteristic, if we talk about, then you can see undergoes the thermal runaway and explosion, as I told just now. I won't repeat the same thing. Due to rapid temperature rise inside the battery stack during irregular charge and discharge. So although the cost of lithium battery is getting reduced, yet costly auxiliary circuitry, as I told just now, and support means thermal management as well as the charge controller, stringent charging algorithm is still required to ensure proper charging and thermal protection, and which leads to the battery management system. This is the key factor which we have to think of now in the current area of research, BMS. An additional cooling mechanism is a must for the lithium batteries under operations. So this is the typical temperature curve of the power limit versus temperature for the lithium batteries. Now come to the more technical part here. Let's say 15 to 35 degrees Celsius, this band is a safer band of operations for lithium ion batteries. We are most likely to operate in between these regions. But remember, while faster charging and discharging, we are also talking about to save our time as well as the efficiency improvement of the chargers. So we need to operate somewhere where the temperature is most likely to go up 35 degrees Celsius, above quite quickly for a higher charge discharge rate. That time the battery starts degrading, and also there you can see that degradation range is here, and the lower temperature, mostly say let's say in ambient temperature which is sub-zero or say 5 or 10 degrees Celsius, we need to push some hot air through it or the liquid to adjust the temperature within this range, which is a safer range, desired working temperature. And it will be sluggish electrochemistry if it goes below this temperature, and if it is above this temperature, it goes for the limited power to reduce the temperature inside the battery degradation. That means the battery capacity can be restricted. We should have to be restricted if we go beyond this temperature level. That means which is not desirable, these two cases. So we are always go for the range of this 15 to 35 degrees Celsius. In this range we should operate, but to do that we always need to have a continuous monitoring and control system of thermal management. Of course, there are multiple cases. We will talk about it in this upcoming slides, that how the air cooling and liquid cooling can help in different applications of based on the intensity of the temperature rise, how quickly it is going to the peak, and we have to bring it down to the healthy conditions of operations. See, thermal sensitivity, to do that, you can see before this one, to understand, we have simulated at our lab in console. There is a multi-physics software, many of you might be knowing here, which is used for different modeling of the battery and any kind of multi-physics devices. So battery is basically the battery chemistry we are importing, and then based on different capacity or specification wise batteries we model in console and we studied. So one such study is here as a thermal behavior study, which we would like to share. You can see here there's a local hotspot. The red is a hotspot. You can see the temperature rise from the blue towards the yellow towards the red. Means from 32 to 52 around temperature at the center. It's the hottest spot of the battery, which should not be continued for longer time. We have to extract the heat outside or somehow, so that battery comes under the limit. Now you can see here temperature rise at 2C, means 2C rate. As I told you, the C rate last time, the C is the capacity of the battery in ampere hour. Let's say 100 Ah battery for an electric vehicle. We have to have a 200 ampere of discharge or charge. If that is the rate, you can see the black one temperature goes quickly, and of course reaches, and if we talk about after some time, if we continue with this without controlling the thermal aspects, then it will reach beyond the 40 degrees Celsius, which will further reach again 50 degrees Celsius. So it will be using, lead to explosion after a couple of operations with unregulated temperature control. And then 1C and 0.5C, the three different cases we have done here on the battery modeling side, and we understood that See, it is recommended to have within the limit of 35 degrees Celsius, but at the cost of very slow discharge, which is not recommended, or very slow charge. So this is important. So we need to have faster charging, faster discharging with the wave of the world goes, and at the same time need to take care of the temperature of the battery. So you can see here one of such work. You can see here the air cooling of the battery. It's a schematic of the air cooling. You can see here in the battery stack, let's say these are the battery cells are riveted together to make a stack. It's a battery stack. And then cooling passages are created where we can through a blower or a cool air we are passing through, or the ambient air, whichever is cooler. And through the channels we are putting it. And as a result, the hot air is taking outside. So it's a circulation of the air from the in to out, so that the heat is exhausted by the forced air cooling. Natural air cooling is not always possible to achieve the cooling for a higher level of charging discharging. If it is even more prone to the temperature rise, means for even higher, say temperature sensitive applications, where like electric vehicle, it is of course human operations, human intervention oriented, and of course there are multiple cases protections we should take, not only electrical side but also thermal side. One such case is liquid cooling, where it is even more prone to the temperature rise or the explosion. What we do, you can see here that this is a battery module, let's say battery stack, or a battery pack, you can say. And then there is a radiator or fan assembly system. There is a coolant pump. So from the cooling channels from some reservoir or source, we are having the circulation of the cold air through the channels. You can see here the even better opportunity to see the console modeling which you have done in the 3D modeling. You can see here the channels here. You can see here it is not a straight here to here. It is basically rather the pattern of the grooving of the channels are there in the battery cell, so that the cold air or the liquid passes through. Most of the liquid cases we are talking about as a this tubular channels we are creating. It's a micro channels or the even lesser channels are created based on the battery capacity and the sensitivity of the applications. Why it is so? Because it is trying to extract the maximum heat inside the battery to the outside. That's why the coverage area is more if we do this kind of channels through the battery pack. That's why intentionally we do this coverage area and the design like that. So here you can see one more technique for the battery cooling or the thermal management system, where it is even more prone to the explosion and the emergency application in defense and other applications where we need the stringent temperature rise limit of the batteries. That is done in the immersion based cooling, means where the battery itself is kept in a reservoir filled with liquid or water. Of course, a non-metallic sheet is allowed here because of the protection, so that the water does not get inside the battery. Short circuit and other issues will happen otherwise. And there is a cooling chamber also, from where we are extracting through the micro pump, and the air we are passing through it. Sorry, the liquid we are passing through it, and basically it is cooling the battery and taking the heat outside of the battery body, and then comes back to the reservoir. And again, it is processed by the radiator is cooling the this reservoir liquid, and again it is circulated. So this is the point where we can think of the immersion based cooling mechanisms are very useful for the high temperature rise cases where there is fast charging and dischargings are involved. These are the mechanism of the cooling of the thermal aspects. Now, the result we can talk about, one of such our work. You can see long back we have done in almost 5 years back. You can see here the uncontrolled temperature, where we are not using any controller or any kind of air or liquid or immersion based cooling. For the same, let's say 2C rate of maximum thing we can taken. We have taken actually that instance of 52 degrees Celsius under uncontrolled thing. If you talk about this one, if you remember this black one we are talking about, and here this air cooling, liquid cooling, and the liquid immersion, you can see we are having majorly within the 35 degrees Celsius. Now remember, based on the battery capacity and the scalability of the battery, how much of important applications we are handling with, how much of delicate application we are handling with, is important to understand that what kind of topologies are required for the what applications of the battery cooling. So these are the thermal aspects of the batteries. And now come to the electrical aspect of the battery, which is also important. Just for a check, I hope I am audible, right? And also things are visible.
Yes, sir. Everything is okay.
Yeah, okay. Thank you so much. Let me continue. Yeah, so now you can see here this is a typical charging profile of a lithium batteries. Why we are talking about the charging profile? Because mostly if we talk about renewable energy integrations or the say faster charging operations, there are ways to go for the faster charging, but the problem is fast charging we cannot always, throughout the process of charging we cannot, or recommended not to allow, because initially when the green line is a battery voltage line and the dotted line is the battery current, and this is the voltage current axis, this is the time axis. Nowadays there are multiple other charging profiles also. I won't go to that because in a single presentation is not possible to everything, because charging topology itself is a research area. So what I would like to see that there are multiple 5-6 stages of charging, pulse charging, multiple charging processes are there. But you can see here different algorithms are there involved in it. But to have a look at it, initially there is a soft charging. It is somewhat like a call it also trickle charging initially, or soft charging, where you can say initially we let the voltage go up to a certain level. Let's say for a 4.2 volts or 4.1 volts is the maximum voltage per cell. It's a single cell I'm talking about. So 3.1 or 3.3 volts around, we are first moving up to a certain level. Then there comes the bulk charging phase, where you can push the maximum current possible in this phase to make it a faster charging, because voltage will raise up quickly. And again, there is somewhat about the equalizing charging also. And finally, once the open circuit voltage or the overcharge limit of the battery voltage comes here, then we maintain into float mode and we maintain the battery voltage across it, so that the current goes down, quite natural because the battery voltage is increasing inside and we are maintaining a constant voltage at the terminal. So definitely the current will go down based on our basic law. So we can see that the current will go down and it will reach towards zero. Of course, not zero, ideally zero, practically very small current in milliampere or ampere range. If we think of that is up to the consumer, that where to cut off the charging, and we can ensure that it's a maximum possible charging is done. So that is a typical charging profile of, it's called a constant current, constant voltage charging. It's called a CCCV charging, where you can see constant current here. Here also constant current. Here also it's a constant current, but being the nominal range, we are having this pattern. It's actually theoretically it's a constant. Practically we are not maintaining that. Within a smaller range it is varying. It's a sort of a constant average value, you can say. So up to this much you can say it's a constant current, CC charging. First half. And second is the constant voltage charging, where we are maintaining the voltage and then current is getting varied up to a certain lower level of limit. So CCCV charging is a very popular charging technique for lithium batteries and any other portable batteries. But to do that, we need charge controller design. And there are multiple cases where charge controllers are coming in the picture. There are power electronics highly involved in this area. We will not talk about the power electronics part here. That is itself is a, again, converter design and controllers is a separate, that someday we can discuss about it. But today our more focus is in the battery storage for the e-mobility. So you can see, just to talk about the battery, how the charge controller design can be decided. To know that, this is one slide which we have provided here. You can see the equivalent circuit model of a battery. It can be, let's say, lithium battery we are talking about. So primarily lithium battery is the left side is a schematic of a lithium battery. When they say positive and negative half cycle, half cell, and then a membrane, and then it's the ion exchange membrane which exchange the ions from one to another side. And you can see here how to model that electrically. That is important. We electrical engineers mostly, I guess, here. So we are here always try to model any battery storage for the electrical equivalent model, so that we can know its internal impedance. We can have an estimation in the internal impedance. Internal impedance can also be measured by electrochemically. It's called EIS, electrochemical impedance spectroscopy. And most of the cases we do not have those kind of costly devices, because those are cell level only. In a stack or a pack, battery pack, we do not have that chance to measure this kind of internal impedance. So there in simulation environment, we need to estimate its impedance. It's a combination of basically your RC. It's a resistor and the capacitor combination in a battery, because you can understand that it's as there is an ion exchange, you can understand it's a conductivity. Of course, it's impacted by its internal resistance of the material. So the electrode offers some resistance. Electrolyte also offers some resistance while passing through the ions. And between the electrodes, there is it's a charged plate. So a capacitor is formed in between the electrodes, as well as electrolyte medium. So in these two cases, if you can see the arrows, the pointer, you can see either capacitor can form here and also the entire between the two electrode plates. So there it's called a double layer capacitor, because CDL, you can see it's a double layer capacitor. Why? Because it's a electrolyte interface. It also forms. This is actually a model of a battery which you have thought of, and it's a you can say model means equivalent model, of course, not exact model. You can have equivalent model. Remember, this all RC values are variable, not fixed values, because it depends on the chemical reaction, rate of reactions, charging, discharging rate, temperature, multiple cases. And now, if we talk about it, say the electrode side, let's say catholyte and the anodite side, electrolyte, in between there is a membrane. Membrane also is a material, so it will offer also some resistance. Rm is a membrane resistance. R0 is the series resistance, you can see, which is the electrolyte resistance. As electrolyte is everywhere, so electrically we are taking it as a series, in series with the membrane. And now, what about these two sets? If this is the, say, cathode side, this is the anode side, anolyte. So in cathode side, you can see RCT. RCT is a charge transfer resistance, typically electrode-electrolyte interface resistance, which offers a resistance while carrying the charge through electrode to electrolyte. Accumulation of the charges happens because of the to maintain the polarity during charging and discharging. And you can see here the CDL is a double layer capacitor, nothing but electrode-electrolyte, basically the interface we can talk about. That's why it's double layer. You can see here electrode and electrolyte. There is a double layer capacitor in the cathode side as well as anode side. These two are the parallel combination of the RC, which actually depends on in series combination with this R0, means R0 in the cathode side, also R0 in the anode side, and this is the membrane side. So these three are the series combinations, and along with series of the parallel combination of these two sides of the RC. So it's typically it's a combination of RC equivalent network. Now, how to do that? Deal with it. This was for a single cell. You can see half cells are there, two sides, one membrane. So it's a single cell. Now, if you talk about the battery pack, it will definitely become like nth cell, for example, in series. So this series will be bulk resistance will be taken outside as a series resistance component, and from the first cell to the nth cell there is a combination of this anode and the cathode side, parallel combination of the RC. This is important. So this is called Randall's equivalent circuit of the electrochemical energy storage. And you can see here, while you can see the current direction, while I stack or the I battery pack, you can say, or the stack, multiple number of cell can make a stack, and based on the capacity we use it. So you can understand here, the I stack goes in for the charging and discharging for the outside, I mean going outside from in to out and out to in, direction varies. And remember here, the terminal voltage is ET. What happens here? You can see here, this is the shunt branches. As we told, that is a electrical equivalent model. So electrical engineers, we think about how does it look like, internal losses and the drops, how it can look like. So internal voltage drop is of course there. You can see these impedance path it has to overcome, and then only the voltage. OCV is the open circuit voltage, which is nothing but the actual battery voltage developed under the open circuit condition, which is a function of state of charge, SOC, and also one more factor which is important called a self-discharge. This is also one more important part of a battery, because the batteries which are having a faster self-discharge are not recommended for longer time operations. That's why supercapacitors, although it's a very efficient energy storage, we are not using in a large scale as of now, and also the longer applications time where we do not use the supercapacitor yet. We are using supercapacitor and battery hybrid, but we are not using supercapacitor alone, because supercapacitor storage has a very faster charging discharging, that is true, but at the same time very fast or a very high rate of self-discharge potential drop. So if you charge a supercapacitor for a couple of moments, after that it will self-discharge through its impedance path, which is not recommended. And that's why it cannot hold the charge for a long time, a supercapacitor. So we do not allow for the long time applications of the energy side. And you can see here the shunt branch is basically somewhat leakage. So through the, as you remember that there's a electrolyte flow and there is leakage through different shunt path. So leakage means it's a bypass. So definitely we are representing this as a shunt path and a current source, dependent current source. Why? Because that is basically, you can say, ultimately charge carrier. So charge flow, nothing but a current we can represent with. In addition to that, we are having a shunt resistance, which is higher. Of course, remember the resistance should be a shunt resistance to represent as a loss component, which is acting as a loss component, which you do not get back, which is acting as a leakage loss of the battery electrolyte. So there are a couple of notations which are already mentioned earlier. This is basically an equivalent circuit model of a battery pack of n number of cells. Now if you talk about the, I hope it's important for you to understand that, let's say one example of 150Ah we have simulated in the lab in our simulator as well as the experimental work, where the 150 ampere hour is the EV battery with 1.6 volt per cell. If we talk about it, it's a small old battery of say, you can say lithium and lead acid battery, and also the flow battery also can be tested. You can see here the cell terminal voltage and the time of hours of use. Let's say 6 hours of operation we have used for the charging and discharging. 5 hours around it was discharged based on the rate of discharge. And ABC, you can see both cases are there, where ABC are nothing but you can talk about, let's say, this is basically blue and the red, this B and C are the experimental one and simulation with self-discharge. As I discussed about, the self-discharge in this circuit is contributing to the voltage developed in the battery. So this self-discharge, actually, if you do not consider in the model, that is why the model is important to be accurate enough. Because in the RC equivalent model, many places, many papers you will find, but typically the comprehensive models are recommended to go nearby the actual response. You can see here, if you do not use, say, the number A for both charging and discharging, what happens if you do not use this self-discharge model here in the say battery parameters, then what happens here? It will lead to, you can see here, because of the voltage, which is always self-discharge happens after some operations. If we put it idle condition, we actually kept this battery in idle condition for 40 hours of operations and then again started. So we understood that instead of a 1.4 theoretical voltage, which starts from here per cell and reaches up to 1.6 is the maximum cell voltage of a battery. But instead of that, we would say self-discharge. In reality, it starts with 1.3. So almost a 90 millivolt of drop is there per cell. So it will lead to, it looks like a millivolt, but even it's a packed in a kilowatt scale battery for EVs and all, definitely it will lead to a couple of volts, which will be a mismatch in the charge controller algorithm, because it is prepared for, if the model is not correct, actually, it is prepared for this voltage to start with, but actually here it will start with. So automatically the quicker higher voltage or the cutoff region will reach. Whereas in the actual region, the voltage is still here. That means the charging will be incomplete. The battery charge controller will be stopping the charge. So in reality, it should be here. So the moment we are having the self-discharge property in the model, it will be more accurate towards the experimental work. And here also in the discharging side, you can see the moment we are not using the self-discharge property in the battery, in the model, what will happen? It will start from a higher voltage here, quite natural. By the time it will be lowering down. And of course, it will take a less time to discharge compared to the other one. You can see here, let's say 4 point some hours, it will be discharged as per the load connected in reality. And the model helps us to also match with the experimental result. So the algorithm will run properly. If in case we have not considered that, so as per this time, the voltage is still here. That means our charge controller, the discharge path or the circuit will not be cut off. If the algorithm is based on this inaccurate model, that means it will still continue to do it. And as a result, the actual battery voltage will come even down. So which is not recommended. Deep discharge repetitively is not recommended for lithium-ion batteries. If it is lithium batteries, it is a problem. So it will lead to a short circuit of the aging and also heat generation unnecessarily in the battery side, which the thermal management is not prepared for, because that is also based on some profiles is designed, cooling arrangement also prefixed while designing the battery. We cannot regulate those designs in between operations. So those are important aspects to be understood in battery modeling and battery research for electric vehicle aspects. Model should be having comprehensive enough. All possible features, how much you can incorporate in the model, you have to make it more complex. Otherwise, it won't be near to the actual one. So this is the target actually why we are talking about this modeling. This is the model, let's say, which you have for the battery. Let's say Z is the impedance, RC values here we know. And from the solar, let us say for any renewable, it's just an example I'm taking as a solar. It can be any kind of, let's say, renewable source or any grid charging also with a rectifier for a grid, and for a solar, it's also a charge controller. It has an impedance because charge controller means it's nothing but a power converters along with some filters. And here, see the inverter side, if you want to push the power to the grid, because nowadays you must be knowing the terminology, vehicle to grid, grid to vehicle. Those factors are also there for charge balancing and load balancing, voltage shaving, those different cases are there. And in these cases, the Z impedance, if it is not known by proper modeling, then we cannot match the source side and the load side. That means maximum power we cannot transfer. our electrical engineering basic knowledge, that the impedance matching is very, very important. For that, we need to know the equivalent circular model of the batteries. Otherwise, we could have directly operated it. So these nonlinear models, there are multiple complex models are there in the literature, which leads to the accurate model of the batteries. In RC equivalent, of course, that there are nonlinearities to be introduced, thinking of the real issues in the battery, so that it is almost matched with the, accordingly the design can be done in the converter side also to match the switching impedance of the charge controller as well as inverter to match the battery impedance. That is interesting for the power transfer capability. Moving on to the battery management, because we have done the thermal as well as the electrical side. Battery management system is an important part to understand. See, I have discussed here so far different aspects of the electrical as well as the thermal. Here, battery pack and the BMS. What else is there? Let's say battery pack is here, and external circuitry. Advanced BMS includes the safety, the precise state of charge prediction, state of health prediction, time remaining, means remaining useful life of the battery, and battery cell balancing. This is very interesting for the ongoing operations. It has to be, because all the cells might not be charged or discharged in the same manner in a battery pack. So cell to cell analysis is very important. To have a rebalancing or the charge cell balancing is important. Active balancing, passive balancing, different methods are there. Because here it's a FDP, so we are not here to take the entire class, a smaller topic in a long time, but rather to have a exposure to you who are interested, they can get back to us later on. So you can understand here the converter electronics is the most important part. The converter electronics is basically the interface part which actually connects the source and the load to the battery storage. And then we have the measurements. This is important, the SCADA system, the supervisory control and data acquisition system, which actually monitors the entire battery parameters in real time and then take actions based on the cooling aspects or charging aspects or the flow control aspect for the flow batteries. So different aspects are to be maintained in a BMS, and which will finally lead to the safety of operations, longer cycle life, and the accurate state of charge estimation. The charge controller should not be overcharged, should not be undercharged, should be the balancing of the cell, and remaining useful life has to be very important to predict. Nowadays, different machine learning and AI techniques are also being adopted in the BMS topologies in the literature. So here, to talk about, summarize if we want to do that, the pillars, this itself is a research areas individually you can talk about. State of charge estimation, there are multiple areas and algorithms to estimate the SOC, and which will lead to the accurate battery charging and discharging. Also the health and operations. Dynamic internal impedance. Internal impedance is dynamic. Why? Because it depends on the rate of reactions inside the battery based on the faster charging or discharging rate and the slower charging discharging rates. So internal impedance is very important to estimate. Otherwise, you cannot bridge with the external circuit to maximize the power transfer, as well as the battery aging. Aging is also an important aspect, as with age of the battery from newer to older, the battery internal impedance gets higher. So more drop is also associated with it, more losses, more heat. So automatically the capacity decay happens of the battery to hold the charge for longer time because of the internal drop. And the battery temperature controller is also important, as I told about, especially in lithium batteries or other compact energy storages. And self-discharge rate is one more interesting feature which is required to be incorporated in the BMS. These are the major 4 pillars. And in addition to that, automation is important. Real-time communication, SCADA system, IoT-based systems are also coming into a big way in this kind of battery management technologies. So this is one such application I would like to share with you some of the basic research now, because it's a sustainable e-mobility. So batteries alone cannot contribute everywhere. We have to have a battery fuel cell hybrid system. See, it's a 4-wheeler vehicle. Let's say, for example, a traction motor we are using to drive the motor. We need power supplies, which batteries are primarily, if we talk about in BEVs, battery electric vehicles, but the moment it is a fuel cell battery vehicles, the fuel cell is a major power source. And then for the steady load to operate and measure, and the transients, because battery has a unique feature of the very high or faster response in operations compared to fuel cell. So fuel cell are used for the steady operations when the battery and when the drive cycle is steady. The moment there are some more transients in the picture, which needs very fast millisecond to few seconds of transitions, there we need battery storage to operate, and fuel cell battery can be a very good choice of hybrid energy source for the electric vehicles. So EMS is the energy management strategy. You can bidirectional control and the communication signals we are having to real-time monitor the battery operations and fuel cell operations, and then optimize the power sharing between the battery and the fuel cell to meet the required drive cycle load demand. This is one such results, couple of results we are showing from one of the recently published paper in our with my PhD scholar. That is the real time we have the experimental setup and the simulator as well. We have the vehicle speed, let's say the red one is of course superimposed, quite natural, and the simulated vehicle speed is here. We have simulated that vehicle speed, and the power requirement is somewhat here. You can see here, this is somewhat like a stall mode, or it's a traffic jam, or somewhere we have emulated in the profile, so that in a regular drive cycle, this is the drive cycle of the vehicle power demand, the drive cycle vehicle power demand, and somewhere we are having negative power also. Regenerative actions are taking place. And you can see here, this is the vehicle in traffic where there is no exchange of power from the battery to the drives. And you can see here, this is a real profile actually we have taken from to simulate and to manage our energy. We have proposed this EMS, a rule-based energy management topology. We are not talking about that here because energy management is a separate application and separate research area. Here in this lecture, it is not there that much. So the sharing, you can understand that the fuel cell and the battery power is to be shared, while you can see this red one is the vehicle power demand, as I told you, that the fuel cell FCS is the fuel cell power, the green one, and the blue is the battery power. You can see here the continuous chattering in the power sharing of the vehicle and the battery and the fuel cell happens, but majorly the fuel cell is contributing the steady power compared to steady. I'm not talking about this constant, but the requirement is more majorly managed by fuel cell, and the batteries are whenever required. The fuel cell is not in a position to have a faster change of responses. Those cases we need battery, and also important part, battery can get a charging also at some times in the vehicle operation. If you remember that, if you know that about different regenerative braking actions are taken place, that time battery goes to charging mode. The negative power shows the charging mode of the battery, and the positive is the discharging to the drive. So this is one cases. If you go more detail, if you want to know about the energy management that we have applied here, and you can go to this paper and read that later on. And so here now, so far what we have done is for the EV related. Now somewhat let me talk about some portion where I think running behind time. 7:30 is the time, right? I hope what was told to me. Yes. Can I continue for a couple of minutes? Okay. Yes, sir. Okay. Okay, madam. Thank you, madam. So so that battery storage for the EV charging station, this is also important nowadays because we are talking about renewable energy powered EV charging stations as well as the stable operations, reliable storage. So we need to have the storage which is reliable and long life. There comes the flow batteries nowadays in a bigger way across the world. See, it may be in different topologies, renewable energy fed directly, or renewable energy to the grid integrated system. It's an off-grid charging station, local charging station, or a residential or any pilot charging station. This is the grid integrated large-scale charging stations, or the commercial charging stations, you can say. And where you can see battery, of course, this is you can see bidirectional, because battery can push or battery can take the power. The moment renewable energy is excess, that time battery goes to charging mode. The moment renewable energy or the other sources are major sources having a lacks the demand or the less than the demand, then battery goes for discharging mode. It's a schematic. Of course, there are multiple power converters and control topologies are involved in this kind of applications. It itself is a individual areas are a research domain. Now, this is the V2G, as I told about the grid to vehicle and vehicle to grid. The moment we are having majorly the G2V, and V2G is applied most cases where there is a vehicle is at rest or there is a sudden dip in the voltage. So for smoothing applications and power quality improvement, we can use the vehicle battery as a battery storage, as a stationary battery. When vehicle is at rest or a parking station or somewhere, we can talk about. This is one cases where the vanadium batteries or the flow battery. This is the work which I'd like to share with you, because that's the area where people can contribute in the research area, where basically the solar with the DC-DC power converters and the battery flow battery is connected here. The stack, you can see the stack. If you remember, we have discussed these things earlier. And tank we are not showing here because tank is a energy related things. The power related things is the stack for the flow battery independently. And bidirectional converter is required for importing and exporting power from the grid and to the grid. Local residential or a small commercial load is also connected to balance. It's a sort of a microgrid setup, which is somewhat, you can say, think of a EV charging station also, which is a rooftop solar powered EV charging station. Nowadays people are using. in multiple areas of a small community-based rooftop solar-based EV charging pilot charging stations. So this is one such area where maximum power point tracking, MPPT, most of you might be knowing that to extract the maximum power when there is a solar or wind, and because it has a very low efficiency of this power generation. So definitely the maximum power point tracking is required to have the available maximum power to achieve from the weather dependent sources. And of course the converter interfaces are important. Every interfaces are controlled by a processor interface, and where all the sensor data are collected, analyzed, and then fed back in real time. So this is one recent work people we have done in my research group, that is the EV charging station. What we have done, not this charging station power, thinking of the Indian scenario, we are not that much luxurious now to totally power by electric vehicle, powered by renewable energy powered EV charging station, because there are reliability issues, fast charging issues, which needs the grid intervention. We cannot avoid the grid intervention yet. So that's why it's a grid connected system for the EV charging case. But for the solar power is a rooftop solar. It's a schematic for your understanding. And there are a couple of cases where in some places we need the internal temperature, thermal comfort of the building we need, because of the complicated, say delicate control panels and instruments are inside. So in those cases we need a thermal comfort inside. So sometimes we allow the the thermal the sunlight inside, or we don't allow. So if you do not want to allow, to make the internal temperature low, say as compared to the Indian context, tropical weather climates of the countries where mostly it's a hot weather, and there we do not need, let's say in the scorching heat of the sunlight outside, we do not need the heat to go inside, so we make it opaque. So we allow some of the small smart window, means there is called glazing. It's a different topology, so it's material aspect. There's a ITO coating based specific separate glass is maintained here, where actually if we have to actuate with a smaller power supply, steady power supply, so that it becomes opaque. The moment it is not activated, it's a transparent. Now, the moment we need outside is a cold, inside there is a heat and outside there is a cold weather, then we are allowing this temperature inside and sunlight inside. But the moment we are having the outside, there's a very high temperature in the ambient, we restrict the sunlight inside by making it opaque. These glasses or the windows in different places are made opaque or transparent, switchable. It's called a switchable glazing. That's why the name is switchable electrochromic glazing window. Opaque means on state and transparent means off state. So this is the what it look like. Reality, and it's an example of transparent, off state, and on state is opaque. So we do not allow or penetration of this direct sunlight there. What is the impact on that? Who has done it? Basically, we have installed a flow battery for longer time of discharge. Say throughout the day, a steady discharge is required to actuate this switchable windows. So we have used the battery, which is solar powered, and then from there entire communication of the scheduling when grid will come in the picture when solar is not available. That time battery also state of charge has to be maintained. If it is lower state of charge, then how battery will be also contributing to the charging mode or discharging mode will be decided. Those mode changing has been done by a proper idea of the IoT based control system. We have done in our lab that smart meters we have taken from the EV charging ports, the solar inverter, the grid, and the flow batteries. And from there, the switch, we have used the Ethernet ports to interface with the processor, which is a small scale, lab scale. We have done it in Raspberry Pi. And then we have taken on bidirectional communication topology, where the flow battery monitoring and control system is designed. And we have finally been able to understand that how the load, dynamic load of the switchable, these on-off states can be managed by a small current passing through from the battery storage, which is powered by a solar, instead of taking that steady power from the grid, because that is again a costly. You have to pay for it. You have to depend on the grid tariff scenario. If it is dynamic tariff, then you have to pay different pay levels, slabs. If it is a static or a fixed tariff level, then you have to also design according to that. Ultimately, you have to pay for the electricity. So this is important, that time of use and the profitable electricity usage by the green energy we can utilize. Also, we can utilize for the power supply reliability of the entire electric vehicle charging station as a conventional charging station. Here we are not showing a conventional charging station. Here we are showing a basically a separate application of the thermal comfort of the building. It can be any commercial building also, not only EV charging stations. because it's e-mobility lecture, so we are thinking of the e-mobility side. Now, the electrolyte flow control. The moment we are talking about this battery to control, this is important. Flow control is the important part, which is called a thermal management and the life efficiency improvement. How it is done? As you remember that if you think of the earlier cases, see, this is one block diagram. Let us not make it more complicated. Maybe I can see here, you can see the tank and the stack. Remember, as I told you that earlier, that this pump is having a continuous flow of electrolyte. So we can control the pump to control the electrolyte flow rate. Nothing but it will control the temperature as well as the charge carrier rate for faster or slower charging. You can see here the flow battery or the VRFB or the vanadium redox battery pump. This pump is, say, one pump we are showing here. This is the pump here. You can say two pumps are there for the two sides. Let us talk about the one pump only, just for the simplicity. And then the stack, it goes to the electrolyte flow rate. Now, from the stack, we are maintaining, managing to calculate the stack power loss inside, I square R, charging and discharging. R is the internal impedance. You see how important the equivalent circuit is. Electrical equivalent modeling of battery is so important because this R is nothing but the internal resistance. It keeps on varying with the charging and discharging rate as well as state of charge. So this is important. This I square R is a loss. And then this is also noted in a database. And then flow rate versus pump power, because as we remember that we have discussed that pump itself takes the power from the battery body. That means the self power consumption. So as the regulated pump speed is there, definitely power also consumption will be different. As a result, the power profile also, the losses of the self consumption is also one factor which has to be maintained in the efficiency calculations. And you can see the flow meter. It is important, the flow rate. That means here you can see the stack temperature is sensed by a temperature sensor, and then with respect to the reference temperature, if you remember that for a lithium battery, it is 15 to 35 degrees Celsius. If you remember the safe temperature operation range, for the flow batteries, it is a exposed structure, not a compact design. That's why it has a drawback of low energy density, but it is good for the long life storage. But it has the advantage of, it has the mode operating temperature range 5 to 40 degrees Celsius. So here you can see here the basic controller you have to design, and which will take these all inputs and finally take a decision. The signal will go to the variable frequency drive to drive the pump. Here we are using an AC pump. It's basically a schematic of an experimental setup that we're not showing here because of the project copyright issues, but the schematic there's no problem of showing that. So V by F control we have done, basically a flux control of the AC machines. So it's a induction based single phase induction pump we had, and then can also be as a DC pump. If you can use, then definitely this VFD can be removed, but it has some complexity. So we have done the AC pump in our usage. Now you can see the flow control. Look at this. The red one is having basically the uncontrolled or the constant flow rate, and this black one is the controllable or the dynamic flow rate. As I told you that based on the temperature changes or the charges changes, charging and discharging changes, we keep on changing the flow rate. That is the only controller here which is the best part of this battery, because you do not need external additional thermal management system, unlike lithium batteries. So you can see here the state of charge 90% can be managed, but within the range of 40 degrees Celsius. Whether this uncontrolled or a fixed flow rate, if you do not control it, or it's the open loop control if it is, then the problem will be around 60% of the state of charge, 0.6 here somewhat, it is reaching the 40 degrees Celsius. Because of thermal shutdown of the battery protector or protection circuit, it will close. It will shut down the system. So it will stop the discharging or the charging. That means the charging is incomplete. Not only the temperature rise up to a certain level and going beyond to battery degradation it will lead to, and also the thermal management is not maintained because of irregular discharging and charging rate. So automatically, because of protection, if you want to do a protection for the on field, then you have to stop it somewhere which is incomplete. You can see the capacity is not utilized fully, whereas you can utilize the full capacity of the battery under dynamic flow rate conditions. And this is the loss of the calculation, where you can also optimize. You can see some of the optimization techniques we have used here. We are not talking about optimization algorithms here because that's not the topic of discussion here. But some optimization technique we have used for the overall flow battery power loss optimization. You can see the green one is a profit line. For your understanding, I have proven. So you can see a 3 liter per minute, 6 liter per minute, and 12 liter per minute, and 18 liter per minute. For the, it's basically for a 6 kilowatt hour. battery setup that we have in the lab, pilot scale. Of course, in reality, in commercialization of the flow battery, it is even higher, 50 kilowatt hour, 100 kilowatt hour is the batteries. But for a pilot project, we have done it through one of my funded project of the DST. They have funded for testing this kind of battery at lab, and its performance of different EV applications, charging station and other power system applications of the renewable energy. So this is, you can see, for for all the cases of the state of charge, we have understood that it's quite natural that maximum flow rate if we allow, battery cooling can be easily achieved, but at the cost of power loss. And also minimum flow rate if you allow, then battery cooling might not be achieved, but at the cost of low power loss. Means efficiency will be higher. So none of them are recommended actually. In between them, somewhere we have to move around as an optimal point. So that optimal flow rate is important to understand that how the optimization of the flow rate can be done to make a proper battery management system. These all are a part of the BMS, battery management system for stationary batteries. So you can see here at the summary, moving on to the last portion. I think we are almost nearby the time. And then if we now, in a nutshell, if we want to check the battery storage is a key area of the focusing for the sustainable development goals, which is also e-mobility is one of the major part of the sustainable development goals. And emphasizing on government policies on EVs and growth of the renewable energy applications, countries like India are heading towards large-scale indigenous battery storage manufacturing plants. It's a message to the people who might be doing some battery research. And the suitable long life and scalable battery storage like redox flow batteries should be more important in the EV charging station as well as other stationary renewable applications here. And intelligent battery management system, that is also majorly we electrical engineers can look into it. Multiple cases, BMS, right from the smaller to medium to large scale battery management system is protection, thermal side and electrical side has to be taken care of. For that we need modeling. We need the controller design, we need the communication systems, we need the sensor arrangements and coordinations. So entirely it will make a battery management system, which is the need of the hour to lengthen the battery life and improve the storage capacity, reliability, and optimize the electrical interface is the last part, which has to be optimized because the efficiency and other interfacing maximize the power transfer from the solar, from the source or the load side to the battery for different EV applications as well as the EV charging applications. The optimized integration means power electronic converters have to be given emphasis and energy storage for improving the system performance. These are the major parts which we thought of in a nutshell to discuss with you. I think that's all from my side. Thank you so much. And the message is go green. We should go towards the greener energy in future. And I have also given my contact email ID. If you are interested to know some more or collaborate in future, we can definitely come together and join hands. Thank you so much for the time. Any queries, I would be happy to address as much as I can. Thank you. Am I audible now?
Yes, sir.
Yes, sir. Yes, sir.
Yeah. Okay. Yeah. Okay. So, any queries from the audience side, if it is possible?
Sir, I have a question. Am I audible?
Yes, please. Yeah, please.
You have used one term, deep discharge capacity. From the layman's point of view, I want to know what is deep discharge capacity.
Yes. So, see, as a point of view, in a nutshell or in a easy language, if I talk about, the battery capacity is manufacturer specified typically that say 10% state of charge, 20% state of charge, maximum up to 80% state of charge you can achieve or 90% state of charge you can achieve. So deep discharge is nothing but the reverse of the state of charge, as I told about. Deep discharge means, let's say, beyond 10% or beyond 5% if we allow, sometimes we need to allow. We, in fact, we daily usage we allow in mobile phones or laptops, wherever, based on emergency loads, we still go deep discharge. And if we repeatedly do that, what happens? The battery inside goes for the aging effect quicker, as well as the quicker short circuit can also occur in the battery, which will lead to high temperature rise in the battery in the next cycle of operations if we make a deep discharge of a battery. So that's not recommended. We always have a window of charging or discharging, means say typically for lithium batteries 20% to 80%, and for the EV applications or emergency applications. Still for the flow batteries or other stationary batteries, we can go for 90% to 10% range. We do not go normally beyond 90% or as overcharged limit or undercharge or the deep discharge beyond 10% limit. So that's the idea of the deep discharge capacity, which is not recommended repetitively.
Okay, thank you.
Yeah.
Thank
Anything
you.
else, please? Yeah.
So we have to conclude now because we have time limitations.
Yes.
Oh,
yes.
okay.
Correct.
As we have another session on 13, no?
Correct.
So thank you, Dr. Ankur Bhattacharya sir, for your wonderful presentation, which reflects your multidimensional wide knowledge and expertizations. Participant may have doubt or questions. As we have time limitations, you may ask your questions in session 13. Sir will deliver another lecture on AI for smart grid and storage applications on 27th September at 5 p.m. Once again, thank you, sir.
Thank you so much, madam. Thank you for hosting and then for such a nice, engaging, I guess, almost 100 plus participants is quite remarkable in FDPs and all, and even at almost 8 p.m. Yeah, thank you so much. I think we have one more presentation now. Yeah, followed by this.
Yes.
Yeah.
Yes.
Thank you so much. Yeah. Okay. Thank you. Let me log out now. Shall I log out now?
You can. You may.
Okay. Yeah.
It's
Thank you
your
so much.
wish.
Thank you. Yeah.
Okay.
Thank you so much. I log out now. Yeah. Please.
Our next speaker is Dr. Pradeep Kumar Sadhu. So before starting his lecture, I'm just briefing his biography. Dr. Pradeep Kumar Sadhu is a distinguished, welcome sir. Dr. Pradeep Kumar Sadhu is a distinguished professor in electrical engineering in ISM Dhanbad. He has completed his degrees, all the degrees, graduations, post-graduations, and PhDs from Jadavpur University's Electrical Engineering Department. He currently serves as Professor HAG and former Head of Electrical Engineering Department at the Indian Institute of Technology, the ISM Dhanbad, with 38 years of experience, 26 years in academia and 12 years in industry. He previously taught at BIT Mishra, Ranchi. Dr. Sadhu holds 30 granted patents and two are pending, and has numerous publications in prestigious journals like ITPT Transactions. He leads government funding projects, including innovation in wireless hybrid charging for electric vehicles and pacemaker battery chargers. He has guided 36 PhDs, scholars, and authored 4 textbooks, and focuses on power electronics, renewable energy, and energy efficient systems. In 2024, he was recognized as one of the world's top 2% scientists by Elsevier and Stanford University. Thank you, sir.
Welcome. So
before
presentation, I just want to share and test the multimedia. Already I have said. So Microsoft Team में share screen window.
At the top, there is share.
I know.
Is there.
I know that. Just testing for Windows. Entire screen. Is not. Entire screen allow. So just check the is it visible?
Yes, sir.
So now it is visible. I just, another testing is there in the last. So is it visible over the?
Yes, sir. Visible.
It is running. Audio is coming.
Yeah.
Madam, audio is
Yes,
coming.
sir, it is visible and audible
Okay.
also.
Okay. Okay.
Yes.
Thank you. Am I audible, madam?
Yes, sir.
So
Yes, sir. You are.
Yes, sir. Let's start. Let us start. And for my habit, actually, in between the session, I shall ask the interaction, as because two way it will help, that disconnection of network. I shall get the, if you give the response, so I shall get the confirmation that network is ready. And another thing, my habit is in the class also, in the mode of interaction. If it is the interaction is not done, so it is just one way we will serve this thing, and I do not understand how much you will accumulate. Okay, please respond someone that whenever we ask this question,
Okay,
or
sir.
anything else. Okay. So we'll start this today's first session from Indian Institute of Technology, ISM Dhanbad. My heartiest thanks to the organizer for inviting me that for this ATAL FDP session. Now my topic is wireless battery charging system of electric vehicle in static as well as dynamic condition. For this part, I just select this thing, this part. Is it selected on your portal? Can you respond
Yes,
this?
Yes, sir.
For
Yes, sir.
NOx, SOx, and carbon management. Basically, the today's for green environment, this part is there, and this work is going towards the direction of green environment. And this wireless battery charging system for electric vehicle in static as well as the dynamic condition. And in my topic, in respect of my session, it has been written the contact and contactless charging. Basically, we'll discuss, we'll start with contact charging, but the contact power transfer, basically it is contact power transfer. So if we start with that, and later we will transform it to the wireless power transfer system. So we will later, after the session, I shall share this slide materials to for the participants, to the coordinator, and he will just circulate this. So here, basically this, I want to see this from this knowledge that real education is that which enables one to stand on one's own leg. Basically, Swami Vivekananda has said the right word. If you technology, okay, it is, if you do not know that anything else, it will be a magic, like PC Sorkar, whatever the great magician it is. But magic is not magic. Magic, in behind the magic, there is the knowledge of technology as well as science. So basically, wireless power transfer, this is your main domain, where the wireless power transfer system, in the short form, it is WPT, or CPT, contactless power transfer. So this is like a 50 years back, 60 years back, then also that it is a magic, just like this in a auditorium. PC Sorkar is showing that one lamp is glowing over the air. So this thing is not magic, it is basically the technology. So let us start this with the contact charging, contact power transfer, and what is the difference between the wireless power transfer system. So go through this some few slides for the introduction, that understanding of NOx, SOx, carbon management of car, basically the 0.2 grams of NOx per mile. It is gasoline or petrol will generate from the each car, and older models emitted the significantly high. And carbon dioxide, it is basically 2.3 kilograms of CO2. Burning of 1 liter of petrol, it will produce this type of carbon dioxide. So this from the vehicular section, actually I am dealing with the e-vehicle, and the e-vehicle has so many subtopics are there. One important topic is charging, and charging is the bottleneck. That in the market, whatever the EVs are available, that Tata Motors, then the Tata Motors Nexon, then Mahindra, this type of all the car makers, even also Maruti has started the e-vehicle. And this e-vehicle is the only solution to reduce this NOx, SOx, CO2 in the environment. But the thing, is it true? Just whatever we are giving the lecture easily, or in the case of diesel, the SOx, whatever the particulate matter that will emit from the diesel engine, it is coming from the small car to railway diesel engine, 4,500 HP diesel engine, or maybe the 6,000 HP SEEP engine. So all are diesel engine. So it will emit the particulate matters as well as the NOx, SOx. But the thing is, in case of why the particulate matter is, anyone can respond that what is PM, particulate matter? Is it a combination of any chemical, or anyone can respond this, that in case of this all the particles, basically their PM, it is a product of unburnt fuel, is it not? Anyone, do you know this thing? And in your mind, that why sir is asking this type of thing in the charging system? Actually, if you want to replace the diesel engine, IC engine, petrol engine, so only is the electric vehicle. Is it correct? Anyone? Anyone from the audience? Please respond.
Yes, sir.
Please respond as early as possible, as because the network is ready or not, or fail, I have to explain. So here this thing, the particulate matter is nothing but it is an unburnt fuel, and it is a carbon particles. So this thing, all the things can be controlled by means of EV, electric vehicle. So electric vehicle will not generate any pollutant. Is it like that? Anyone can respond from the audience?
Sir.
Electric vehicle, 1 minute for, I take this opportunity for this mute, please. so already we have discussed that issue for the e-vehicle. Will it be pollutant free? It will not produce any pollutant. Anyone from this audience? Anyone?
Pardon, sir. What is the question?
My question is, e-vehicle is the solution whenever you replace the IC engine, diesel engine with electric vehicle, then electric vehicle, basically it will not produce any SOx, NOx, carbon dioxide. But is it true that electric vehicle will not produce any pollutant for the...
No, sir.
That is my question. Please.
Sir, the disposal of battery is also a very challenging task in the coming future, sir.
Okay. That is also under the battery waste management. Any other else? Actually, I want to share you, I want to focus that e-vehicle also for charging, if you take the electrical power from renewable energy, then it is green power driven. But if you take this from the grid, actually in the grid, thermal power station power supply is there, and from the thermal power station, whenever you take, show that carbon emission is there, carbon dioxide emission is there. So
Yes,
it
sir.
is
Yes,
not
sir.
zero emission. Actually, what is the advantage? That in a bigger way, whenever you will produce the electrical energy from thermal power station, so in the thermal power station, you can regulate, you can filter somewhat in the level for the carbon dioxide emission. But in a small car or small diesel engine driven car, small that IC engine driven car, there you can regulate this thing. So e-vehicle can solve this problem, but if it is green power driven like Denmark, so it is okay, 100% power if it is taken from the green power, so it is solved. Otherwise, the some pollution, it is a secondary pollution, will come from the thermal power station whenever the grid power is utilized for charging. So this part is there. Now if you impact over this, these are the unburned fuel from the car. Is it visible from your portal?
Yes, sir.
Yes, sir.
So it is similar. Nowadays, it is a luxurious train is available, a palace on wheels. It is Delhi to Jaipur. That train is taking the foreign tourist passengers and ticket is under the $1. But the thing is, the coal engine driven that train are not shown here. In our student life, we have seen this thing. So how much pollutant, how much carbon dioxide emissions are there. So this part is there, but our topic will start from here. Basically the diesel engine, whatever the diesel engine you have taken for the goods vehicle or for passengers vehicle, but diesel engine will produce the particulate matter. In place of this diesel engine, basically this diesel engine have the CO engine. The C stands for ABC. That is the position of C is third position. So 3 wheels rear and 3 wheels are in front, and each wheels are driven by the 750 HP engine, the motor. And that will be the diesel engine will produce. This is the diesel engine will be utilized for the prime mover, and that generator will drive. But the thing is, to solve this problem, the contact power transfer. Basically, this is the contact power transfer for Indian Railways or tramways or the electric brass in the Nepal, that Bhakpur to your Kathmandu, 15-kilometer distance. It is traveled by electric trolley bus, and that is also contact power transfer. So from here, I have to transfer the knowledge. Basically, it is contact power transfer from the pantograph. It will take the power from the catenary. And this contact transfer, what is the coupling? It will start the system for wireless charging system or wireless power transfer. That is basically here the by pantograph, whenever it will take the power. So what is the coupling coefficient in this? Any participants can give this the question answer. Anyone? That whenever from the catenary through the pantograph, it will take the power. And what is the coupling coefficient? Anyone? Coupling coefficient is actually utilized in the transformer. Is it not? Whenever it will transfer the power from the primary to secondary, the coupling coefficient are very, very important there. Here also coupling coefficient is there. What is the value of coupling coefficient in the traction wire to pantograph? Anyone? Anyone please respond? Otherwise, I shall give the answer. Anyone in the audience? Please respond. Hello. Hello. Hello.
Yes, sir. Hello, sir.
Actually, I do not know that the network is working or not. That's why in between that I have asked some question. Please give the response, otherwise it will be delayed. For the coupling coefficient for power transfer from the contact wire, basically I have one topic for contact charging and contactless charging. Contactless charging is much more difficult area. So we'll discuss about this. In the case of electric train, it will take the power from the catenary. So at that time, what is the coupling coefficient of the power transfer? That is my question. Anyone?
No idea, sir. Hello, sir. Hello. Hello. maybe network issues. So just we will wait some time.
Madam, একটু personal
Hello,
contact.
sir.
Okay, there is some network issue
Maybe.
from sir's end.
Maybe. Just wait.
So, am I audible now?
Yes, sir.
That's why I am asking always that the response, please, you will give the response for every question. Then two benefit. One benefit for connection. So you will just but sharing organizer presenters, you have to give the share options. Yes.
So now you are visible, sir.
So that's why I am.
You are visible.
Please, someone, madam, you will engage that for giving the response from the candidate. Maybe written response are giving in the other window. I have opened the materials, so that's why I have to check that second window. So it is very difficult. Please, someone responds that it is working or not. Okay.
Okay, sir. Okay, sir.
Otherwise, it will be very difficult to. Okay. So here I have lived actually from this topic that coupling coefficient of contact power transfer. Coupling coefficient through pantograph from the catenary to pantograph, whatever the power is delivered for this delivery of power, contact delivery, what is the coupling coefficient? Anyone from this audience? Anyone? Please respond.
Oh, no idea, sir.
No idea. Okay. Thank you for your response. Actually, the coupling coefficient, you will get this idea from the transformer in the basic electrical engineering or electrical machines. If it is a primary and secondary is isolated transformer, so there the coupling coefficient, what is the coupling coefficient that near about 0.85, 0.9, that tightly coupled primary and the secondary, in between that flux will carry. That means flux will be generated from the transmitter coil and it will cut the secondary coil, and flux will actually transmitted through the core materials, magnetic materials. So it is tightly coupled. So maybe 0.9, 0.8. But the thing is here, this coupling coefficient, whenever it is contact power transfer through your pantograph, that is coupling coefficient K equal to 1. Just like this coupling coefficient and the power factor, it is similar category. That means coupling coefficient band is 0 to 1, never greater than 1. In power factor also same thing, 0 to 1. And in power electronics, another domain, that is your duty cycle. There the duty cycle also 0 to 1, in between that. So that is the main custody of power coupling of power. So K value in case of contact transfer, in case of contact charging transfer, they are K equal to 1. And if it is the tightly coupled, so K equal to 0.8, 0.9. But in case of wireless power transfer, I shall show you that model from this. And there the coupling coefficient is 0.23, 0.25. This type of coupling coefficients are there. Whenever coupling coefficients are less, so efficiency also will be less. But in the case of e-vehicle, already we have discussed that e-vehicles is not so many commercialized. It is for the metropolitan city. If you go 100 kilometer or 150 kilometers, so 150 kilometer you can return back, then it is okay. But in case of charging, whenever you have the headache for long distance, just like Dhanbad to Kolkata or Kolkata to Dhanbad, your headache will start after 200 kilometer, how much distance it will cover. So continuous from the dedicated road, if the charging will be possible. You have seen in the case of electric train, Howrah to Rajdhani Express is running from Howrah to Delhi, 1600 kilometer. There is no problem. Actually, continuously transfer the power through catenary, and it is a contact power transfer. But in case of the vehicle, car, you have a need of wireless power transfer. If it is a wireless power transfer, then only possible that. Otherwise, in between the 300 kilometer, if you have a requirement of charging, so fast charging is required. That means normal charging overnight, 8 hours, it will be charged your vehicle. It is contact charging. And after that, if you have a need of roadside assistance, so you have a need of fast charging. Fast charging is within 2 hours, the battery will be charged, not 100% of SOC. State of the charge, how much in fast charging? Anyone have any idea from the audience? Hello? For normal charging, we can acquire 100% of charge.
Hello, sir.
Yes.
Sir, can I interrupt you? Sir, your
Yes.
slide, there is no slide. Actually, one trend line photographs is there. Please share your slide.
I shall come back. I shall come back. Actually, I have not changed the slide. I shall come back. But my question is to the audience that whenever it is fast charging, will come later, that this topic will become to the contact charging. Actually, the contact-less charging, it is another important area of wireless battery charging system. So there, basically whenever EV you will take or you will drive the EV, so after 200 kilometer you have a headache for charging. So roadside assistance is required, charging infrastructure is required, and there the charging infrastructure, if you want to charge up the battery for 8 hours, it will normally charge, but no one has the time to wait for 8 hours. So nowadays available facilities, there are second types of charging, which is fast charging. Fast charging means how much level of battery it will be charged up. Anyone have any idea?
Up to 80%, sir.
Up to 80%. Why not 100%? That is the question. Later we'll think about this. So here we'll apply the theme. If it is interested, then it will enter to the heart of the EVs. So heart of the EVs is actually, which is heart of the EV? Heart is basically, yes, battery. And battery is again similar to another physical apparatus. what is in the physical structure, you can compare with this thing, battery with the biological manual system, that what are the physical structure is there, which component is similar to that. Digestive system of the man or the any persons is basically the battery, is it not? That in the case of electricity, you will charge up, so you can take this out from this battery. In the case of the heart of the EVs is battery, but battery is similar to your stomach, your digestive system. Okay, so we'll see, but reverse engineering will apply in this the topic. That last topic I shall show you. Then we'll come back to the heart of the system, how it will be charged, how it will be, then otherwise the interest will be decreased. So I shall just reverse engineering means last product, like your Suzuki, Japanese car, they are making it is a reverse engineering. First it will be architect, then the architect after that making the body, the IC engine expert will come and that will fit the car. It is a reverse engineering. But the General Motors or that, it will come first the passenger capacity, first will produce the engine and then you will make up the car body. So better we'll start for the wireless charging system, which is developed for laboratory scale in IIT ISM Dhanbad by the DST fund. From this project, actually I want to show this is a government DST, Government of India, as well as the IIT ISM Dhanbad has that launched this in the YouTube. If you write down this IIT ISM wireless charging system developed by IIT ISM Dhanbad, so you will get this video and will from the multimedia we'll see this thing. So is it visible or not? Is it visible?
Sir, it is visible.
Okay, audio
Yes,
is
sir.
coming. Okay, so please respond in this way, otherwise it will be very difficult to operate this from the far end. So first you will go through this video. I shall link is in my, the 16 battery packs are there. Each battery has 12 volt. So 192 volt bus, DC bus voltage has been prepared, and this DC will be given to directly. So here I want to explain this thing, that it is not a dry cell battery or your flash gun rechargeable battery. It is the size of battery whatever we have taken for the more or less that 192 DC bus voltage SMF batteries are there. So it will take the for the wireless power charging system. Dashboard meter of this vehicle. These 2 meters are showing this. So here we will explain this thing, that this is the highway, dedicated lane of this highway for the wireless charging system for e-vehicle, and this is the first generation of e-vehicle we have constructed in the lab. Later that self-propulsion car also it has been developed, and over the highway this car whenever it will move, there is no electrical connection in between this car and road, so it will deliver 2.2 kilowatt power at a distance of 2.54 centimeter gap. The 2.54 centimeter gap means 1 inch gap. The power will be transferred. I shall show you the whole videos by step. And here the roadways have 4 units. Here the hardware simulation is that 1 meter of length. This is one module. 1 meter of length is produced, and 1 meter of length is presented for 10 kilometer highway. It is just like in your scale down map, that in the map that 1 centimeter is presenting the 100 kilometer, this type of 1000 kilometer over the globe. So here it is presented, the 1 unit is 1 meter length, and 1 meter length is covered from the real-time system 10 kilometer highway. So
one is discharge, another is voltage, terminal voltage condition of the battery, and this is the e-vehicle motor.
So here you will see whenever the bigger size, that means it is not a tape recorder size motor or small miniature motor. It is half horsepower motor is there, and it will driven from this electric vehicle, e-vehicle motor. This motor is coupled with the axle and which will drive. It is a self-propulsion motor, and this power will be taken from this highway, and wirelessly it will take this power. And whenever the vehicle is not in moving condition, it is only charging the battery, this battery. You will see.
Motor is coupled with the axle of the wheel. So now I want to discuss the.
So here you see that over this, that road and the vehicle, whatever the distance, there is no electrical connection. Only it is AR core transformer. What is the concept of wireless power transfer? Wireless power transfer is nothing but it is a AR core transformer. AR is a magnetic material, and with the magnetic material you will pass on that flux, and it will cut the secondary. Actually, this flux will be generated the transmitter coil, primary coil, and it will cut the secondary. And whenever secondary will cut, so induced EMF will be there, and that induced EMF again it will be high frequency rectifier for DC battery charging. Then 1.2 kilowatt of incandescent bulb loads are there. I shall show you that in the working condition, and at the same time it will drive the self-propulsion motor. Please respond. It is clear up to this? Hello? Hello?
Yes, sir.
Please respond. Otherwise, that the network is ready or not. So we'll see.
Wireless power transfer system for static. Suppose the vehicles under static condition, you will see over the road or over the platform, this is the vehicle gap. There is no electrical connection in between that. And here 1000 watt resistive load is there, as well as the half horsepower motor is here. It will take the power from this unit. So you will see this, the power is delivered to motor. There is no connection in between this roadways.
I just skipped this some video, interesting side. It will be there.
The static condition.
Here, this is the whenever this it will work under the garage. That whenever this vehicle is under rest condition over this night, you have no need of this connection, electrical connection. So it will transfer this power from the garage to this one. That is the under static condition.
The static condition. Under static condition, 1000 watt power will deliver in this, and as well as if you switch on the.
So from this you will see that some operation of the transition that here.
Here, whenever it is coming over this next vehicle. So here again it will move across this vehicle part. So automatically it will trap this. It will sense automatically that vehicle is coming over the road. So it will automatically catch the power. Okay.
So this is like your your mobile tower, one transmitter coil, whenever it will couple, so it will deliver the power. It will transfer this in the second. Actually, intentionally, second coil is off at the time of first generation. This video is for first generation. Now the third generation project has been developed. All the coils are ignited. Actually, at the first generation, we have not ignited the all side-by-side coil, as because there is a mutual effect or anything adverse effect will come. So that's why intentionally, one after one, it has been ignited. So there is a gap here in the whenever
this other coil, so automatically it will has the power from the next coil. So next coil, if I ignite, so again, if I move this, so this coil is.
So you have seen that one place to another place, it will take this power, but this power on and off in the naked eyes, it is traceable. But in case of the speed of the vehicle, whenever it is 60 km per hour or 40 km per hour, it will move. That repetition, that off and on, this position will be minimized, as well as side-by-side transmitter whenever it is on. So the time of on-off, it will be minimized. Is it clear? Hello, anyone response? Hello?
Yes, sir.
Yes, so please respond as quick as possible. So that thing is automatically from one place to another place in 60 km per hour, whenever it will move, in naked eyes or visual condition, you cannot follow that this power is on and off. It is very quickly, it will transfer the power. So,
and again, if we move this coil to this point, so automatically it will transfer this, and as well as the battery charging. Here you see that
now here
is possible.
Here you see that one is dashboard voltmeter in the vehicle, e-vehicle, another is charging meter, ampere meter. This ampere meter is utilized for battery charging. Whenever the battery is charged only, so at that time, it may be 8 to 10 ampere charging, but whenever the self-propulsion motor will start, so maybe it will come 4 to 5 ampere, as because both the loads are coming over the wireless power transfer system. Here you see that whenever this sound is coming,
is taking this power from dedicated lane.
Here whenever motor is taking power, so the charging is 4 ampere.
Solar power as doing the grid power.
So that is the small initiative, and this work has been done group of project people. Here Professor Nitai Pal, Professor Orijit Boral, KC Jana, Professor Anirban Ghoshal is my scholars. He has completed PhD under my guidance. Dr. that is Devayan Sarkar, he is now faculty in NIT Silchar. So these are the group work. So small video has been shown. So we'll go to the.
There is some question from Dr. Priyadarshini Dhar, madam.
So now we'll go to this. That these are your work reporting in the Times of India and Economic Times. So later we'll see. But the thing is, heart of the e-vehicle, basically the wireless charging or maybe the wired charging, it is the battery. Basically, if you know the battery, show battery concept. In earlier session also from BITS Pilani, Professor Bhattacharya is taking this SOC. He has explained this thing. But
Hello,
something, yes, please. Please respond. Hello. Anyone is asking any question? Hello. Shall I continue?
No, sir. No, sir.
Yes.
Yes, sir.
Hello.
Yes, sir.
Please. Okay, actually, I shall be disturbed. I am confused that your network problem of that. Okay. So in this electric vehicle, I shall show you later that for the reporting of this, but I have to take this technical portion, that contact charging, wireless charging, but whatever over the battery, basically EV's heart is battery. If you take this comparison with the price, if the Tata Nexon car is 18 lakhs, out of 18 lakhs, the battery cost is 9 lakhs, 8 to 9 lakhs. So these are the 50-50 costing. And for that reason, actually you have to give the much more emphasis of the battery, how the battery will be handled. And that's why we have to enter in the small domain as well as higher domain. Everywhere it is similar. What is I am taking, basically the lithium-ion batteries are used in the e-vehicle, as well as some small Toto three-wheelers are fitted with, or two-wheeler fitted with lead acid battery. And out of these two batteries, comparison to that, we have to discuss this thing, but much more critical is the lead acid battery. If you know the lead acid battery, then you can cover up this lithium-ion battery, everything that every concept, every characteristics over the lithium-ion battery. If you know this thing, the characteristic of your lead acid battery, then it is possible to cover up. So better we'll go to the battery section, and this everywhere in the over these contents, you will see that a small application, even the electric vehicle recharging system. The small application is pacemaker battery. Pacemaker battery size is 2 milliwatt capacity, whereas the 15 kVA, that is the size of the Tata Nexon battery. So this battery size, what is the battery size, depends on that. Charging power is there, it will be regulated, but the concept is same. I want to ask you this figure that I want to show you, that one certificate from this Government of India. Is it visible in your portal? Please respond.
Yes, sir.
Yes, sir. This is a pacemaker battery rechargers for the enhancing the service life. What is this thing? This thing, pacemaker. Some relatives has pacemaker whose brain signals are not coming. So there the pacemaker is a unit which is a pulse generator basically. And this pulse will be driven in the heart. This pulse will be given to the heart for drive the pumping. So this pacemaker battery, if you follow this, the battery of the pacemaker is basically lithium-ion battery. And this lithium-ion battery lifetime is 10 years. And every time that you will get the certificate, warranty certificate, lifetime. Company will change the pacemaker. But what is the problem with that? Problem of changing the pacemaker. The changing of pacemaker, it will take the rest for 30 days. After changing, you will be bed rest for 7 days, then 21 days for rest. And you have a requirement of blood or anything else, or the cardiac surgeon is required. So it is a hazard. It will be your problem for the changing of pacemaker. Actually, pacemaker companies, they are giving free of cost the second pacemaker after 10 years. But this 10 years is variable for in case of the variable frequency pacemaker. That means for the player, for the staircase, whenever you are unfolding that staircase, then pulse beat are more required. So for this case, the battery of auto changing this frequency pacemaker, so it will take 8 years time, or maybe the 7 years, or maybe the 9 years. So every after 8 years, you have to change this pacemaker. So there, if I enhance the life, service life of the battery, so that will be better. So this patient can take rest. It is also under wireless power transfer. Basically, it is not allowed as per the medical science. Just like your 2C charger in the mobile, you will connect the charging socket and you will switch on your electricity supply. Is it possible? From the physical body, the medical science will not allow any wire connection. Is it not? Please respond.
Yes, sir.
So contact charging everywhere in the application, it is not possible. So in the battery charging, if it is wirelessly possible, that over the bed patient will take the rest for 6 hours or 8 hours. So his battery life or her battery life will be enhanced. 80% can be charged up or 100% can be charged up, but lifetime, that means first time if it is sustained for 8 to 10 years, the second time it will not sustain for 8 to 10 years, that it may be 6 years, third time it will take 4 to 5 years. So overall life after 2-3 charging slot, you will get the 20 to 25 years of life. So that's why enhancing the service life. So you are reducing the medical hazard. Do you understand wireless power transfer? So these are the applications, and it is granted, this patent is granted over the 31st August 2022 in the name of Indian Institute of Technology, that is the Dhanbad, and these are their inventor's name after the certificates, it is there. So all the things are there in this application. Now we'll come to this point that it may be pacemaker, it may be electric vehicle. We have to know the characteristics of the heart of the e-vehicle, that means battery. So if battery will cover up with the lead acid battery, and after that lead acid battery, we can transform it to this whole characteristics we will transform to the lithium ion batteries. So here the types of battery, basically the lead acid battery, if you go through this, that is if it will hide this charging process and discharging process, can you indicate from your that is window which side, which figure is for charging, which figure is for discharging? Anyone? If you hide this part also, so how can you diagnosis, make this diagnosis. It is load is connected, here generator is connected. That's why you can say, but by hiding these two, how can you say this reaction is for charging, this reaction is for discharging? Anyone? Anyone from the audience? Please respond.
Sir.
Please respond that my question is that if you hide this generator and load, someone can say that which side is for charging, which side is for discharging by visualizing this equation. Can you say? Anyone?
Sir, left side will charging the
Left side is this weak H2SO4 to stronger, and one is stronger H2SO4 to weaker H2SO4. Which one is charging, which one is discharging? Actually, this side here, by seeing the load or generator, you can say easily this is charging process and this is discharging process. But if you hide this point, and from the weak H2SO4 to stronger H2SO4, and this one is for charging. Basically, weak H2SO4, it will form the stronger H2SO4, sulfuric acid, and here the stronger is yes, please say.
Yes,
Hello?
sir. Yes, sir.
That means
yes,
here producing of H2O. That means you will add some H2O, so it will be diluted. So this is the discharge equation. Stronger H2SO4 to weaker H2SO4, weak H2SO4 to stronger H2SO4. That is the undercharging. Now the question is, why we have shown this? It is a current source. It is not the voltage source. Anyone have any answer why it is connected the current source? Hello? Why the current source? Why not voltage source? Anyone? Actually, you will. You have already given this. Yes, please. Yes, who are saying this answer is? Yes. Actually, in the case of fast charging also, you have indicated that it is a constant current charger is required up to 80%. So at the time of starting of the charging equation, charging state, so there the constant fast charging is required. So constant current source is connected. So here and here it is for discharging, load is connected for this. So this part is there. Next is the another indication, PbSO4 to PbO2, lead sulfate, it will form PbO2, that it will be under charge, and under discharge what happened, PbO2 to PbSO4, and PbSO4 is so dangerous. Actually, the lead sulfate, whenever this coating will come, it is looking like face powder. So this fine molecule, it will be covered up this total plate, anode and cathode. And there what happened, this whenever PbSO4 coating will come across the plate will be hardened. So at the condition of PbSO4, this will come much more in the last session, Professor that from BITS Pilani, he has explained this, the deep discharge condition. In the deep discharge condition, PbSO4 will be coated over the plate, and that will be hardened the plate, and plate will be damaged. So your battery life, if it is the 4 years, so the PbSO4 coating, if it is sustained for long time, so battery life may be 2 years. So it is drastically reduce the battery life, lead sulfate. So lead sulfate, how to protect this thing, that under the slower charging, later we'll see that lead sulfate will be avoided by means of, just like your transformer oil. If you purchase the standby transformer, distribution transformer, so standby distribution transformer will not be alone or will not be that isolated. So if it is stored in the store, so that deterioration of oil will be there due to the addition of moisture from the atmosphere. So always the primary is connected over the grid. So what happened? The coal loss will be happen due to heat generation. The moisture will not come. And here the lead acid battery, to protect the lead sulfate, whenever battery is fully charged, then also after the full charge, lead acid battery will be under the hibernating condition, that is the float charging is required. As the later it will be discussed. Is it clear? Please respond. So PbSO4 is a vital product which will that affect the battery life. Please respond. Connection is ready. Am I audible? Hello. Yes, please.
Yes, sir. Yes, sir. You are
As early
audible.
as possible, you will respond. Otherwise, the time will be that. Now that discharging of lead acid battery here, without seeing this title, I can assure you this will produce the water. So it is dilution of sulfuric acid. So that's why it is discharging. And for the charging also, this H2O will be added, and with the PbSO4, so PbO2 will be formed. This PbO2 is basically, it will help the battery life, that under the charge condition of the lead acid battery. Now come to this question. This is another interesting effect of discharge rate on the available energy from a lead acid battery. If it is for lithium ion, same thing, it will come. Effect of discharge rate on available energy from lead acid battery. It is a, that means your mobile phone, it may be for your inverter, household inverter battery, or whatever may be the application, torch battery, everywhere, that it is not linear. Basically, the faster discharge, this is the faster discharge curve, drooping characteristic, this is the slower discharge curve. Here I have to take the application. You can note down this, that faster discharge rate and slower discharge rate, how it will affect. I shall ask you one very simple question. Suppose in your house, one inverter set is there, 180 ampere hour capacity battery is there. So there, the 4 fan and 4 classical tube lights are taking load from the inverter. Now, if it will run with the 180 ampere hour battery 4 hours at full load, so if I reduce this, the 2 fan, 2 tube lights, how much time it will run? Anyone? Anyone can respond. Please respond. In your house, one inverter is there which can take the load of 4 fan and 4 fluorescent light. So it will deliver 4 hours or 5 hours battery discharge. If it will give the 5 hours time in the inverter mode, so 2 fan, 2 tube lights, whenever the load will be half, so how much time it will deliver the power? Anyone? Please respond. Hello. Hello. Hello.
Yes, sir.
What is the answer? Please unmute your mic and say. If
You are audible, sir.
No, I am audible. My question is, suppose one battery is connected with the inverter and one inverter is taking 4 fan, 4 tube lights. Now the load is half, 2 fan, 2 tubes. Earlier it will take 5 hours discharge. Now how much time it will take if the load is half? That means 2 fan, 2 tube lights. Anyone can give this answer.
It will be 10 hours.
Half of the time?
It is load is half, so 2 times you can expect. Is it like that?
No, sir. This relation is not linear.
Yes. That is my question. Relation is not linear. It may be for the lithium ion, it may be for nickel cadmium, it may be for alkaline rechargeable battery. All the discharge is not linear. So if it is 4 fan, 4 tube lights are taking load, so 2 fan, 2 tube lights, it will take this longer duration. That means instead of 10 hours, 5 hours will be double 10 hours, but it may take up to 12 hours. Am I correct? Please respond.
Yes, sir.
That's why in your house, whenever the power will not come back, your guardian or your senior family members are saying, please switch off some light and fan. That is their experience, so it will take longer time. Another experience, you can do this thing, that faster discharge rate and slower discharge rate in your basically our grandmothers on those days, the incandescent torch is there, incandescent bulb fitted. So incandescent bulb has 2 options. One is continuous discharge, push to slide, that is the continuous discharge, and push to on and push to off. That means for a fraction of 15 seconds, you will push to on and push to off. And other options is there, continuously for 1 minute you can switch on. So which one is better for any battery? Their practice, grandmother, grandfather in the village, they are doing this thing, that for 5 seconds, 10 seconds, they are switch on, they have switched on, and then again it will be switched off. They will not operate the torch continuously. Do you agree? Hello? 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 Please respond.
Yes, sir,
Hello?
you are audible.
That is the requirement. So here the lead acid battery lifetime in cycle. Here another concept, that it is also important for taking the battery in the domain for battery charging. The lifetime cycles versus average daily discharge. What is the thing? Lifetime cycle, once if it will be charged and it will be discharged, one lifetime is completed. This is the cycle. Lifetime cycle means once you will charge up this battery and again you will discharge this. As per your mobile operation, lithium-ion batteries operation, there also the average daily discharge is there, that it is the 10 or that 15% it is discharge, average daily discharge. So it will get that is the 4,000, then 4,500 lifetime cycle. And if it is daily 75% discharge, so what is your lifetime? That 2,500 lifetime cycles you will get. But which one you will choose? That this one or this one? That here it will see that this is your position, and here for 75% of daily discharge you will get this thing, that lifetime will be 2,500 lifetime. So in between that, once it will be charged and discharged, one lifetime will be completed. So someone has bad practices. In case of mobile phone, I shall assure you that he or she will go outside, he will travel by train or air. So after the 10% discharge, immediately he or she will put in the charging. So what happened? One discharge and charge, this lifetime will be completed. Do you agree? So here we have to optimize. That means 75% discharge or the 10%, 15% discharge. In between that, we have to choose the 50% or 40%. If it will choose, that lifetime will not be such affected. Is it clear? Please respond. Hello.
Yes, sir.
So this lifetime, life cycle, actually you will see it is also affected the deep discharge. In case of latter, from the characteristic we will see SOC condition, that someone habit is there in mobile phone, that it is giving red flag for the deep discharge condition. Please shut down your mobile phone. Otherwise, it will go to the deep discharge condition. So that will affect the lifetime of the battery. So this thing you have to remember for lead acid battery as well as your any alkaline battery or lithium-ion battery. So everywhere the same concept, the lifetime and the effect is there on the discharge. So this is the next cell voltage and specific gravity, and here it is time two part. One is the discharge concept. Is it selected over your portal? Please say. Hello.
Yes, sir.
Yes, sir.
Okay. So here you will see that specific gravity of the acid, that will be H2SO4 specific gravity. It will be decreased in the linear form, and the cell voltage is non-linear form. Almost 80% this crossing point is constant after that drooping characteristic. So this part you can allow for workable condition, that part. So cell voltage is constant as well as the specific gravity. Also optimize this thing. But after discharge, you have a need of charging cycle. So in the charging cycle, here you see the specific gravity in nonlinear mode. That is it will come, and after that it will saturate specific gravity, and charging, it will overshoot this point about the 2.2 volt, and then it will go to up to 2.5 or 2.4 volt. That is the charging after this full charge condition. So these two characteristics, one is discharging characteristics with the cell voltage and specific gravity, another is charging characteristics. So variation of cell electrolyte specific gravity and cell voltage during charge and discharge. Next is, this is the SOC. Very, very important for the battery health. In the case of the battery health, I want to mention this thing, why battery is under your comparable with digestive system. That normal charging, fast charging, how it will be affected, I shall explain. I shall take one example that in case of the digestive system, if I take this for the food charging, you'll take the competition of taking rasgullas for your digestive system. In 10 minutes, you want to take 50 rasgullas, and in 1 hour, you will take the 50 rasgullas. Which one is normal charging? Which one is fast charging? Anyone? Hello? Please respond. That for taking food, it is also charging for the digestive system. So normal charging is which one? Fast charging is which one? One criteria, within 10 minutes, you will take 50 rasgullas, and within 1 hour, you will take 50 rasgullas. Which one is normal? Which one is fast?
1 hour is normal.
Yes. So what happened? Actually, in the case of the food digestive system charging, basically in 1 hour, if you take 50 rasgullas, if you have no sugar or diabetes, no problem. So it can digest. But then in case of the within 10 minutes, if you take the 50 rasgullas, maybe you will start vomiting. Is it clear?
Right, sir.
So your body will not absorb this thing. In the battery also. Yes. Yes. Yes, please. Okay. So in the case of this, normal food charging system is the 50 rasgullas in 1 hour. In fast charging, you have seen that 10 minutes, within 10 minutes, 50 rasgullas you are taking, but all on a sudden you start vomiting. Okay. So this is not accumulate the food charging for this fast charging. And in the case of battery, every day, if you start the fast charging, so battery health will be disturbed. Is it clear? Please respond. So the fast charging will be avoided and normal charging will be there. So state of the charge, here one thing will be there, that 100% charge is full charge of SOC, state of the charge. At that time, specific gravity is 1.265. So 100% charge in this case, the 2.12 voltage, battery voltage is 12.70. So this part is there. 75% you can discharge, then 50%, in 25%. Sometimes you will see that in case of our prime ministers are saying indigenous technology. In the case of here, lead acid battery in foreign books, you will see that 25% is the deep discharge level. So this is the deep discharge level is written in the foreign books in IEEE, But the Indian technology, Indian environment, actually whatever the environment in India, that is not actually, it will not match with the Indian environment, Indian road condition. Later on we'll see. So this Indian scenario, Indian atmosphere, we are considering the deep discharge condition here over the 50%. And what is this thing? 50% deep discharge. That means if 180 ampere hour battery is there, how much we can discharge? 90 ampere hour. 50% of the full charge. Is it clear?
Right, sir.
So in the 180 ampere hour in European country, you can discharge up to 135 ampere hour. So that is the difference between indigenous technology and that part. So that is also important. Next is in the deep discharge, you have to know this thing. What is the deep discharge? How it is affected the battery health. I shall give you the for the your diabetic test, that is the your PP or fasting of the sugar level, that you have a need of how much blood? That 15 to 20 ml, is it not? But in spite of this 15 to 20 ml, if you take the 250 ml of blood from the body, so what happened? Your brain, your oxygen flow in the brain, it will be disturbed, is it not? So that's why you are saying, you have seen that for donating the blood 250 ml, they are giving the blood under the sleeping condition, under the laying condition, not sitting or not walking or not standing condition. Is it clear? So here the basically deep discharge, the blood sample from the physical structure, it will take very few, 1% of blood or 0.1% of blood it will take, and after that it will be tested. Here also same thing, if the whole charge will be discharged, so battery positive, negative, that means anode and cathode plate will be covered up with the lead sulfate. Or in the case of other, the alkaline battery or other thing, same effect will come. So this part is over. Next, the SOC condition, and here the charging, that is 3-stage contact charge control. Actually it is showing that fast charging, then the constant voltage charging. Actually fast charging is this one under this domain. Is it clear? Bulk stage, that means charging current is constant, and so you have started this lead acid battery with the constant current generator, and 80% of charge will be given from the first charging. Next, what happened in the normal case also, it is under the bulk voltage. This stage is absorption stage of charge. Bulk voltage, here the voltage is constant, charging current is variable. Is it clear? So actually the power is constant. Basically the power supply, here the current is constant, voltage is variable, so that it can manageable. Here the voltage is constant, the current is in the absorption stage, it is linearly, it is diminishing. But here the third stage, what is third stage? It is only for lead acid battery. It is not required for the lithium ion battery. Later that will, whenever we will complete, today the up to this contact charging, we have a need of concept that battery, and tomorrow as the another session for this wireless charging system. That is basically, it is depends on the lithium-ion battery and the power electronics converter. Here we will see the how it will be charged through contact and how it will be charged through the wireless. So most probably is over, madam.
Yes, sir, but Priyadarshini ma'am, you have some query?
So better I shall just, if you have any question, you just please say and conclude. Tomorrow we'll complete the second part. Anyone has the question?
Okay, thank you, sir,
Okay.
for your that nice lecture and wonderful lecture, and also that one is very informative for us also. Okay, and also we are waiting for your next session.
Yes, there we'll see this. This is the first, the health of the battery. If we know this thing, this is the heart of the EV. So after that, we'll apply the application in the second part.
Okay, thank you, sir.
Okay.
Okay, thank you, sir.
Okay, shall I?
Yes,
switch
sir.
off?
Yes, sir. For today.
Oh, thank you.
Okay.
Thank you.
So
Thanks.
good night, everyone.
Good night.
You can leave also. And the feedback links are also given. Attendance is also given, and take that one. No problem. Okay. So just for today, we can conclude the session. And tomorrow, that one will be start again from 6 p.m. Okay. Good night to all.
Okay, madam,
sir.
tomorrow
Yes,
I
sir.
shall give you the
Good afternoon, Rajiv sir.
গুড আফটারনুন।
কেমন আছেন?
ভালো আছি, ভালো।
2018 31st জানুয়ারি আমাদের প্রোগ্রাম ছিল কলেজে।
আচ্ছা আচ্ছা।
আর তখন আপনি এসেছিলেন।
হ্যাঁ।
আবার 2025 7 বছর।
হ্যাঁ, মাঝে তো করোনার জন্য অনেক ডিসরাপশন হয়েছিল।
হ্যাঁ। So 10 in moment 20 participants.
স্টার্ট করে দিই, নাহলে টাইমটা তো চলে যাবে। আস্তে আস্তে জয়েন করুক। Good afternoon, everybody. Good afternoon, everybody, and Shubho Panchami. Mr. Rajiv Kumar Das from CESC, Calcutta Electric Supply Corporation, is our today's first speaker. He graduated in electrical engineering from IIEST Sipur in 1983. He joined CESC Limited in 1983 and retired as Deputy General Manager in 2022, presently working as consultant to the company. Mr. Das worked in the area of electricity distribution planning, regulatory affairs, CapEx budget planning, monitoring and control, project execution or management. He involved in consultancy jobs for reform activities of distribution utilities in key Indian states and abroad in association with global professional services companies. He has experience in implementation or policy making, policy advocacy towards smart grid initiatives, demand side management, energy audit, electric mobility, etc. Mr. Das is also attached with some training on distribution network planning, regulatory, renewable energy integration, EV integration, smart metering, demand side management, etc. to electricity distribution personnel in India and abroad. So, sir, please start your session.
Good afternoon to everybody. One small change in my introduction, that I was there in CSE till April 25. After my retirement, 3 years I was there as consultant to the company. And thereafter I am fully retired since April. So now today's our subject is impact of EV charging on electricity grid. So why electric vehicles? So there are serious concerns about pollution in our cities, in our country. So there is a record that India has 13 out of 20 most polluted cities in the world. That is the concern, major concern. And on economics, so we import 85% of petroleum requirement from outside. And often in some months, if we see the data of Department of Petroleum and Natural Gas, Government of India, recently I was observing that it is often beyond 90% in some months. So lot of drainage, money towards importing petroleum products. And again on air pollution is responsible for 12.5% of all deaths in our country. So our 1 lakh children below age of 5 die due to bad air in our country. So these are the major concerns why we should opt for electric vehicles. And the road transport, so it accounts for 12% energy related CO2 emissions. Major is, thermal generating stations, and road transport is no less. So these are the concerns for which Government of India, not only Government of India, state governments, they are also promoting electric vehicles. Now IQAir, anybody can check the website. They report this air quality in various cities and towns across the globe. So I took some snapshots from IQAir regarding the pollution level, air pollution level. You see Delhi, Kolkata, all big cities, so condition is very bad and always it is red. However, Vizag being a city on the seaside, a little bit better. In even our small towns, relatively smaller towns like Kalyani, Barakpur, everywhere, this air pollution conditions is not good, or rather bad. Now, not only in India, across the globe, see, IC engines, they emit a lot of carbon dioxide into the atmosphere, and it is approximately 20% of total world's emission. So not only in our country, all countries, particularly the advanced countries, they are promoting electric vehicles. Now, you see, these are the electric vehicles that we see on the road: bicycle, then scooter, three-wheeler, four-wheeler, and buses, electric buses. Though recently in Kolkata, one ferry service started with battery operated. Now there are various projections. So the CAGR could be more than 50% in next 4, 5, 6 years time. So we expect that there is a huge market and huge penetration of electric vehicles, and for which you see the distribution company in particular, they should be geared to take the challenges. Now, various states, almost all states as of now, they have prepared the electric vehicle policies. So major considerations for almost all the state EV policies is, first thing is job creation. We expect that there will be some employment towards for charging, for maintaining, etc., for these electric vehicles. And in the policies, almost all the states, they have target for electric vehicle as well as EV charging station. There is investment target as well. Almost all states, they are providing some relief on interest for buying the electric vehicles. And states, they have identified some cities for as smart city where electric vehicle will be heavily promoted. You see, long time back, I went to China about 10 years back in Hangzhou. There I have seen in the city that IC engines, petrol scooter motorcycles are not allowed inside the business district. All are battery operated. Now, there is some budget allocation by the states for this promotion of EV. A road tax and car registration exemptions are also there in some states. And there is some subsidy support for EV charging as well. So other incentives towards scrappage of old IC engine vehicles or retrofitting. You see in Kolkata as well, there are parties, they contacted us to retrofit some of the vehicles, say Maruti van with battery. And also states, they are also providing some incentives towards electricity tariff for the charging stations. Electricity tariff for the charging stations, they are kept at a much lower level. So UP, they have policy, it was, you see, a little while ago, then Delhi, then Karnataka, Maharashtra, almost all Tamil Nadu, in that same line that we discussed in the previous page. Now, so far as Government of India concerned, so you see, they started in 2020 with that National Electric Mobility Mission Plan. So DHI, Department of Heavy Industries, they are the nodal agency for promoting this electric vehicle under National Electric Mobility Mission Plan 2020. And under that mission plan, a scheme called FAME, Faster Adoption and Manufacturing of Hybrid and Electric Vehicle in India, undertaken. So target is to 5 to 7 million hybrid and EV from 2020 onward. You see that time because of COVID, there is some backlog. Then under that mission plan advocated government policies, incentives, subsidies for demand creation of electric vehicle as well as charging stations. Some targets were set and the results for that, if we can meet the target, would be that avoiding 120 million barrels of oil and 4 million tons of CO2, etc., etc. And total investment was assessed at 20,000 to 23,000 rupees crore. Now there is another scheme by Government of India, Deen Dayal scheme. Primarily, it is that time it is to promote battery operated electric rickshaws in Delhi, in some other states as well, Tripura, etc. Then FAMES, under the FAME scheme, initial first phase of FAME, it was for the period of up to 2019. Then mainly focus on technology development, demand creation, pilot project, etc., etc. And 14,000 crore invested in creating infrastructure and promoting use of EV that time. It was the first phase. And 2.8 lakh vehicles were supported under FAME 1. Then came FAME 2. FAME 2 total outlay was 11,500 crore. Incentives for two-wheeler, say 20,000 for 10 lakhs, e-rickshaw 50,000 for 5 lakhs, four-wheeler